You are currently the only person in this conference.
Batterien für Catchboxen.
Ja, das hatten wir vorher gemacht, die haben
Die machen das echt.
Nein, was das keine Musik sein soll.
Deswegen sind sie offen, machen die rein und dann fertig haben wir das in die Catchboxen.
Sie haben
alles klar. Da muss die Batterien schauen.
Ja.
Passt. Das ist aber Spaß.
Ja, das ist ein Weg, das
ist gelesen.
Das Voller uns alle in Becher explodieren lassen.
Im Libanon. Also, die Hezbollah-Kämpfer kommunizieren nicht über Handys, sondern über Pager, weil die nicht ortbar sind. Die wurden offensichtlich vom Mossad abgefangen, wurden umgebaut, wurden mit Sprengstoff beladen und fernsteuerbar zugbar gemacht. Und gestern wurden sie gezündet. Ich habe die Bilder auch nicht gebraucht. Die geht doch nicht. Und das hat funktioniert. Das muss man sich mal vorstellen.
Und jetzt der iranische Botschafter in Libanon auch so einen Pager hatte, das muss man vermuten.
Das ist ganz. Das ist wahrscheinlich das Nein, es ist ganz. Was da passiert. Aber wenn man ansieht, dass so das muss funktionieren, was ich schon gesprochen habe. Okay, machen wir es einfach weiter. Wir wollen die Batterie bezogen sind, das ist jetzt. Wir kommen wieder.
Ich wollte Sie vorhin auch nicht, meinst du, selber auch nicht, dass ich noch die Video reingeben muss.
Ja, das ist schade. Sie müssen es ja trotzdem. Wir sind jetzt 10 Minuten umsonst gelaufen.
Das ist schade. Das sind die erste Runde noch, die zweite Runde noch.
Nur die dritte Runde. Aber das sind jetzt die Verantwortungsbewusst. Gut, machen wir was ein bisschen.
You have less to
Yes, I know, it's kind of ridiculous, but
Okay, I can read
yeah.
that.
L1, this one right here.
Yeah, I need to take a guess.
Yeah, sorry.
Well, I'm going to turn off beacons. No, it just like, it like froze. It won't turn. Oh, key 6. 8. Yeah. Okay, go off. Okay, 1. Let me fire up 1. Okay. I guess I will get started in training just so they feel like we're doing something. I'm going to focus on. What do we want them to focus on?
I know, yeah, I'll do it. Hopefully this works. If not, then.
No, it has issues. So can we switch watches?
Let me try to read here. Resync them all. Well, this is not maybe the right or not. So these might not be right.
Watch that.
Or not. Okay, no touching.
Because at first we were London, and we stayed there for the weekend. And I usually try to plan it where I fly out at like 8 in the morning and get off 8 at night. But they have a curfew that after like 9 or 10. Yeah. So, yeah. Our police had some issues, so they couldn't get another. So I said to your network, luckily I don't know, I couldn't. I was trying to look at some different stuff with the DSPs.
Well, what's your life? So you were spending over 10 hours in the airport?
Well, she was in Paris.
Ah, she was playing in Paris.
Yeah. She went to a concert.
Okay.
And then we were just in
Hey.
So I ended up just being away for like 2.5 days straight.
Oh.
And then all the flights were delayed.
Couldn't you just go back home?
I could have, but it takes like 4 minutes or so. And at that point I was like,
You wouldn't need the security there. Okay.
yeah. So I just moved to the lounge and hung out.
My wife is looking at it.
Yeah. when Alexa ported that over, I don't know. I have to. I think there's maybe one part that I have to get copies from the like the CPU from the Vienna data center. Which I think I have a couple of functions to do that. But I think there was some other verifier errors where going from the Vienna memory back to like with the
So it's actually a really mechanical part. That's cool.
yeah.
Yeah, that's good.
Yeah, I know. But it's also like, I don't think that works until 69. So you
Yeah, the perpetuals are almost 30 million. I mean, a couple of like, yes, I did.
Yes. Because I had talked with my last and I think the problem is he focuses on versus like whereas it's like all this stuff is like
But if you have something you want,
Okay, so we go.
it's alright.
Computer, I got something for you and your students. I got a bag from yesterday, and I cannot carry it back. My luggage is full. Thank you. No, it's just like oh, thank you.
I looked at their content like they used to say like they did with the DVD player, they're old enough, you know what I and I saw there are people actually outside. You took it what kind of situation?
Okay. Yeah, I'm impressed with your eyesight.
Initially, but after
How long is the lecture?
one day,
I kind of really reminiscent of the old Sony. Which company?
Yeah, it's open until if you push the button for the layer,
You gotta look that up with I don't know, it's like a flip control. Like people will share with you. Yeah.
We also broad kernel this year.
Sorry?
We also write the next
It's my main well, it's not my main active.
So, yeah.
But that's my main.
You need a band like this.
Sometimes I have to use this when I'm getting old.
More characters are really challenging. I think I'm 1 year away from like getting to the 5 seconds.
Yes, it's the same, I guess. If you go to root LPC,
Let me see if it works. Take presenter. Can I move the slides? Why it doesn't work? Where's page up? Okay, here. Yeah, it's working. More or less. Be able to upload the slides. I think I need to take presenter from here. Upload presenter.
Oh, hey! How are you? Good. Good to see you. Good. Yeah.
I'm shepherding yours.
Oh, nice. Yes, yeah.
We need one of the planning committee shepherding into the room, so I picked this one.
Okay. Good.
Nice. I'm uploading all the slides. Doing my homework.
Yep. A tiny little machine.
With a tiny little machine, yes. The DVD player, they used to tell me like, oh, you brought a DVD player. Because I was showing demos, they were like, oh yeah, that's not
what's
like
really great is when you're on the plane though, where you have your meal and your laptop doing the work side by side.
And I have this, I put this in my bag wherever I go.
Yep.
I can work. Okay, let's see, all the slides are there, maybe. So
There is power up here, right? I always make sure each one has power.
the power, yes.
But unfortunately, the room doesn't have power.
So if I take presenter from here, theoretically, why it switch to this one?
No, I can do that one.
Okay, so if you go to yours, that is going to be this one, I guess.
yeah.
And then it's just, that should work. Now we go back to
Okay,
the
so
default.
here I pick my presentation and then just click it to. Okay.
Yeah. Oh.
Okay.
Yeah, we need to do like the.
Okay.
Where's the first slide?
Oh, really?
No, that's fine. I wanted to
Right.
go to the beginning
Oh,
of this
okay.
one because we need to say thank you to the sponsors and welcome everyone.
I don't know how to.
I don't know either. I'm supposed to do.
Maybe you're supposed to click this button.
Oh, that's the first one. Okay.
Is it space? What was the? Oh,
No,
arrows.
that's the first one. Okay, just because we just need to say
Yeah.
welcome and thanks to the sponsors and the harassment code. Be nice, don't insult people.
For us, it's our first conference. Really?
I got lost in my normal work, assessing some conference for digital documents, but I never attended.
That's a picture, so I have to talk a lot, but not as actualized as here we are. Yeah,
see if there's. Okay. Wait a couple. We can start. There. Are we ready to start? You guys ready? Okay, welcome everyone. This is the SCADX microconference. Just a few words about, I want to say thanks to all our sponsors. And let's see if I know, yeah, be nice to each other. Really short summary. And we are not on a break. We're gonna move to the first presentation. There we go, with Taejun, that will talk about the status and plans for SCADX.
Thank you. Real quick, just mention notes and one last thing.
Oh yes, thank you. If you, is it working? Yeah. Feel free to just log in and take notes in the shared notes. Whatever you want to type, even if you have like random notes, just feel free to put there, and we will eventually filter out later, but it's important to have notes. Can go.
Hey, nice to meet you. I am Taejun from, I work at Meta, and I've been working on SCADXT for the past few years now. And I was expecting 15, 20 people who were already working on SCADXT, so my material is low effort, so sorry about that, but well, we'll see how it goes. Okay, how do I go to the next page? Okay, so in the simplest, this is how it looks, right? I mean, in the corner, like on the left side is the corner, right? There's a scheduler core which interacts with the rest of the corner, and there's a lot of threads in the corner, and and user space threads too, and they go to sleep, they wake up, they wait for events, and all that happens. And if you really overly simplify it, the only two main operations which happens to the scheduler is that something wakes up and I'm ready to run, right? That's the in-queue event, right? And then something happens on the scheduler side, right? And run this guy, right? That's the pick task, pick next task, dispatch, right? Basically those two operations are the two most fundamental operations, right? So there's a scheduler core has this abstraction implemented, and then it has its own interface where scheduler classes, which is different scheduler implementations in kernel, are plugged into. So SCADXT just plugs into that. So it's one of the scheduler classes, and it gets the events from scheduler core, and it forwards that to the cloud thing in the bottom, which is just a giant BPF program, or a set of BPF programs implementing operations that SCADXT exposes. So basically SCADXT, what it's doing is that it's bridging scheduler core events to this, the events which are more friendly to these BPF programs, and which are a lot safer. Right? So inside the BPF scheduler, who here has worked with BPF?
Genau, das haben wir
Who has no idea what BPF is? That's really cool. Most people know. Okay, so it's basically you write code in C, almost C, right? And you compile it to into an object file. You upload it to the kernel, and kernel verifies that it's pretty safe to run. And then it translates to native code, and then it runs it, right? That's what happens, right? So you write this scheduler in BPF, right? And then you upload it. It's basically like a big function table, right? This is my in-queue, this is my dispatch, this is my whatever, these operations, run it, right? And the SCADXT core rules it, and then does a lot of plumbing and dancing, and then the scheduler switches to the BPF implementation. So the main operations, all the operations get forwarded, in queue, then BPF scheduler can do whatever you want to do. There are abstractions called DSQs, just because, so you can just use pure BPF data structures, arbitraries or whatever have you, but implementing complex data structures in BPF can be a little bit tough or inconvenient at the at least. So DSQs are it's just kind of helper abstraction, right? So you have queues which can be FIFO or ordered a priority queue that you can use a little bit easier. So you can have any number of DSQs, and then you just put your tasks in there. Oh, this guy woke up, put it there, and then when the scheduler call asks, what should I run next, right? Then the dispatch event happens, and then you pull the task out of it, and then you give it to the kernel, right? Then it runs it. And another part, which is kind of a little bit different, is that BPF has these maps, basically like, I don't know, like in programming language, like modern programming language term, like containers. So you have like this pre-built data structures. And one thing really nice about BPF maps is that it's a really rich and high performance interface between kernel and user space. So you can move a lot of data between kernel and user space really fast. So BPF, with BPF programs, it's kind of easy to build this kind of hybrid model where you do certain like hot-path things in the kernel, and then you do more complex things, like math involving like floating points in the user space, right? So a lot of schedulers kind of do that to a certain degree. So that's basically what it is. And SCADXT, the kernel feature is just implementing the interface, and then there's a bunch of schedulers that we are working with in a separate repo where we're all working together with. So so kernel support, that's the Git tree. It has been pending, and I'm hoping that this will get merged in this merge window, which is this week and next week. So we'll see, but I mean, I'm pretty hopeful that it will get merged this time. What is there is that this basic scheduling, all the things that you need to write like a system-wide scheduler for a single system is there. And then there's a CPU frequency scaling support, CPU hot plug works. There's the basic C group support. It's not like fully featured, but you can do the weight interface and all that. And like helpers, right? I mean, to make things easier, there's like debug support and things like that. And one thing, I can do this later. So, and there's the separate repo, which basically hosts all the SCX or SCADX schedulers that we are working on, and the GitHub. And many people in this room actually work together in the repo. So we have multiple schedulers there. It has been, we've been working on it, for me, a couple of years, maybe 3 years, and others maybe over 6 months, a year. But schedulers, any complex subsystems, in implementing like low-level system features take a while to mature, right? So we are still in very early stages, building up, learning things and building things. But we still have multiple schedulers which are showing fairly good results already. So there's 2 schedulers, LAVD and BPF land, which are more focused on like your personal use, right? LAVD is going to be deployed or in the process of being deployed on Steam decks, so it's more gaming focused, and it's showing like more consistent FPS, higher performance, a little bit lower battery usage and things like that. And the BPF land is another scheduler which is focused on like a laptop usage, and it's showing better interactivity, low latency responses, and better battery behavior and things like that. And there's also user space scheduling, where if you think back this diagram, right? So BPF scheduler part is you can imagine a scheduler implementation where the BPF part is big, user space part is really small. And you can also imagine an implementation where BPF part is really small and BPF, user space part is really big, right? So that's what Andrea did. So what happens is that the BPF part is just kind of forwarding scheduling events to the user space process, and all the decisions are made in the user space process, right? So So we're basically writing a scheduler in your own user space process, and like any other application. So that's those are Rustland and RL-FIFO. And Rustland is actually quite usable, surprisingly. So at the beginning, I was kind of skeptical because just the overhead of folding all these events and getting it back seemed to be that it'd be fairly expensive. But in practice, it is more expensive, but not too much. So it's still really nice. And then we have something called XX Rusty. That's something Dan Schatzberg in this room started, and then it's mostly focused on implementing, kind of experimenting with load balancing. We had a kind of interesting problem because in SCADXT schedulers, right, CPU to request queue or CPU to queue mapping is flexible. You don't have to have like one queue per CPU, which means that multiple CPUs can share a single queue, and that kind of makes load balancing calculations really interesting. So there's kind of our way of experimenting with that and see how that works. And then there's a customizable soft partitioning scheduler, layered, which I'll get to later in the next slide. So what is all that good for, right? So LAVD, BPF-land are probably more, I don't know, closer to home, right? I mean, it's your PC, your laptop, your gaming device. But this is me trying to deploy layered in our production workload. And it's a really latency sensitive one, and people really care whether the performance is a little bit higher or a little bit lower. So basically, what's happening here is that it's the request response server, right? And then how much you can process in a single machine is regulated by how quickly you can respond, right? So the higher, I mean, if you can maintain your latency, tail latency lower at higher bandwidth, right? Then the machine can just process more, right? Which leads to more money, I guess. So this is it doesn't really matter the exact metric, but the x-axis is time, right? And y-axis is bandwidth, right? And the two graphs up and down, upper and lower, are basically showing the same thing, but slightly measured at slightly different points. And the vertical red lines is just me changing the configurations and the scheduling implementation. So what I'm showing here is that to set this up, right? It takes like 2 weeks, right? It's like and it's in these 1,000 machines, and I don't know why, because I'm not really too familiar with all the production setups. But like even for like production engineers, it takes who are familiar with this, like setting up and calibrating AA sets and comparing them and making sure all the numbers are right, takes a while, right? And then if you try to change the scheduling on these machines, right? Then you have to like reboot the machine. Then everything is off the whack again. Stabilizing takes multiple days and all that. So here x-axis is like a minutes, right? So I am changing scheduling over 1,000 machines, like 15 minutes in 20 minutes or an hour interval, right? So I'm not limited by how quickly I can apply the changes. I'm limited by how quickly I can make those changes and how quickly I can read the signals, right? So the deployment part just goes out of doesn't become a bottleneck at all. So here I'm just trying like different solutions, and in where the green lines in the upper graphs, green lines goes up. There's a happy place. Right? I'm just trying to understand why that's happening, how to hone in on that configuration. So the reason why this is possible is because first of all, you cannot crash machines. Stands bugs. I mean, there can be bugs, but you can write really bad scheduler, and you can store out the machine. But there's a hang check timer. So after certain seconds, if the scheduling is not right, it's going to get kicked out, and the machine will recover, right? So there's a lot of safety mechanism. The machine will almost never crash. So you can do basically whatever you want to do, deploy, see what happens. If you're not happy, revert it back, deploy the next one, and on and on and on, right? So the development cycle for this becomes really short. So compared to, say, days, get compressed to like 15, 20 minutes intervals, so which really accelerates what you can do. So that's my I don't know. It's to me this is the first evidence which really showed me the value of doing it this way, how powerful this can be. I'm sure like all other developers who are working in different parts of the projects, experience it in different ways, but I'm sure this is helpful for most people. So right now, what we are doing is that because it's early days, we are keep building up and learning. It's going to take a while because there's just a lot of things that you have to build up, and we are not there yet, obviously. So we're in the process of just everybody's ramping up, building, try to see how things play together. And all the while, we are trying to gain as many practical wins as we can get. As a sanity check that we are doing things right. It's always important. And also, it's just nice to have wins, right? So LAVD being deployed in Steam Deck, as far as I know, or is going to be. BFF land is working really nicely for personal machines. So layered, we did like the slides that I showed before that, the graph. So we are doing multiple of those experiments with different production services, production applications in the fleet. And it's already deployed over 1 million machines, and it's doing really well. And we're like trying to expand that and generalize that. Yeah, and of course, because it's early days, we're trying to build up our community, how to ramp up people and all that, and how to make it more accessible. And making it easily available is the important part of it, especially because we are still not in the kernel feature is not upstream. So accessing it can be a little bit difficult. So CacheOS guys, did a really good. It has been a great supporter, and then continues to be a great asset. And so a lot of kudos to them. But Arch, Ubuntu, Fedora, Nix, OpenSUSE. So if you're running most popular distros, installing a kernel which supports KDXT and playing with it shouldn't be that difficult. It basically, if you just want to run a KDX scheduler, it just comes down to downloading the package and just running the binary, right? That's all there is to it. And there's a Slack channel. Now it's like a couple hundred people, so come join us and ask anything. We are trying to, we are pretty helpful and friendly. So if you have any questions, we'll be happy to answer. We have a weekly office hour. Show up and say hi. It's always nice to see people. Right, and there are a lot of things that we are doing and we will continue to do, but like longer term, that what I don't know, like more architectural things, bigger picture things that we want to do. One is composability. If you remember what I said about like these multiple schedulers, right? They are kind of concentrating on different layers of scheduling, like LAVD, BFF land. It's basically like kind of concentrated on like a timeline management, right? You have a group of CPUs which are tightly coupled, and you have like a thread which you want to run. Where do you put where, right? And then Rusty is more focused on load balancing. So if you have multiple of these groups of CPUs, so if you think about the modern AMD CPUs, they have multiple CCXs, right? So the different S3s. And if you ignore those boundaries, your machine is not very happy. It's a lot slower. So you want to have like something which is grouped together, load balanced. So that's what Rust is concentrating on. And then there's like kind of the soft partitioning that what SX Layered was doing. And what that is if you have like multiple types of workloads on the system, and most systems do, even if you're like laptops and you have like cron jobs or whatever running in your main session, your graphical composer and whatnot. So there are like different characteristics that of workloads that are running on a system. On the servers too, the actual workload, which is latency sensitive, a lot of management stuff, all the monitoring stuff. So they are kind of different classes of workloads. And if you kind of group them and soft partition the machine and treat them differently, you can get a lot of cache locality benefits. and just scheduling policy, which is more fit to each group of tasks. So those three are, if you think about them, kind of layered, right? They are connected, but not quite solving the same problems. So we want to make that composable, so that not everyone has to. If LABD wants to solve like timeline problems really well, but don't really have to implement, right, the load balancing over and over again and the soft partitioning over and over again. So we want to make these things composable, so that people can just pick components and assemble a scheduler they want. And the another thing, which is probably a longer term, is that it's a little bit similar to composability, but a lot of, and it's on the servers, nowadays run more than one workloads, and they may have different scheduling requirements, or even like application-specific scheduling, right? So maybe the application want to hint the scheduler that I am something, treat this differently or whatnot. So if you want to support that, right, we want the kernel to have kind of stackable scheduler support, so that you have like trio of schedulers where higher level schedulers distribute CPUs to lower level schedulers, and then that implements in turn hierarchy of schedulers. Attached to C-group hierarchy most likely. So that's something that we are working towards. It's going to be a little bit longer term. So yeah, that's the status and the plans. Any questions?
You had this beautiful graph with the data where you were switching the schedulers. Sure. But there's just so much noise in this. I mean, can we actually use this kind of data to derive statistically significant answers about which scheduler is better?
I'm not sure I quite followed the question, but so for something like this, right? Like the end result that we want is fairly clearly defined, right? We want the graph to go higher than the control graphs, right? So maybe it's just not clear enough. But if you just ignore the lower lines, upper group of lines, there's green line and like two other lines, right? So the two other lines, the dotted lines, are the control group. They're the the default settings, the kernel scheduler, and the green line is the group, the set of machines that are running the KDXT scheduler. So in this case, NS, right, it's really simple, right? If you can make that line go higher, then you're happier. If it's lower, you're less happy. But is that
sure? But if you take the average and the variance of both lines, then they overlap.
Oh, okay, yeah. Let me okay, yeah. So this is the happy part of the graph, right? So this is all different configurations and different schedulers that I'm just constantly switching to find out which one is working better. And then this is ultimately the eventual configuration we landed on. And there are like multiple ways to calculate this gain, but over a long time, so this is just during iteration, I'm just doing this to find out the right configuration, right? So after this, once I was happy with this, then I ran that configuration for like several days. And then the production team ran it in the S scale for like a week, right? And then the eventual gain was like 4% or something like that. So yeah.
Okay, thank you.
Me or? Okay. On the future work slide, I was in the future work slide, the last one. Right. I was wondering if there is anything you learn by implementing all these different schedulers that I guess the group can think to contribute back to the kernel schedulers. Anything that you plan to?
Possibly, but I'm not sure that's like in our like direct roadmap to do. But I think it's more in the lessons we learn. So for example, like here, like where the configuration is better, right? So the main things that gave us the gain, we can and could easily verify that by just turning off different part of configuration, was like a better work conservation. Just not letting CPUs idle when there's work to do. And the second thing was soft partitioning. where you group related threads as much as possible into the same set of CPUs, and also like for things which are not latency sensitive, right? Pack them into as few CPUs as possible, right? If something doesn't care whether it runs in 20 milliseconds or 40 milliseconds, right? Don't spread them out. You just pack them so that the rest of CPUs are available for latency sensitive ones, right? Then you get the cache advantage, dirtiness advantage, and also you possibly get higher frequencies on those CPUs, right? And what was the third one? So, but I mean, the lessons we run are fairly generic, I think, at least up until this point. And there are like some specific part, right? I mean, like treating certain threads more specially, right? I mean, prioritizing them higher than usually possible. So I don't know. So for example, like soft partitioning is kind of, as an idea, is fairly obvious. I don't know how the interface should look like on the kernel side if we bake that into the scheduler. So right now, I don't know. But I mean, it's just trying to learn.
Okay, so one of the reasons why I was kind of a proponent for SCEDX was because my long-term goal that I would love for the scheduler to be is have I don't want to say pluggable scheduler. I would be almost like scheduler governors. So basically, kind of like power governors. If your system wakes up, you have a type of governor. So there's like right now 3 type of scheduling classes or governors, I would say. The one is kind of like Meta, Google, backends, huge data systems. That has different requirements to me than, like, I work for Chromebooks. A Chromebook machine doesn't need a scheduler that's made for scheduler there. Then you have the embedded devices. So the 3 classifications I would say is, at your level, is a multi-user, multi-functionality, high-level scheduler. Chromebook is a single user. You have a single interface. Everything in there is optimized for a single user. The embedded has no users. It's event-driven only system. These 3 systems, and I've always I had the problem with the one scheduler to do everything has issues. I think that's one of the driving forces of SCEDX. If we actually had 3 different schedulers like that, or governors like that, this is where I think SCEDX actually could play a role where you could have those that are focusing on the enterprise do like, hey, I have this algorithm. Would you like to try it? So everyone in the enterprise could try it, and once you find something you like, you can then roll back into the governor, into the real C scheduler. Same thing for desktops, and this is where I think SCEDX would actually be powerful, because ideally I don't really want everyone implementing SCEDX. To me, SCEDX is the experimental. Let's try different things, But if you actually had a single-use scheduler, but I think the problem is that we had one scheduler for all these that forced this fragmentation. I don't know what your thoughts on that.
Yeah. So largely agree with it. So there are, it's not always simple, right? So there are like a really generic part of the lessons that we learn, which can probably be directly applied to the, one scheduler for all scheduler too. Mm-hmm. And there are parts which are kind of specialized in like SX layered, right? I mean, you probably wouldn't want that, in your desktop, right? So there are all those. So right now, I'm not sure that, we have a direct plan of contributing, writing the code back into the kernel scheduler. But I think like more of the contributions are going to be around the ideas and the things that we find out, and what works and what doesn't work.
You're one of the runners. Okay, so just throwing this out there, how much work is being done on trying to automate which one provides the best performance, and to be able to, I guess, learn from the loads that are being presented on that particular machine, and then be able to automatically pick the one that seems to be right for it?
Right now, not much. So I mean, again, we're still fairly early. So like the closest work that I know of automating like scheduler tuning is done by Google, and I only know that by just by second or third hand. So there were like effort to kind of auto tune the scheduler parameters. Watching performance metrics. So something like that is definitely something we can try down the line. But right now it's just, still all kind of manual. You try this, you try that, and try to learn in the process. But down the line, maybe, we can make it more formulaic maybe, but we are not there yet. Oh, Jeremy in the back.
Troy, thank you.
Just about the lessons learned and talk about noisy and talk about different schedulers as well. Is there much of an effort in isolating? What is the better way of doing it? Isolating cores and tasks and then controlling them separately, or is it happy to work along with the main scheduler all the time?
Can you repeat
So you have the default scheduler and then you have certain priorities, or is it latency, is it performance metric for some of the threads? Would you want to isolate those threads and isolate a set of cores that you want to schedule them on, or the main scheduler interfere much?
Right now, so maybe this will, we will find like different cases, but then it's up until now, all the schedulers that we use in practical deployments take over the whole machine. So it just schedules all the threads in the system, right? So we don't usually, that's called a partial mode in SCADXC terms. None of the schedulers really run in partial modes right now. They all assume that they take over the whole machine. And in practice, there were some concerns because what about case threads? Shouldn't we treat them differently, right? I mean, this and that. And eventually, it just turned out that it's not all that different or all that difficult to do. So yeah, all the schedulers that we are using now will just take over the whole machine.
Okay.
So Tejan, in terms of observability, are the existing scheduler trace events sufficient, or for some of these custom scheduling algorithms you need something more? And if so, what's the interface? What's the way forward for that?
Yeah, observability is always really important. It's it kind of goes two ways, because you get really used to BPF, right? I mean, you want to tracing is BPF is heavily used in tracing. So you can approach it that way. But another way is that because now you have a scheduler that you can eject and load in seconds, right? So you can just add printfs, right? What's happening here? Just printf, right? What's happening there? Printf, right? So it just becomes really ad hoc at the same time. So I don't think it's going to stay that way, but I mean it's going to always be. It's always nice to have that ad hoc way of getting visibility. But also there are we're kind of seriously talking about efforts into kind of creating more visibility into in a more structured way. So for example, I think Daniel wrote this BPF script which measures latencies in each DSQs. So things like that. So I think down the line, we are planning to add a lot more observability and visibility tools in the SX repo, so that which can be used across schedulers, hopefully.
Okay, thank you. Joel.
That's a long throw. Oh, yay.
So I was just trying to understand the dispatching part a little more. So what happens if the BPF program doesn't implement dispatch? Like, does the core do a round robin of runnable tasks, or?
My memory is a little bit. So at the beginning, I wanted to make it as easy as possible. So if you don't want to implement anything, there will be just default implementation. So default there's a fallback implementation where it just do FIFO, really dumb global FIFO scheduling. But I think we actually now require dispatch to be implemented. So there are some operations you can omit, but the core operations you have to implement.
Okay, and the other question I had was when dispatch happens, you tell the core run this task for either infinite amount of time or certain amount of time. So what happens if the task is runnable after that small slice?
Right.
Does a dispatch have to happen after that time again so that it can run again?
So whenever you dispatch a task, you can set slice, and then when the slice expires, your scheduling path is called again, and then your dispatch can decide to keep running it or run something else, right? So it's just that when the slice expires, you can make that decision again, or whatever decision you want to make. Another part is that you don't have to set slice, so you can run it indefinitely. Then schedule a separate timer to trigger events. So there's one I did. There's called the SX Central, which is not really a practical scheduler, but where all the scheduling decision is made on one CPU. And all other CPUs are just running. And then whenever the central CPU makes a decision, it sends an IPI, right? There's an interface to send IPI. It's called SX PPF kick CPU. And then it enters into scheduling path.
Okay. Yeah. So just to be clear, like so if you give it a slice and the slice finishes, the core removes the task from the local queues, and then a dispatch has to happen again to put it back, right?
The details is a little different. It's just that it stays on the core and it still asks dispatch. And then if dispatch decides not to dispatch another task, then the current task keeps running. So it's a little bit, semantically just a little bit different, but basically that's what's happening.
Okay.
Yeah.
Thanks.
General question about how you, I guess, and the team thinks of maintaining these in the future. So as far as I understand, 612 should see the core bits merged, and then the actual schedulers are maintained somewhere else, like in different
repos. That's the
right.
SCX repo. Yeah.
Yes. So I guess the question is, how's the idea of about maintaining those schedulers, and do you think this is a good representation already that is general enough to be able to service kind of different kind of workloads, or do you envision more schedulers to be added? And in that case, how does it work? So anybody, I guess, is welcome to propose. And yeah, I don't know if you can comment on plans around maintaining this thing.
Okay, maintaining. So one part which makes things relatively easy is that BPF has a lot of features which allows you to make compatibility fairly easy. So you don't have to like decompile or anything. So a lot of linking actions happen at the load time. So even as the kernel adds more features and changes the interface, it's not that difficult to maintain backward compatibility with older binaries of the scheduler, right? So that makes things a lot less painful. And another part, the second part of the question is that we have schedulers, right, which are really good, pretty good at what they specialize in, but they're not versatile enough, right, to just kind of blindly recommend to people, right? So if you're on like Steam Deck, or if you're on a gaming PC, and if you're focused on gaming, or it's your personal PC, like certain like specific use case scenarios, right? It will work, right? And if you have like certain server scenarios, right, with layered, you can probably get gain relatively easily, right? But at the same time, if somebody says, hey, I have my machine, I don't know what's happening really here, but I want to try it, right? Then we don't really know, because all the schedules we have don't really cover the entire spectrum of the problem space, right? So that's why I mentioned in the long-term plans, there's like composability, right? So that's what's kind of really lacking, right? So we have like this problem space is different parts of problem space is covered by different schedulers right now, and in that way they are not generic, right? So as soon as you kind of cross over to the different layers of problem, it's not going to work that well. So once composability is there, I think we probably can say yes to, we have a general scheduler that most people should be happy with. Right now we don't have that yet.
So in the Android world, there's a lot of cases where vendors are already kind of...
Can you bring the mic?
Sorry. Yeah. In the Android world, there's a lot of cases where the vendors are already kind of tweaking the scheduler, but they're doing a lot of things tying into like locking. And so I was curious, as far as in the SCEDX core, are you also expecting to kind of have ties to other subsystems than just kind of the core scheduling?
Tied to other systems in terms of locking?
Yeah, so like things like choosing the lock handoff order, that sort of thing, getting pulled into the scheduler decisions as well that they're doing. So that's sort of like, there's a lot of, I guess, the tweaks that the vendors tend to kind of spread across a lot of subsystems. And so I was trying to see how this might be usable for that.
Can you repeat the last part? I'm sorry, I'm not.
So basically just trying to figure out how can SCEDX schedulers also influence like lock handoff and the orders that other subsystems manage things that influence the scheduling.
Okay, yeah, I think I can answer in two parts. Like one part is that there are a lot of lacking complexities, just making things work. So those are all hidden by SCADXE core, right? So from the scheduler side, the BPF scheduler side, it's not that difficult, right? So most of complications are hidden from the schedulers. And the other part where, there can be a lot of different problems, right? Like how to handle like priority inversion, like can you do like priority inheritance in some easier or smarter way? We actually just hit a similar problem like a couple of weeks ago in production, and I think there are just because BPF gives us a lot of ways to gain a lot of visibility into what's happening on the system in a fairly dynamic way and in an ad hoc way. And because a BPF scheduler, when implemented, you can just you can always integrate with any other BPF programs, right? So if you wanna like hook it up with a BPF programs which is watching locking state of the system, right? How many system locks is holding or whatever, right? That means the slip over state and all that. Then you can pipe that into the scheduling decisions easily. So we haven't done that yet, but I think that might come into the picture because we actually see problems caused by those in production. Yeah. So, but we haven't tried that yet.
Thank you.
Yeah, it's fine.
Hi, I was wondering, you are using the BPF, which, if I remember correctly, uses vmalloc as a backend. So does that mean that you might have exposure to TLB trashing in case there is something which is doing a lot of...
Yeah, maybe. I'm not really sure. So the thing is that, I mean, like the code, and I don't know. We haven't seen anything like indicating that that is a problem. Like the TLB pressure is a problem. We haven't seen anything which points that way. At the same time, one thing which I kind of don't know, right? So like during the early experimentation, right? When I started the working on the project, like the overhead, like the processing overhead, like the branches, the jumps, and all these things, I was kind of obsessing about how much that would cost and all that. I mean, it still matters, but like the experience in production workload, like comparing them, indicates that like these small overheads tend to be small, really small, compared to the gains or losses you can make by good or bad scheduling decisions, right? So you just just being able to make better decisions, even at a little bit higher overhead, the gain seems to like dwarf any overhead by going to BPF, going to vmalloc or TLB pressure and all that. It's just it is. I think it almost feels like it's multiple orders of magnitude difference in what you get. So right now we are not really seeing that is a problematic part.
Okay, thank you.
Yep. I think we're done. Thank you very much for coming.
Okay, we are plenty over time. I'll try to be fast.
I don't think we ever met in person on URL.
Okay, so yeah, as Tejan mentioned, we have different schedulers implemented in different ways. Some of them are like pure BPF schedulers. Others are hybrid schedulers, meaning that they have the BPF part and a user space part. And other schedulers are fully user space. Well, just a couple of them right now. And so in this presentation, if I can figure out how to change the slides, okay. So basically, I started, at some point I decided to implement a scheduler using Rust in user space and use BPF to channel, to basically intercept the SCADX event and channel all of them to user space. We were very skeptical at the beginning, even with Tejun. We were like, this is just a fun project, it's going to be a toy. Probably still is, but it's the thing is like the potential was interesting because like once you're in user space, you have the flexibility to use, you know, any kind of user space libraries, and also in terms of observability, you see the scheduler as like a regular user space process. In Linux, you can either even top and see how much CPU the scheduler itself is using. So yeah, I decided to keep going and continue to work on this project. And at some point, I was like, well, let's generalize this and extract the back end of this scheduler and make it generic so that other people can easily use that to build other user space schedulers on top. So that's why I created this SCX Rustland core. It's a Rust crate or Rust library, if you want to see like that, that implements the abstraction layer over SCADX. It's basically an interface between the SCADX and the user space. And so with SCX Rustland core, it's a crate. You can import the crate in your project. You can create a standalone Rust project like any Rust project, you know, cargo init and whatnot, cargo build and run. It's a GPL v2, so your schedulers need to be GPL v2 as well if you use this. Yeah, as I mentioned, like the main goals for this project are the better user space integration. I say libraries, but also services, because once you're in user space, potentially you can communicate with other things easily. Tejun mentioned the fast edit, compile, test iteration as a benefit of SCADX in general. If you're in user space, even more, like you can literally, well, even the BPF schedulers, you can / and Control-C to change the scheduler, do modifications and whatnot. But user space even more. Yeah, so here's the architecture. Basically, there is, can you see the point? Yeah, maybe. So let me go here. So there's the kernel part, that's the SCADX, the in-kernel patch. Usually what you do, you implement your scheduler here in BPF, implementing the callbacks. Oh, I need to use the... You're right, good point. So that's the kernel part, I hope you can see. This is the BPF part. I mean, I can be more descriptive. On the left, you can see the kernel part. On the center, you will see the BPF part. When you implement a scheduler in BPF, usually you implement the callbacks in BPF, like in queue dispatch and whatnot, and everything sits here in the BPF space. Or you can have something in the right side that uses the user space part, like SCX Rusty, for example, that implements the load balancer in user space. But most of the decisions are done and implemented in the central part with the callbacks. With Rustland, what happens instead is that this layer for the SCX callbacks is really small. It just implements a kind of message passing interface to user space, whereas any task that wants to run, it just bounds to the user space part. User space takes all the decision, like 100% of the decisions, and sends everything back to BPF. So it's Rust, but it's not Rust for Linux. I'm cheating. I'm bringing Rust into the kernel, but from user space, actually. Moreover, I'm not generating BPF code from Rust. I'm generating binary code in user space, and there's still a C component implemented in here that is like the connection between the two words. That's how it works. I'm not going through the details of the workflow, but you can already describe everything. The only thing that I want to mention is that at some point we switched to use the BPF map type ring buff and user ring buff. When we switched to that, we got a massive boost in performance. Because before we were using maps, queues that are using syscalls. So every time that a task was moved, bounced between user space and kernel, there was a syscall. Now everything is just copy. I mean, you share, from user space, you share the address space with BPF. So you just copy stuff into the ring buffers and it's really fast. And another thing that I want to mention is, so when I say like scheduler in user space, one of the concerns is like, yeah, but overhead is going to be a lot if you move to user space. It's not actually the case for many reasons. One of them is the scheduler is not a CPU-intensive task on its own, because usually the scheduler doesn't do anything except for short bursts. When you need to take a scheduling decision, and then it's most of the time is the user space process or the kernel process that are just going. That's why, like, if your scheduler is using too much CPU, then there's a problem in the scheduler. I mean, you have a design problem, probably. And the other reason is that you need to be fast at reacting when the scheduler needs to take a decision. And if you can achieve that, you don't have much overhead for doing that. So in this my session, I wanted to focus on the API, and I'm happy to accept suggestions or if you have any comments to do. The goal was to make the API as easy as possible so that literally everyone can just use the Rust crate, implement, and use like, this is really simple, right? You have a BPF scheduler, you declare a BPF scheduler object, and you have the queue task that gives you a task that wants to run. You can call select CPU that will use a built-in policy to select an idle CPU, and dispatch task. When you're like, okay, I'm done my scheduling, just send this over, and the kernel will actually run the task on the target CPU selected for the amount of time. And there's a notification to say, okay, I've done all my scheduling, just BPF, just do your work and dispatch everything. Okay, yeah, the data types we can. So, okay, it's not all rainbows and unicorns. There are caveats to that. In particular, like if your scheduler is in user space, the scheduler can't be blocked. If it's blocked, everything stalls, of course. And in particular, page faults. Like if you're, let's say, your user space scheduler triggers a page fault. In order to resolve the page fault, you need to run a K-thread. But if the K-thread can't run because the scheduler is blocked on the page fault, you have deadlock. So we solved this by creating a memory arena that is M-locked and pre-allocated, so that and it's all done transparently in Rust. So this part is mostly addressed. There are some corner cases, like one of them is the K-compact D. So even if you M-lock memory, that's something I didn't know. Like even if you M-lock some memory, K-compact D can still map something to do compaction, and that's bad for the user space scheduler because it can trigger page faults. Another thing, so multi-threading was tricky, but it's currently solved. So you can have multiple threads running in your user space schedulers. There's, again, overhead is one of the issues, but the overhead is not about the communication. It's more about the user space not having all the visibility that you have in the kernel. In particular, and like the SCADX, the other SCADX people knows this very well, is the visibility of CPU masks. if we can figure out a way to share the CPU masks, like the idle mask, idle SMT masks and whatnot in user space, and if we have a way to create CPU masks, I think we can really achieve performance identical to pure BPF schedulers. Because like even right now with the latest few changes that I pushed, like the FIFO scheduler in BPF achieves exactly the same performance of the FIFO scheduler in user space. That's impressive considering that we started with like, oh, that's going to be a toy, that's it. So the kernel visibility is really what we should focus on if we want to improve this project. Potentially, like my idea is, except for standardizing the user space APIs, because of course it's important, but I want to introduce reuse the concept of scheduling domains, probably from Rusty could be a good idea, but have a way so that to create CPU masks from user space. And for those that are familiar with BPF, it would be nice to use like the test run in the BPF functionality so that you can call BPF functions from user space. And in this way, like you can create a domain as a CPU mask, maybe assign an ID, and then when you call this guy here, select CPU, you can say instead of using select CPU system-wide, maybe you can attach, like you can ask a CPU in a certain domain. That should give more control on what you can do from user space. And once we have that, I think, in terms of performance, we can achieve really good performance, even if we are in user space. Yeah, let's see, what time is it? I would like to, I don't know how much I spent, but I would like to have time for questions, if there's any question. Especially if you have suggestions on the API that you would like to see for this stuff. There.
Is there some measurement of the overhead that you mentioned?
I have some slides, not in this presentation, in another one that will be on Friday. But the overhead is like, I need to redo all the measurements because I just pushed a change like on Monday that improves things a lot. The last measurements that I've done, running the selection of benchmarks from the 4Onyx benchmarks, I picked the benchmarks that the Cache OS is usually running. They're mostly so that they're not interactive benchmarks, they're more server workload benchmarks. And I tried like to run Rustland with those benchmarks and EVDF, same benchmarks. Like the difference was like 3-5%. Rustland was lower 3-5%. And it's kind of surprising because Rustland is designed to be like to prioritize a lot interactive workloads. So I was expecting if I run server workloads that are not like, I mean, you don't get many benefits if you over prioritize interaction. But still, I mean, I was pretty close to EVDF. But that was a good test because I could, like, the scheduler was not stressed too much, so I could really measure the overhead, like the pure overhead of the layer. So I would say around 5%. It's still a lot, but not too bad, and it should be improved. Yeah.
Thank you.
So yeah, about the mlock issue, I was wondering, like, can that be fixed by maybe moving the scheduling logic for the K threads to BPF and just having the rest in user space, so that way it won't, you can take page faults?
Yes, that's a valid point. That was the first fix that I did. I decided, okay, let's just ignore the K threads, just dispatch them from BPF directly, and send everything else to user space. It's possible. At some point, there was even a flag, like a global flag, that was called local K-threads that you could set to like enable this mode. The problem is you may have big K-threads that are doing a lot of CPUs. Let's say you have an encrypted file system and you're doing a ton of writes, and you may have a K-thread that is monopolizing the CPU, so you also may want to control that. So yeah, this option doesn't exist anymore. I decided to remove that option to dispatch K-threads from BPF. What I'm doing, though, I'm still dispatching per CPU K-threads from BPF, but that's because of the RCU, the per CPU, RCU/N K-threads. And because if you block them, it's tricky. You may still have deadlocks. So those are the only K-threads that are dispatched directly from BPF now.
Yeah, I guess you could. The first fix could be an option as well. Even though you removed it, maybe some people might prefer that and then not have to do the mlock.
Yeah, that's good. It's a good. Yeah, that's the question that I wanted to. API. What kind of API would you guys like to see? Yeah. Thanks.
Hi. So you mentioned that it would be nice to have a CPU mask where instead of assigning specific CPU, you ask it to be assigned some CPU in the mask. And it seems quite similar to what the device driver are doing for interrupt, because they could also ask the interrupt for the device to be assigned to the same NUMA node, I guess. So I suppose we could kind of reuse, I'm not sure, but reuse the interrupt API and maybe have a kfunc in the kernel or something like that?
Yeah, that's a good point. I'm not familiar with how the CPU drivers are using the CPU mask for that, but so one of the things that I want to provide is a way that the user space can create the CPU masks. Then how they are implemented, it's irrelevant, because in the backend I can do whatever I want. And so in terms of API, I think using the function call from user space to BPF is a good way, because I can say, create a CPU mask with these CPUs set. Instead of passing the whole CPU mask, I can have a function call where I can say, enable this CPU in this domain. And that would reflect the change into a backend CPU mask that is allocated, for example, when a domain is created or stuff like that. And then on the back end, it will be like a CPU mask. And I can use select CPU in the CPU mask domain or stuff like that.
So just making sure I got it right. So you're saying that passing the whole CPU mask is kind of high overhead?
No, it's not like an overhead. It's how do you give visibility for the CPU mask to user space? That's the problem. Because if it's small, you can just reference the CPU mask from user space, and that's it. But if you have many CPUs, the CPU mask can grow a lot. And so how do you map that? How do you share that with user space? You can have a buffer, but if you copy the CPU mask to a buffer, it becomes racy and not reliable at all. So that's the problem.
Thank you.
Yes, Igor?
About the last question, I was thinking, could you have a dedicated VSDO?
A dedicated what?
VSDO. I never remember if it's VSDO or VDSO, but basically read-only object shared by the kernel to user space.
Uh-huh.
So basically,
you mean with the CPU mask?
Yeah, so basically you can have this
one way. Technically, it's read-write, because I may want to be able to set certain bits from user space as well.
From user space, you can send the signal, say, hey, set that bit. But on the other hand, you can read the whole mask from the kernel.
It's yeah, like so. I'm thinking of CPU masks to mark the idle CPUs. So it's read-write from user space because you can say isolate just these CPUs, but it's read-write also on the backend because once a CPU is allocated, let's say, it becomes non-idle. So
yeah, I was just wondering if you had to use the same method to write them from user space, or if you could.
No, I mean, one thing can happen in the backend when you set the CPU idle or non-idle. And another thing is to say, okay, enable this pool of CPUs. And it can be I mean, it can be the same. Maybe. No, it's different. One is, I mean, ultimately you still set and clear bits in a CPU mask, but it should be a different interface.
I had a more fundamental question. Why do you need to set the mask from user space? Can't you just schedule a sleep task and that's going to automatically take care of it?
Yeah, the idea is to give user space the possibility to say, I want to create a domain with CPU 1 and CPU 3 and another domain with CPU 2 and CPU 4. So instead of saying, when I was showing this, this API, the select CPU, instead of saying select CPU, give me a CPU across all the CPUs available, I want to say, give me a CPU in this domain. That's why I want
Are we still talking about CPU idle masks, or you're just talking about something else now?
Yeah, it's CPU idle mask, but I also want to create, like, I want to put the idle mask in end with a custom CPU mask so that I can restrict the domain of idle CPUs. If it makes sense.
No, but
okay.
okay.
Let's say I have, so you have an idle mask with all the CPUs. I don't want any CPU in the idle mask. I want any CPU in that idle mask put in end with a custom idle mask so that I can say I want an idle CPU in the range 04, for example. That's why I need to create CPU masks from user space.
Okay.
Because I need the end CPU mask.
Okay.
I think I'm missing some details, but I want all the background stuff running outside, I guess, not in user space, always like conflict with anything that you do in user space, unless, I don't know, if you configure like isolated CPUs from the boot, or how do you actually isolate, let's say, your domains that you think you'll need in user space?
Yeah, it's like, it depends what kind of isolation you want. If you want like strict isolation, this is more like create a domain so that you can preferably allocate CPUs on that domain. And if
you don't really care that much if anything else is running there when your user space task is running there.
Yeah,
as well.
right now that's the way that I was envisioning this. Okay. But we can extend to provide like real isolation. Maybe in that case this is not the right way, but yeah. Any other questions? Agat.
Thank you. In your API, why do you return I32s at some points and error at another point? I guess this is could be an enum or something with proper error codes.
Which one, Agat?
The errors in your results are I32.
This one.
On top.
Oh, this one.
Yeah, it's a result, but with I32, I would have expected an error or an enum, maybe, to make things more sensible.
Yeah, I'm trying to remember. So, oh yeah, so that's the I32 is the error that you get from the ring buffer API. So it's a libBPF error. So it shouldn't be an I32. It should be a libBPF
error.
RS error. Yes.
That you could.
Yeah. That's right. Yeah.
Okay.
Good point. Thanks. Okay. No more questions. We are over time a lot. Next one. Thanks. Who's the next one? I forgot. I don't have the schedule here.
Myself.
Who's the next speaker? Which one do you guys have the schedule? Sorry? Doing again. Good, good.
Can you hear me?
Oh, it's Changu, are you next?
Yes, I am.
Okay, let me. You can.
Could you give me a
Did you click on take presenter?
I do not see the presentation button here.
Let me see. Yeah, how do I give the? Is it in the plus button? Yeah, sorry. Is it here on the left? Yes. Yeah, okay, found it.
Yeah, take.
Yeah, so Changu, if you click on the plus button and you select your slides, I should have done that. Okay, you're done. Cool, thanks.
Okay, shall we start? Can you guys hear me well?
Yes.
Okay, so let's get started since we are already behind the schedule. So I'm Chang Min from Igalia, an open source consultancy company. Today I'm going to talk about how SCAD-EXT can be used to improve the gaming experience on the Steam Deck. Particularly, I'm going to share the ideas behind the SCX LAVD scheduler. I go to the next slide. Okay. So this talk is about basically the LAVD scheduler, which stands for Latency Criticality Aware Virtual Deadline Scheduling Algorithm. And basically, the LAVD scheduler is the SCAD-EXT basis scheduler inspired by the gaming workload characteristics. So its main target is the game, especially running on a Steam Deck. And as the LAVD name implies, it actually uses the latency criticality of a task as a main factor to making a scheduling decision. And that latency criticality that we're going to drive from by analyzing the gaming workload characteristics. And also, especially in case of the handheld device, the battery consumption is really important. So LAVD knows the cores, handles the cores differently, so it knows the heterogeneous cores. And also, in order to further optimize the performance and battery consumption, it actually adopts the scheduling policy according to the usage pattern. So before diving into the details of the LAVD scheduling algorithm, let's first describe clear the goals and the non-goals. We want it to be the best gaming, provide the best gaming experience in the Linux platform in general. Not only for the Steam Deck, and more especially we want to provide high gaming performance without having the stuttering. So that basically means that we want to achieve high average FPS, and also we want to maximize low 1% FPS, so frames per second. So we want to achieve high FPS without certain FPS dips. So from the more general server workload terms, we want to maximize throughput while minimizing the tail latency. Even though we are targeting for the gaming workload, we still want to provide reasonably good performance across various workload and hardware combinations. But being the best scheduler for the server workload or being the best general purpose scheduler is not the current goal of a LAVD scheduler. So in order to understand the design decisions that I made for the LAVD, let me briefly discuss about the gaming workload characteristics. We did a pretty good amount of the workload characterization study, how the game works, especially the scheduler's point of view. And I just bring only 2 points, which are, I think, the most relevant and important. The first important factor is that the task runs for a very short period of time. So roughly speaking, once a task is scheduled, it just burns a few cycles, 100, 400, and 200 microseconds on average, and then just sleep, right? So the graph on the right-hand side actually shows that average runtime per schedule across the different tasks, and you can see most of the cases. Move down.
Changu, we lost your voice.
Can you hear me?
We still can't hear you.
Can you hear me?
Yeah, now it's okay.
Okay. So let me repeat this part from the beginning.
No, lost again.
Lost again?
Now it's back. Say something.
Okay.
Okay. Yeah.
Okay.
Keep
so
talking.
The first. Okay. 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 So the first important property is that the average execution time per schedule is very short. It's just 100 or 200 microsecond scale. And the graph on the right-hand side shows the distribution of the runtime per schedule across the tasks. As you can see, most of the tasks actually spend less than a millisecond, and most of them are just spend 100 or 200 microsecond scale. And then just sleep. So, it is really important to understand what these tasks are doing for that short period of time, and then why they actually sleep. So the reason is that in order to finish just one user-level job, such as the updating a frame, given the user input, many tasks are related and cooperate each other. So this graph actually shows that the waker and waiter relationship across the tasks. That basically means that and this is another real task, waker and wake up relationship among the tasks in the real game, the Cyberpunk 2077. And as you can see here, right? So wine server is the center of the in the task graph. And the game engine thread, and game thread, and wine-related thread are tightly communicated with the wine server, which basically means that if there is a scheduling delay happens in the wine server, that actually cascadingly delays the execution of all the related tasks. So scheduling delay in the critical path of a task graph is really critical. So that actually entails the latency spike and the spike of the frame time and cause the low 1% frame per second. So having this in mind, from the LAVD's point of view, scheduling let me describe the key ideas of the LAVD scheduling algorithm. So essentially, from the LAVD's and most of the deadline-based scheduling algorithm point of view, the scheduling is nothing but given the runnable task, we want to decide which task should run first, second, and so on. And then once the order is decided, and how long each task should run. So essentially, from the technical point of view, the LAVD should determine tasks virtual deadline and time slice. And then let me explain how to decide that the virtual deadline of a task, right? So as the name implies that we want to schedule the latency critical task first, then the question is how to define the latency criticality of the task. Right? The key idea from the workload analysis is let's leverage task graph. In this task graph, simplified task graph, task A processing some job, and then wake up task B, and task B get the job from task A, and then processing each job, and then they wake up task C. And task C actually process the result of the task B. So that's the wake up frequency. But on the other hand, from the task C's point of view, task C waits for task B's completion, and task B waits for task A's completion. So wake up, we found that the wake up frequency and wait frequency or the blocking frequency matters a lot in determining the latency criticality. So the implication of wake up and blocking or wait frequency is that if the wake up frequency is high, that basically means that my task frequently wake up the other task, that basically means I'm an important producer in a task graph. On the other hand, if blocking or wait frequency is very high, then that I'm going to frequently wait for the result from the other task. That basically means that I'm an important customer in a task, a consumer in a task graph. If both are high, I'm in the important task in the middle of task graph. So when we actually in the LAVD, when we actually calculate the virtual deadline of a task, the major factor is the wake frequency and wait frequency or the blocking frequency. And that's what we call the pipeline factor. So the pipeline factor is the most important factor in determining the virtual deadline. So of course, both frequencies are high. We actually try to schedule as early as possible. And actually, the wine server and many critical tasks belongs to that category. And besides that, we also consider nice priority and virtual runtime to be somehow fair. So once we actually decide the virtual deadline, we should decide the time slice. The idea of the time slice calculation is somehow similar to the CFS scheduling algorithm. So we have the concept of the target latency. So we wanted to, for example, for 15 millisecond interval, we wanted to schedule each and every single task to run. So that actually helps to ensuring the progress of all tasks without starvation. So basically, time slice is the function of number of tasks. So if the system has more tasks, scheduler will going to assign a short time slice. So every task can make a forward progress. And if system has a less number of tasks, then the scheduler will assign a longer time slice. So each task can enjoy the cache locality. Once the deadline and the time slice are calculated, then that's the core of the LAVD algorithm, right? But for the battery power consumption, the important thing is also the considering the battery power consumption. So in particular, the processor architectures are these days heterogeneous. So for example, in case of Intel, they have performance core and efficiency core. ARM also has a big core and little core concept. The idea is that basically performance or the big core provide high performance at the sake of a little more power consumption. But efficiency core or the little core, it is a little bit slower because due to the simple microarchitectural design, but it actually consumes less power. So from the scheduler's point of view, we have the two important questions. One question is that when we should use the big core or the little cores, right? And another one is that practically speaking, all the CPU architectures are multi-core today. So especially in the lightly loaded system, should we use the older cores all the time? Our answer is no, because the core have some optimal operating frequency range. So for example, in this graph shows that the x-axis is the performance or clock frequency or the CPU utilization roughly, and y-axis is energy consumption. If you go on the right side, so clock frequency becomes higher, right? We get a better performance, and typically the current the frequency governor, its CPU utilization is high, the clock frequency becomes higher, then we can able to get the better performance. So the higher clock frequency actually triggers more power consumption in the core. And if the clock frequency becomes too high, that basically means that core is turbo boosted, so they're going to consume much more power consumption in the core. But on the other hand, on the other side, the clock frequency is too low, right? Then the execution of a job is going to be very long. So it also consumes more power in the on-core side, like outside of the CPU core, like a memory controller and something like that. So because of the tension between these two, we have the green zone, which is the optimal operating frequency. So it is a little bit early to generalize. But in my experiment on the AMD and Intel CPU, about 50% of CPU utilization can easily help us to landing at the optimal operating frequency range. So that actually make me to come up with the idea of the core compaction. So idea is quite simple. So instead of the spread of the all the job to the entire CPU cores, right? Let's just use the minimum number of cores and run those cores in the optimal frequency range. For example, instead of run 16, utilize 16 cores in 5% CPU utilization, let's just use only 2 cores and in the 40% CPU utilization. That actually boosts the performance due to the higher clock frequency and also reduces the power consumption. So that's basically how we handle the power consumption. And another question regarding the processor heterogeneity, we need to answer is that when to use big cores and when to use the small core and little cores, right? But what I found is that there is no single correct answer. For example, if your system is lightly loaded, let's say 10% of the CPU utilization, and you are doing code editing using the Vim and reading the PDF documentation while listening the music streaming service, right? So most of the laptops today, actually these tests can be easily supported by 1 or 2 CPUs, right? So in these cases, just using the little cores or SMT hypertwins can solve such cores. So choosing those cores is going to be better because that we can actually consume less amount of energy while satisfying the user, right? But on the other hand, if the load is very high, which means that if, for example, running a AAA game on your laptop or the full compilation, then achieving the high performance should be the primary goal of scheduling. But in the medium low, like let's say 70%, right? Just running a casual game or just compile the module compilation, compiling couple files, then it is really important to balance the performance and power consumption, like using the core compaction feature. So having this in mind, the observation actually triggers make me the idea of the autopilot mode in the LAVD. So basically, autopilot mode dynamically adjusts the core selection policy according to the system-wide CPU utilization. So system is lightly loaded. LAVD is going to run in the power save mode. So actively utilize little cores and SMT cores first up to some certain point. And then the system is highly loaded, then the LAVD actually performs the core selection policy to fully utilize all the cores and to raise to the idle state. And in the middle, LAVD is going to run in the balance mode, what we call, and basically allocate the minimum number of cores using the core compaction feature, which serves the load, and classify the workload into the performance critical one and the not performance critical one. So try to utilize as many little cores as possible to save the power, right? So that's basically the autopilot mode. So in summary, the LAVD has the two ideas in terms of to save the battery consumption. One is the core compaction and the other one is the autopilot mode. So that's the core, that covers the core idea of LAVD scheduling algorithm. And let's have some performance comparison with the default eVDF scheduler. I'm not claiming that the LAVD is always better than eVDF, but at least in the gaming scenario, especially in the Steam Deck, we actually see a lot of performance improvement over the eVDF with less saturated. For example, this is one of the race performance in-game benchmark result of the one of the racing games. So as you can see here, right? So LAVD achieved a little bit higher frame per second with a less stutter count, and also the power consumption is a little bit lower. And this is a AAA game, and another one is that the other old game like Tomb Raider. So since the game itself does not consume a lot of CPU cycle, it is easy to achieve 90 frames per second. But the LAVD actually achieves the lower power consumption. So that's the covers the entire array algorithm and the experimental results. I wanted to bring down some of the discussion and the questions during the session or even after the session through the message chat or the office hours. The one is that what other factors should we consider in making scheduling decisions for the latency-critical constructive workload like games, right? We, in case of LPC, so far the wake-up frequency or the blocking or wait frequency is the major factor. But what else we should consider? That's the one thing. And another one is that so far, even though LPC is motivated by the game workload, right? But there is not too much specialization for the Linux graphics stack, Wine, Windows emulation layer, and game engine. So we might need more specialization to achieve the better performance and the lower latency. And we found that the autopilot and core compaction is pretty useful features to the gamers and the laptop users. And what other scheduler features are needed? So that's something that I'd like to discuss. And lastly, I also wanted to discuss the LPC is not heavily tested on the other workload other than the game workload, but the design seems to be might be good for the other server workloads. So do we? Is it? It might be worth. It might or might not be worth to try for the broader workload set, the beyond the game workload. That's all I have, and I'm happy to take any questions.
Just one comment, be really fast with questions because we are plenty over time. So I was thinking to do the break now, but I don't know. Joel, you got just a couple of questions. I think Joel raised the hand first, and someone back there, maybe, yeah, you just fight for the question.
So my question is, it's kind of related to your second bullet. So in CFS, I'm not sure what I think with EVDF2, the nice value, the weight of the task reduces the latency of the task as well. Like it has to wait for shorter time on the run queue and so forth. So is there any way you could use that information from the gaming stack as well, other than just the wait frequency, to decide the latency criticality? And then, so that way you have some hints from user space about what's latency critical as well, and you don't have to just keep, measuring. You could measure, but also use that information together.
That's a really insightful question and good question. So currently, we just only consider the wait and blocking or the wait frequency. So currently, no. But I actually plan to explore further. For example, in games that the frame needs to be displayed in 60 or 90 frames per second rate. So which basically means that all the tasks which are related to the graphics pipeline need to execute for some certain periodics, right? So that kind of information can be encoded and somehow delivered to the scheduler so we can make a better deadline management. So currently, should I say currently no, but I'm actually considering and improving the plan to improve LAVD to that effect. Thank you for the good question.
Okay.
Does it answer your question?
Yeah. Sounds good. But basically, the deadlines, but also the weights, whatever you get from the user space, you can use it as well. Yeah. Any other question?
Yeah. One more, and then the break. If I understand correctly, you have core compaction and you have latency sensitive workload, right? How do they work with each other? For example, when you have core compaction, you have probably some tasks which are already running and you are still stacking on top of it. Isn't your latency going to get hurt there?
That's a very good question, and that's exactly what I worried when slightly skeptical when I actually start implementing the core compression. But in result, I found that we actually ran a lot of the benchmarking with core compression and without core compression. But the result is that the with and without core compression, the latency result and latency distribution is almost identical. So it does not affect heavily, but the main reason is that we basically wanted to keep the core utilization below 50% utilization. That basically means that the very likely the core is going to be idle in the half percent of the chance, right? So I think that's the reason that the core compression does not hurt the latency too much.
Maybe it's because of it's SMT2, so maybe the numbers kind of makes it for the best case, right? Yeah, that's.
Thank you very much, Chang-Woo. Thank you for the good questions. And now I think it's time for the break. Bye, Chang-Woo.
the user space dependencies like make the records they are somewhere and constrain us to CPU mask and you can write to it and that so that creates a domain and CPU the idle mask is maintained by kernel we don't and what I imagine maybe there's like so in the directory there's one that we set and there's one that we read and the one that we read returns the end between the item and on the detail side we just get
People will be like, wait, they go that way. I'm like, no, I mean, don't use that. Use this one. Right.
People will still get wrong.
Yes.
Change the paradigm.
So, I'm going to be forgiving of you. This is your first microconference.
It's going pretty well.
No.
Yeah.
So one thing, it was up to you to control, saying you have a few more minutes. It's up to you to stop it. It's up to you to tell them, okay. And also, yes, and you also should be more proactive in explaining. It's not about a presentation. There was no discussion. That's actually why Right. So actually, no, I learned, because I'm learning too. I'm learning, basically I'm learning how to instruct people. The thing is, what started is this slide. Here should have been first. That should be the first slide. And then you can say, here's what I want to discuss. And then have slides that, the slides should be focused towards the questions. And say, this is my questions, and this is the background behind it. And then let's have a discussion. So that's what it hit me. Like, you don't go through a whole presentation, and people are just like, okay, whatever. Because they don't know what you're, like, then you say, let's discuss this. And people don't know.
I mean, it's okay to give a context, but it should be
Right. And I'm being okay for, because this is the first scale. It's you're learning, not just learning, it's the fact that it's everything's new, so it's new to everyone. Everyone's coming up to speed. But the next time, like if we have another one, it's going to be, I need you to have more, like, okay guys, come up with like discussion topics. And actually I might tell people, your first slide should be your questions. Your Q&A or whatever should be your first slide.
I think that's a good point, so that people understand. Because if you say, we need to bring questions, like, okay, fine, I'll do my presentation and then questions.
Yes.
No, it's like, you need to bring question, period.
Right, your question, actually, that's, I'm learning. So now that's another way of saying it. Telling people to have your questions as your first slide, and all the other slides are feeding that first slide.
I think it came up lately. Like I went to the speaker session, and that's when I first heard that microconference are supposed to be discussion. I guess it would be nice if in the submission
so we've been might be the first. The problem is, how do we tell everyone? I have a blog post that I posted back 4 months ago that says this is the ideal microconference topic. I told everyone before the microconference were even accepted, I had that first. And I told the microconference topics, or the submitters, the ones that were like the microconference things,
I
they say,
think it's fine to delegate these to the leaders.
Yes,
That's the
yes,
goal.
yes,
That's the task of the leader. We need to define a better protocol to be more clear. Like, show the first slide.
Yes.
That's the problem.
Yeah.
That works. But if you say, like, box of questions, people are like, okay, have a Q&A session. I think that's what they understand.
So I'm where I'm going. So it's
we are learning even more for the first time.
But like I said, that's why I'm sitting there like, okay, I'll be okay with you guys.
You've got a totally new community.
That's why nobody really knows what's going on elsewhere.
A lot of people have a lot of people are coming from non-kernel background, so they know what this is.
That's why I'm not yelling.
You should.
No. Because I'm sitting there, like, at first I was like, oh,
It is getting everyone up to speed. This is because it's such a new thing.
Yes,
it's like it's just a bunch of
estimate
it's
for
like
the future.
it's no. Actually, I'm saying this is let everything here, and then maybe next year you say here, watch these slides before coming, and then we can have better discussions.
Yeah, maybe we should have like minor conference leads. We should have another submission session where you correct the slides.
And one thing I did actually, Android sometimes does this, and I want to kind of put this is, the first half could just be presentations. And the second half is, okay, we're going to discuss, the presentations are basically, here's what you need to know to have your discussions.
That's why I wanted the occasional session to go over, because he was presenting the topic.
Right. Well, I didn't realize that you could actually modify the schedule.
Yeah,
You could have made it, yes, I should have made that.
I wanted to be fair, like assign 20 minutes every
Well, remember I mentioned that. I said it's okay to have some topics longer than others.
Yeah, you said that.
So that was a perfect point. That would you could have 2 sessions and get a little short.
Do you have any way to message them, or do you see their name?
I thought they were in the... Oh, yes, Barrett, right here.
Hey, what's up, Josh?
Oh, cool. We can hear you.
That's great.
Sorry?
You said there was a second remote person?
No, just the one, just Barrett.
Okay. Ah, Barrett is remote. Okay.
Yes.
So it's you and Barrett. Yes. Great.
Are you leading the...
Helping Giovanni Gerdovic, by the way.
Josh, nice to meet you.
Nice to meet you. But those are not the slides.
Right.
File name of...
Pluggable scheduling in Google here.
There's a reason why I put design on the back, on the other side.
Yes.
So next slide is here. It's very simple.
Oh, cool. Yeah.
Like that.
Got it, got it. And then you can just tell me when I should get started.
Right. If you point at the slides, maybe use the touchpad so that also in the recording the cursor will show.
Yeah.
Instead of going there and say, hey, you see this? Because that's not recorded. This is, right?
Yeah. Do you want me to hard stop at 20 minutes or?
Nice.
I mean, I don't know whether, based on the way things have been going, I don't know if there's
the
more.
thing is, because we forgot to bring those panels that says 10 minutes left, 5 minutes left. We don't have them. And but maybe I can do it with a piece of paper myself and can tell you when it's 5 minutes left.
Yeah, I timed it for like 18 and then like a couple questions. Hi, Josh, nice to meet you. Yeah, nice to meet you.
Question, do we have that? Sorry, go.
That just one hint, suggestion. Try to be brief on the presentation and give more time to questions.
Yeah, we timed it that way. We timed it for like 18 minutes or so.
Yeah, that's perfect. It's like I'm also learning. Like it's the first year that we do this conference, and like someone is doing more. Yeah. We don't have the sign 10 minutes left, 5 minutes left. No. I'm making with a piece of paper myself.
Yeah, if you can.
Maybe I can stay in first row. Yeah, sure.
Move my stuff if you need. This is free or not? Yeah, it's free. On, hello. Okay, we are starting because we are, the schedule is kind of messed up, but we'll try to stay on track. Josh?
Thanks. Hello, my name is Josh from Google. I'm joined by my colleague Barrett. Barry, want to do a sound check?
Hello.
Perfect, we can hear you. So I'll try to keep this end around 17, 18 minutes so we can hopefully do a couple questions. But the main thing we're going to be talking about today is the application of pluggable scheduling with respect to Google Search. So Barrett's going to spend time talking about how we implemented a bespoke policy to help improve performance there. And then I'm also going to talk a little bit about how we've been using pluggable scheduling to improve general purpose scheduling, because it's not realistic that we're going to write a custom policy for every user. So before we get there, I just want to super briefly talk about our motivation, because we've been working on this for a couple of years now. With respect to pluggable scheduling, we had three main goals. The first was we wanted to solve the rollout speed challenge, right? If you want to update policy in the kernel, doing a rollout is really slow. Putting all the updates in user space and BPF, you can push the updates order of magnitude faster. Like probably around months for a kernel update becomes days or weeks for user space rollouts. Additionally, within the kernel, we're kind of constrained with how the scheduler is designed, in that, like, for example, the scheduler is built around the idea of per CPU run queues. It's a very natural thing. It kind of started out from unit processor, and then it just gets expanded to multiprocessor, but that has certain trade-offs that we want to move away from. Barrett will talk a little bit about how we used per CCX run queues to help improve search. And this is also a follow-up from, Taejin kind of teed us up earlier about soft partitioning and thinking about how do we do more CCX-centric scheduling. And then finally, anybody who's programmed in the scheduler knows we only have, a small number of scheduling classes, mostly just CFS, and so any changes you make have to pretty much go into one of those few classes and be generic enough to apply to any scheduler. But with a user space or BPF scheduler, we can make any changes we want. We can make any kind of bespoke policy. And then super briefly, we started working on this in 2019 under a project named Ghost, which you may have heard of. We made that open source and published some papers. SCEDIXT then came along, and we've been collaborating with Meta on that. The difference is mostly that SCEDIXT is kind of a BPF first approach into how the hooks are designed, whereas we were kind of a user space first, but then BPF acceleration. And so we're currently working on migrating some of our Ghost APIs to be built on top of SCEDIXT, especially now that it appears that SCEDIXT will go in the next merge window. So with that, let me hand it off to Barrett to talk about search.
Hey everybody, I'm Barrett. Next slide, please. Some of you may recall this picture. This is from LPC a couple years ago, but this is the overall picture of how BPF works with Ghost. So on the far left there, you see a bit I call kernel space. We have kernel and Ghost scheduling class, which is roughly equivalent to SCED-XT. Everything in red, I consider the schedule, the agents. There's a BPF part of it in the middle that makes the actual scheduling decisions. And it has a couple little hooks into the kernel. Those are the BPF message and BPF picnic task. Those are similar to some of the SCED-X stops. But basically, the kernel tells us about events, and then we tell the kernel what we want to run. But the bulk of the actual logic happens in BPF. That's where I think of it as the loop of a scheduler. And then we communicate with user space via BPF maps. And we have a giant BPF map for every thread struct, things like that. And in our user space agents, we originally had user space doing a lot, like telling the kernel exactly what to run when and where. We've kind of moved to a model of having user space be responsible for like parameter tweaking and monitoring, adjusting things, but not under the path. And then importantly, we have this green box, which is the application itself. And the application can talk to user space. And we actually give the application a file descriptor for the BPF map so that they can talk directly to our BPF agent. Next slide, please. Let me talk about search a little bit. Search is just a gigantic application, but from a very high level. We have numerous groups of threads. We have like query threads. These handle like RPCs of various types. And they'll range in duration from maybe only hundreds of microseconds up to tens of milliseconds, or even hundreds of milliseconds for some queries. There's also another class of threads call them pollers. They're very important, but they're also very noisy. They typically run like an order of tens of microseconds at a time. They'll wake up, move data from one queue to another, and go back to sleep. And they're important, but they, as you can see with the 10 microsecond run times, they can be very disruptive to other workloads. Similarly, there's also just a whole bunch of other things like housekeeping threads. Don't really want to go into it. Overall, the application is sensitive to cache locality and CCX placement. And of course, latency matters for all these things, especially for the queries. And finally, we run on multi-socket NUMA machines. Next slide, please. One of the policies we wanted to look into was some form of CPU soft partitioning. So looking at the overall problem, we have lots of CPUs and several thread groups. The very first thing that pops in your head is how about we spatially partition the machine among these groups? One of the benefits from this is cache locality. So for instance, my RPCs can all be run on one cache and the pollers can be on another one. But the other aspect is that those pollers were very noisy. So this way, if I put them on their own little partition, let's basically minimize their interference on the rest of the machine. One of the things we didn't want to do was use CPU asks. The affinity is kind of too stiff. Like, for instance, I don't want to say, yes, you have this exact set of CPUs. I just want to give it a little guidance. So what I would do is say, hey, how about I assign CPUs to a group? And if that group of threads wants it, you'll get it. You'll have dibs on it. But if you don't want the CPU at the time, somebody else can use it. So this was kind of a little policy that we had put together. We said, oh, this is a great opportunity to have user space come along and periodically adjust the sizes of those groups. So the group assignments we'll basically change them every like 32 milliseconds or something. But in the meantime, even though user space changes the group assignments, from BPF, that's more just a hint of where threads should be run. And if you want to run outside your assigned CPUs, well, that's fine. That's just something, a little decision a BPF will make on the fly. Next slide, please. Another policy thing we wanted was per CCX run queues. And each CPU is assigned to a specific CCX run queue in a many-to-one relationship. This is specifically a run queue structure that every CPU pulls from. So there's a spin lock for it. Everyone's grabbing from it. It's physically like a regular run queue, except it's just every CPU knows to just pull from it. The things we were going for is getting the high L3 cache locality, but there's a trade-off is that we have less CPU and core/SMT locality. We also have because of this policy, a kind of rapid assignment of threads to CPUs. Like for instance, there's no head of line blocking where if you're like you would get on a per CPU run queue. For instance, if you were sitting on a per CPU run queue and it just so happens that that CPU is held up by one thread, normally you would wait for a while. You'd be waiting on a load balancer of some sort. But if we got a per CCX run queue, then or any shared run queue, that will cut down on our scheduling latency. We actually do have optimizations in place to try to keep threads in their previous CPUs, but for the most part, we don't want to wait around for that. Next slide, please. And then finally, we have an application-specific pick next task. And I mentioned earlier that we have different types of threads. So for instance, RPC threads, we actually know what the deadline is from user space. And they actually tell us this through that giant array map. We actually will be using a BPF arena eventually, but for now we're still using a giant array map of for every thread, there's a little struct that the application can fill in. And one of the policies we wanted to explore here too was keeping tasks on the CPU until they complete. We know that they have a specific task and that they will eventually get off the CPU. So we actually don't have any time slicing built in. For the pollers, we have basically a much more simple policy, which is just get on any CPU quickly. We know you're just going to run quickly and block and get them off. We do have some future work in that spot, but yeah, that's future work. Next slide, please. And finally, how do we put all this stuff together? We have this framework called Flux, and I mentioned this last year at LPC. But the general idea is that we want to express the search policy as a hierarchy of schedulers. Remember, we have numerous CPUs and several thread groups. Well, how about each thread group is its own scheduler, and by scheduler I mean like a struct scheduler with code and everything like that. And Flux itself is a framework that I put together that lets you write hierarchical schedulers and for composing these multiple scheduling policies all into the same overall scheduler. And at the top of the hierarchy, you think of having a scheduler of subschedulers. And that's the thing that does soft partitioning of CPUs to groups of threads. And at kind of the leaf in the bottom of the hierarchy is kind of what you think of as a typical thread scheduler, assigning threads to groups. Assigning threads to CPUs. And that's where your group or application-specific policy comes in. Next slide, please. Here's a little picture of what we have. At the very top level, we have this thing I call DIBs. It's just a block of code. It's a subscheduler that assigns CPUs to other subschedulers. Remember, subschedulers are basically groups of threads, or you can even think of them as C groups. And its policy is one of soft partitioning the CPU. And it'll do something like, hey, let me set number of CPUs based on a child's load and attempt to pack you into a CCX. And it'll have two children. They're both subschedulers, one for RPC and one for polar. The polar one has that very basic policy, global FIFO queue, just runs, run whatever task is next on a CPU as it becomes available. The RPC one is a little bit more complex. That's the one that actually is much bigger. It takes up more of the machine. So that one has the per CCX run queues. It too schedules threads onto CPUs, but it uses an EDF policy. Next slide, please. People always like to hear about the results. I always throw out the big caveats on this, that this is a single node benchmark and it's testing data, but compared to CFS with this policy, we have 10% more QPS and lower latencies, both at the P50 and all the way at the P99. And next slide, please. Yeah, but at this point, I'll pass it over to Josh, who'll talk more about general purpose scheduling. Thanks. Hey, not sure if you guys can hear me, but no one can hear you on the stream. Still nothing. Oh, okay, great. Do people in the room hear you?
Yeah, I think so. This is
Oh,
on?
there you go. It's on now.
Okay, I will just use this. Yes, and so once we write such a policy, we're going to have a mixture of user-specific bespoke policies and a general purpose policy. Can we layer these things together on a single machine? And then furthermore, and I think this is an even more important question, can any of the things we learn about be applied back to kernel CFS? So the main thing I want to call out, and our main observation about general purpose scheduling in our experimentation, is we observed that the kernel scheduler really cares about threads rather than groups of threads, right? C groups as an entity is a compile time option, which means that the scheduler has to support everything as a thread in terms of the schedulable unit. And this works somewhat well, but it has some important downsides. There's no real way for the scheduler to try to keep a group of threads constrained within a particular group of cores other than giving a single hard affinity, which is not something you want to do. What you really want to do is schedule a group of threads onto a group of CPUs. Keep the C group as the fundamental abstraction that the scheduler is operating on. If you look at how CFS load balances, for example, it just iterates, a list of threads on the CPU and starts spraying them out to remote CPUs. There's no ability for it to try to keep threads together from a particular application. And there's all kinds of reasons why you'd want to do that. For example, maybe you want to keep your application mostly concentrated on a CCX, but still allow it to spill out to some remote cores if it has to burst. This is chiplet scheduling, and getting the performance here is super important, as you just saw with Barrett's presentation. So I'd say this is our biggest observation in terms of general purpose scheduling in the kernel versus what we've been able to do. There's also a couple other things I've been looking at, namely mixing real-time latency bounds with fair type properties. We also see, with EEVDF, there's movements there in the kernel. And then the last big thing to call out is a lot of the tuning knobs that we see in CFS are kind of treated as debug knobs. I mean, they were literally moved to debug FS. But we applied some ML tuning to try to optimize these for different applications and predict the right values. And we're actually able to extract several additional QPS from the same machine, same hardware, just changing these 3 or 4 different debug FS knobs that the scheduler exposes, which kind of implies that there's actually a lot of headroom to add even more knobs and more heuristics. And so we're adding new ways of tuning the scheduler, and we think that this is something we can apply back to CFS because it's clear that these are not just, set to a power of 5 and then be done with it. These are things we should actually be adding more of and trying to tune better. I think we're almost out of time. I will leave this up, but I won't talk through the whole thing. But this is kind of building off of Barrett's earlier call out of how we can layer policy on a machine. You can have different jobs with different types of policies all exist within a single set of cores. And you have a hierarchy of schedulers that delegates cores up and down. And then at the tail, you have the thing that's actually driving the scheduling policy, whether that be like a FIFO policy or a throughput optimized policy, or whatever it happens to be. So yeah, the main theme is BYOP, bring your own policy. We can have any user at Google write their own custom policy and layer these things together seamlessly into a single framework that we call Flux. And with that, I think there's maybe like a minute or two for questions. Yes?
We will take one question, and also let me remind to the next speakers, to the people who give presentation later, that the 20 minutes also include the question and answering. Okay, it's fine. Thank you for the presentation, Josh. And now Gautam, and then we move to the next speaker. Okay.
So, Josh, thanks for the nice presentation. In terms of what we could carry from your experiments back to the BPF scheduler is a per CC. Can we move the run queues from individual CPUs to a per CCX level? Is that something that we can explore as well? Because it seems like it's working out pretty well in the RPC case that you mentioned. So.
Yeah, you mean in the kernel, right?
Yes.
Yeah, that's tricky because so much is based around the idea of per CPU run queues and per CPU RQ locking and everything. Probably the closest we came to that was with core sched, where we kind of made both SMT siblings somewhat share the same RQ lock and maybe a common grouping of threads. But I don't think it's going to be an easy lift to make, any larger granularity run queue type things. And per CCX is just one example, right? Like we've also experimented with per NUMA run queues. Depending on what you're trying to schedule, if you're trying to schedule, 1 million threads, maybe that's not the right abstraction because there's going to be way too much contention on that single run queue. But if you're scheduling, say, VMs, where you're only scheduling a finite number of vCPUs, maybe the trade-off makes sense to make the granularity larger because there's going to be a lot less pressure on that single run queue source. So that's where it gets down to. It's very application specific what the right trade-off is. Thanks.
Madri's next one. Oh, there is.
Use this or
whichever works. And how do I
Is-
change the slides?
just click left.
Is this working? The remote people can hear me because before it wasn't working. And no one remotely? Okay, then it's working.
As long as you see your name up there.
Hello, hello, hello. Yeah, it works.
So you can use this one.
This one, does this work?
Right, say something.
Can you hear me, people?
Yes.
Thank you. Right, okay. Okay, so hello, I'm Himadri. I'm a final year PhD student in the Whisper group at INRIA Paris. And my research focuses on extracting and utilizing per-hour scheduling information in order to improve the performance of parallel workloads running inside virtual machines. My thesis is supervised by Jean-Pierre Lozzi and Julia Laval. Both of them are present in the room. And I'm going to show some graphs which are generated using the graphing tools that Julia presented at the LPC last year. Okay, so the context of this work is the dual level of task scheduling that is experienced by parallel applications that run inside virtual machines. I have a minimal example here. Suppose we have a parallel application which is trying to run with 2 worker threads. First level of scheduling it is going to encounter is at the guest level, which is going to decide how the threads are going to be placed on the vCPUs. And the next level of scheduling decisions would be made at the host level, where we would decide how these vCPUs are going to be placed on the vCPUs. And just as a side note, on Linux with KVM, KMU kind of hypervisors, our vCPUs are like any other regular task, so no special treatment. They run with the sched normal policy. So as you can see here, we have only one vCPU over subscription is like 2 to 1. So only one of the vCPUs can run. And vCPU 2 is unlucky, which gets stuck into the run queue of on the host. And here I would like to define a term, phantom vCPU. So a phantom vCPU is a vCPU that is stuck in the run queue on the host, which wants to run the application worker in the guest. And so, of course, this is problematic because most of the applications achieve parallelization using some kind of parallel application runtime libraries, and these libraries make decisions based on how many number of CPUs you have available on your machine. And they don't consider the fact that you might be running inside a virtual machine and not all of your vCPUs are actually able to run. Some of your vCPUs could be phantoms. And the impact is that you don't necessarily get optimal performance for your parallel application. And we tried to implement a solution as a policy which adapts the number of worker threads for a parallel application at runtime. And you can see like which kind of metric we use to do this adjustment. The implementation is at the moment based on libgomp, and we build it by modifying the OMP dynamic interface, which lets you change the number of worker threads at runtime. So Here is the experiment setup that I generally use for testing this policy. So we have a standard Linux host, Linux guest scenario. I'm using the 6.11 kernel on the host and 6.6 stable kernel in the guest. We achieve virtualization with like KVM, KMU, libgomp is from GCC 12 release branch. And I have 36 pCPUs, 36 vCPUs, and it's a single socket machine, so NUMA effects are not present. For VM workload, I have selected UA, which I run it with input class B. It's provided by NAS parallel benchmarks, and I selected this because it has unstructured computation patterns. There are primarily 3 big loops, and then OpenMP parallelize it using some 38,000 internal decision-making points. So that many opportunities we have. It's a very fine-grained benchmark to adapt your degree of parallelization. And with OpenMP, you also have opportunity to either use spinning versus blocking for your application. So when you use wait policy active, your worker threads are going to spin after reaching a barrier while waiting for other threads to finish. And when you use wait policy blocking, you are going to, wait policy passive, you are going to use blocking. And of course, there are trade-offs of using spinning versus blocking. Intuitively, using spinning in an ideal world where there are no phantoms, there is no overload on your host, spinning is going to be faster than blocking. So for this particular example, it's like about 80% faster. But as soon as you introduce overload on your host, then the performance drops for spinning. And it drops relatively more in comparison to how much it drops for blocking. And the degradation that happens for spinning performance is in proportion with the increased number of phantoms, which is how many vCPUs are not able to actually run on the host. So what are we trying to do is we want to keep the benefits of using spinning, but at the same time, we don't want any phantoms. So we want to dynamically adapt our degree of parallelization depending on the overload on the host. So again, continuing with that periodic, an example of periodically overloaded host. This is a graph that shows how many of the spinners from noisy neighbor are running. So the idea is that for 1 second, you have noise, for another second, you don't, and then the pattern keeps repeating. And the graph is, the green lines show how many of these noisy neighbor threads are running. Red lines shows how many of them are also stuck in the run queue. And this is done with EEVDFS host. And yeah, I mean, the experiment setup I already described on the previous slide. And what we want to achieve is something like this. So whenever there is overload, we are able to immediately decrease the degree of parallelization, stabilize at that value depending on the degree of overload, and then immediately jump back off to using more threads when possible. So it kind of works. We can get about 50% of performance improvement. And then I wanted to try that, okay, it also works for other kind of scheduling policies. And primarily I wanted to try SCX pair and SCX flat CG because that would be more interesting for virtualization workloads. But I think they need a bit more work for running experiments like this. But SCX Central is also an interesting policy because all your scheduling decisions are offloaded to a central CPU. And I would expect less number of context switches, hence less number of phantoms. And I should expect more or less same amount of performance, performance benefits, if not more, which we do. So that is all good. And the primary question I have for this MC is that I want this policy to be available for people to try with their diverse kind of parallelization workload, to be tested in various kind of machines architectures. And so I would want to make it available for SCADX schedulers. what would be the right way. Like the experiment I showed with SCX Central is done using like the first obvious method. I ported it to a SCADX scheduler, SCADX kernel, and then everything is still implemented in host kernel, guest kernel, and there is not much that I really changed with SCADX. I just launched a SCADX scheduler and run my experiment. So that's one way to do it. I can provide patches for the guest kernel, host kernel, the kernel modules I use for setting up the shared memory, and a patch for libcomp. Another better way would be provide a set of BPF programs and get rid of all the changing of schedulers, changing of host guest kernel part. I'm already working on it, I also plan to provide that implementation. But I thought it would be really interesting to think about what if I can provide like an example SCX scheduler that implements the policy within itself. And so first of all, like maybe I can stop here and we can do a poll or something, like what would be the right thing to do, like most efficient thing to do. Okay, or maybe we can do it in the end. And finally, so thinking more in the direction of implementing the whole thing in SCADX, because hey, if I can do it in BPF, SCADX uses BPF, SCADX is this great thing to write schedulers, but what I'm writing is not really a scheduler. It's like, it's still monitoring, but thinking of like, can we do it within a SCADX scheduler would be interesting. And there I have like a couple of requirements. I mentioned some of this in the last office hours, I think we can continue the discussion during the remaining minutes here, and maybe if we need more time, we can continue it on Slack later. So this scheduler would need a way to extract vCPU IDs associated with the task struct. It would also need a way to set up and access the shared memory. And I think the trickiest part is that it needs to detect precise context switch and SCAD wake-up boundaries with like a proper timestamp, because that's how I collect these events, and then I have a way to process these events at every scheduler tick. So I think we already discussed that with a BPF timer. I can take care of that part. But the detection of precise boundaries, when the vCPU became a phantom, when it became viable again, when a pCPU became idle, I need to gather all this kind of information. Is it feasible to have it as implemented inside, like an example scheduler? So that's where I'm going to stop, and then, I can take.
Yeah, I have a question, but if there's someone that has more questions, I'll go. Now, one thing was, is it working? One thing was, so you have a part that is collecting information, and that could be pure BPF, like you don't need to have that in SCADX, right? And you may also, based on that information, you may want to enforce certain actions, and that is where SCADX could come.
Yes, but the good thing about SCADX is it's very simple to use. Launch just your scheduler, and it would do what you what you need it to do. And having additional BPF component would not make like that seamless.
That you answered my question. Like I was going to say, why don't you just collect everything in kernel and do in kernel? But it's easier to do in BPF because you can iterate faster and stuff like that. Okay, thanks.
Yeah, so we are also doing a project in the same line. So regarding collecting the information, currently what we do is use trace points and use a BPF program to attach to the trace points. Okay. Is that what you're also trying to?
But trace point would be in the kernel. And I mean, even now what I'm doing is more or less in the similar direction, but like to do it from a SCADX operation is something that I'm toying with.
Okay. Yeah, the other idea was having a struct ops and But from within the SCADX, I don't know how to do that, but the struct ops and attaching to KVM was another way which we are trying to do. Okay. So now with SCADX, we have 2 struct ops, one for the scheduler and one for the KVM. I don't know how to do that.
What you are doing is going to be very helpful in like the eBPF implementation of things, but it would still have a separate BPF component and it would not be entirely in SCADX. So I still am looking for a bit more.
Yeah, I think the challenging part isn't the scheduler, where the scheduling is, and to Vinny's point about the kernel, at some point you do have to get the kernel involved because I'm guessing your benchmarks are purely user space and don't try to tie into the guest kernel at all. And when you get the guest kernel involved, like it's blocking on a spin lock, you have to communicate that information. And conversely, if the host is injecting an IPI into the guest and it's a priority thing, you want to communicate to the guest that that's priority, and also to the host scheduler that that's priority CPU to run faster. So it's the challenging part is for any para-virtualization setup is the ABI between the guest and the host. And so that's where my question is, what are your plans to move beyond SCADX and actually have an ABI so that you don't have to control both the guest and the host kernels and the guest and the host schedulers, because that works if you have a completely customized setup. But if you want to run a distro kernel in the guest without too much on top that is custom, you need to have an ABI that is established and can be guaranteed to a distro kernel or to some off-the-shelf guest component. So what are the plans for establishing an ABI?
So I'm also giving like another talk next week at Kernel Recipes, and that's precisely in the same direction, that we need to come up with like a consensus on how to do it. I've been studying various projects that sort of try to do peravirt scheduling, and everyone is more or less trying to reinvent the rule. They have like their own way of exposing shared memory and what kind of information they share. And I think what the vCPU priority boost patch set, it's a step in good direction, but it's still like not completely, I wouldn't say it hasn't landed yet. There are still discussions and definitely things to think about. But at the moment, again, the policy is, it's an implementation detail. I'm like a researcher. I'm more interested at the moment in making it usable to the extent that I can get feedback. I'm at that stage, but I think definitely it's a good thing to consider. But I haven't really have big proposals about what to do for ABI yet. Yeah, I rely on the kernel developers for that.
Thanks.
Hi. Have you thought about like VM-specific DSQs, or like what the DSQ layout should be for hosts versus guests? And should they be separate, or?
So this would fall into the category of workload-specific or like VM-specific schedulers.
Yeah.
And that was also a point I wanted to make, that we don't have really such kind of example schedulers available with SCADX.
Right.
So it would be nice to maybe come up with some kind of policies which are VM specific. But no, I don't have anything in that direction working yet.
Okay.
The more I think about it, the information collection, like Andrea mentioned, it need not be a part of the scheduler, right? Because we are not taking any actions per se. We are just updating the shared memory.
Right. So that was also like the first question. Is it something even worth trying to do it in SCADX? Or maybe SCADX is just for writing schedulers. If you want to do your monitoring, do it outside.
Yeah, because we don't have hooks inside a SCADX or a scheduler to do that specifically. So that's what I was thinking. Maybe do it separately.
Yeah, but I think it could be interesting to provide monitoring information on top of SCADX, because why not?
Of time. Yeah, I mean, you can reach out to us later. I'm sorry. Next one is
thank you.
Leading. Thanks, Imad. Giovanni, you're Next one.
I'm going to need my water as well. Good morning, everyone. My name is Giovanni Gerdovic. I work at SUSE, and this is an atypical presentation because we are going to have two guest speakers who are not professional kernel developers. The title, or let me pull up the title slides. How do you click? Like this. The slides is SCAD Underground. Can you see it? Custom SCADs, that's the one. Yeah, the title is heaps. Try this. The underground culture around custom CPU schedulers. The speakers, I am only a facilitator in this meeting, the speakers are hopefully on the line because they are Alfred Chen, who you see listed as an author from China, and Masahito Suzuki from Japan. I gave them the exact time of our talk, but that was 20 minutes ago. So oh, thank you. Oh, guys. Oops.
Hello.
Hey. Oh, that's me. Can you see? All right. So, hello, Alfred. Hello, Masahito. Thank you very much for being patient and waiting on the line. So I will pull up my notes and begin the talk proper. So. We're going to talk about out of tree schedulers, which is not something related to SCADX directly, but is related in some way because SCADX as a technology to implement to implement custom schedulers could bridge this gap between niche projects like the one that we're about to see and the mainstream Linux community. The friends from the CashOS Linux distribution, which are Petr and Piotr here in the audience, helped me discover those relatively popular CPU schedulers, which I didn't know they exist. They are called Bore from Masahito and BMQ and PDS from Alfred. So together with me are their authors, Alfred Chen and Masahito Suzuki. Alfred, how are you?
Hello, Giovanni. I'm fine. Good to see you.
Great, good to see you too. And Masahito, good evening. It's late in Japan, also in China where Alfred is. So how everything all right, Masahito?
Yes. Can you hear me?
I'm happy. Oh, please. Awesome. So let me introduce, give you a brief biography of them. So Alfred lives in the city of Guangzhou in the south of China. He used to be a software developer in the network and communication industry. He enjoys system programming and open source activity in his free time as a hobby. He has been working for over 10 years on this project that he will show us today. First with the priority and deadline-based skip list multiple queue CPU scheduler, which for short is called PDS, and later with the BMQ scheduler, which stands for bitmap queue. He is now developing both of them under the umbrella name of Project C. For the last 4 years, the Project C by Alfred has been a mentoring organization at the Open Source Promotion Plan,
which is a program organized by the Nanjing Institute of Technology in China, and it's very similar to the Google Summer of Code. Is that right, Alfred? Did I forget anything?
Yes, that's correct. And for the name of PDS, it's now not skip list based. So so I I have read that in my presentation later.
Because as Alfred explained me when I was asking him a question about the scheduler, that the main data structure using the PDS is changed from skip list to this other data structure he calls bitmap queue, but skip list is still in the name. So PDS, but the S is not justified anymore since a recent refactoring that he did. Now Masahito works in the IT industry in a management capacity. He is a software developer by passion and writes code in his free time as a hobby. He is from the city of Niigata in Japan, which is 300 kilometers north of Tokyo. He is the author of the Bore scheduler, which stands for Burst-Oriented Response Enhancer. Bore is the default scheduler in the CachyOS Linux distribution, which is an Arch Linux derivative with a large and growing user base of Linux enthusiasts, as we will see in the next presentation by Petr and Piotr. Did I miss anything, Masahito, in your biography?
Everything okay. Thank you.
Awesome. We will. Masahito, can you start and tell us something about your work about Bore? I can give you a presenter in the BBB platform. Are you going to do this live? Right? You don't have a recording, Masahito?
Well, I do not have recording. I'm going to talk.
Do it live, and I will pass you the presenter privilege in the app. Okay, I'm gonna do it right now, and so you can move to the next slide. You don't have to tell me next slide, next slide. You can move it yourself. All right, I'm gonna do it. Just a second. They're not in order. Masahito, yes. So I'm gonna. Great, Masahito. Now you are presenter. You should see two buttons on the bottom of the slides. If you can try moving to the next slide so we are sure that it works.
I'm going to share my screen.
Are you share your screen? Ah, okay. You don't need... Oh, okay. That's all right.
Can you see it?
I can see it very well. So it's all yours, Masahito. Please go.
Okay. First of all, I would like to express my gratitude to Giovanni Gadovich of SUSE for proposing me the opportunity to speak at this conference today. And additionally, I want to thank Linus Torvalds and many other pioneers who have been involved in Linux development over the past decades, particularly Ingo Mona from the mainline scheduler team, also Hamed Salim Al-Mari, who is not there today. He introduced me to scheduler development, like in 2021. So Peter Jung and Vladimir Nepogodin, Piotr Borsky, and all the members of the CachyOS community for their immense contributions. So you guys are so amazing. So today, I will be discussing the burst-oriented response enhancer, so-called Bore scheduler modification. Well, like many desktop Linux fans, I have been a long-time user of alternative schedulers aimed at improving desktop responsiveness. I remember various attempts such as Concolivas's RSDL and BFS, MUQSS, and legendary guy Alfred Chan's PDS and BMQ, and the Cachy scheduler family by Hamed Salim Al-Mari. I used to use all these modifications and appreciated them a lot. But in fact, I would always end up returning to CFS, the completely fair scheduler, because the reason for this is that CFS, being sophisticated, straightforward, generally performs pretty well and continues to be improved by many researchers from around the world. Although the the original CFS had some weakness. In fact, if you overlooked those, it provided good performance generally across a wide range of use cases. The aim of BOR, is to maintain as much good character of the base schedulers, in this case CFS and EEVDF, as possible, while improving its handling of case it originally struggles, and to ensure good responsiveness across more versatile use cases. The development of BOR began as an improvement to CFS. Today, the mainline scheduler, although has been updated to EEVDF, and BOR is also compatible with it today. So one of weakness of the mainline scheduler was that due to its weight-based fair scheduling, responsiveness could easily be compromised by tasks with heavy computational loads. The fundamental idea behind BOR is similar to many other schedulers that aim to improve the responsiveness of interactive tasks. Greedy ones get less. The concept I adopted is called burst time. This measures how long a task has been trying to consume CPU time since it last slept, waited for I/O, or yielded. This burst time is then log2 transformed into a burst score. As the burst time increasing exponentially, the task's weight decreases accordingly. This makes that tasks that quickly yield CPU time maintain high priority, while tasks that engage in continuous computation receive penalties and quickly become relatively weaker and weaker, achieving some sort of equilibrium between various types of workloads in system. When a task releases CPU time as well as resetting the burst time, the history of its burst score is smoothed using an approach similar to exponentially weighted moving average, which mitigates the impact of sudden spikes in burst times. Additionally, when tasks are forked, the existing scores of other tasks are taken into account, considering the topology of the task tree. Other modifications include automatic calculation of optimal base slice and also some adjustments to placement calculations upon task wake-ups. I observed that some of the idea seems to be taken into upstream changes recently. Through these changes, BOR is designed to maintain high responsiveness even under workloads that the base scheduler struggles with, without sacrificing its inherent performance benefits. So now you're going to see how it performs. Yeah.
We're seeing about 20 frames per second. Is that right, Masahito?
You should have them put, if this is a YouTube link or something.
Yeah, I know.
Have them put it into the.
In the playback. Wow, that's a lot of frames per second, Masahito.
No,
are you sure you're not breaking it?
Back high, like 200. Yes.
That's impressive, Masahito. I really thank you. This is amazing. Thanks for your introduction.
Smooth.
Yeah, it's great. I would like to switch over to Alfred and play his recorded presentation because we are a little. Yeah.
Disable. It stutters again.
Masahito, can you hear me? Can you hear my voice? 1, 2, 3, 4, 5. The cube. Masahito, can you hear me? Can you hear me? This is Giovanni from the room in Vienna.
There's no audio cracks.
I'm not getting through? That's kind of annoying. Oh. The mic on.
Okay, thank you for your attention. I now return the floor to Mr. Galovich.
Yes, thank you. Masahito, can you hear me? Can you hear me speaking? I will do it remotely with my headset from BBB online. Yeah, okay, here it works in the room.
The room are not remote.
Fine. I will play the. So the room can hear me. I will now play the recorded presentation from Alfred. They don't. Just give me. Yeah, but that's not necessary at this point. Beautiful, but the room must not lose this.
Thank you.
I'm gonna take presenter.
Attention.
Yes.
Now back to Mr. Galovich.
Wait. Keep it for later. We have now Alfred. We have recorded a video. It's coming. And I should play it. I can hear it online, but not here. This is very sad. It's a disaster. Let's have a brief introduction about Project C. Project C goes from my, I will speak it, personal development blog about 10 years ago, and now it is hosted on GitLab. The project is committed to developing and maintaining alternative CPU scheduling algorithms for the Linux kernel. In the name of Project C, C stands for cross. It's the combination of two CPU schedulers in the project. Those two algorithms are BMQ, the BMQ scheduler, and PDS, priority and deadline-based scheduler. Currently, our development is based on the latest Linux kernel branch, and we provide them in one single Linux kernel patch. We also support the latest two long-term support Linux kernel branches. Project C has participated in open source activity. For example, we have participated in the OSPP event since 2021. This activity is mainly to provide the annual updates for the long-term support Linux kernels. That's all for this page. Let's turn to the next page. In this page, we will have a brief introduction about BMQ and PDS schedulers. BMQ is a simple Linux scheduler implementation which uses the bitmap queue data structure. It is inspired by the CPU scheduling algorithm in the Zircon kernel in the Google Fuchsia operating system, highlighting the features for the BMQ. Firstly, the bitmap queue. I'm sorry for the people online. I know you hear my voice twice, but in the room we lost audio. Use the bitmap for the availability state of the double linked queue. The bitmap queue is an efficient data structure to provide the insert and delete operations. Second, the boost priority design, which provides dynamic priority adjustment upon the static task priority. PDS is a virtual deadline-based CPU scheduling algorithm, which is deeply evolved from BFS, which is Brain F scheduler by Konkolivas algorithm. Actually, it has longer history than the BMQ, and it used to be implemented with a skip list data structure, but now it is using the bitmap data structure. Like the, if I can mute myself.
Yeah, no, are you like connected via sound anywhere?
I think we can just, it's
yeah, I just want to make
over.
sure, so okay.
Yeah. The design links between the task virtual task deadline to the bitmap data structure. In Project C, the BMQ and PDS share most common scheduling code. These are also the very important parts of these two schedulers. I would like to highlight the improvement comparing to the mainline scheduler code in the Linux kernel. First improvement is the task wake up and how to choose a CPU to run on. The second improvement is the task selection in the CPU context switch. The third improvement is the CPU load balance, that is, for the long-existed hyper-threaded CPUs and the hybrid processors in recent Intel and AMD CPUs, in recent years. For example, the performance core and the efficiency core currently in the Intel and AMD CPUs. And the last improvement is the scalability, when the CPU number goes up. That's all for my sharing about Project C, BMQ, and the PDS schedulers today. Thank you. So this was Alfred Chen with some technical difficulties. Alfred, can you hear me now?
Yes, sorry for the inconvenience.
Yeah, there was a bit of inconvenience from remote, I know, because we lost audio and then we got it again. Yes, so, but I was reading the subtitles for the people in the room, so they got all the content of your presentation. And I know that online it didn't sound good because there were double audio. But at least I can tell you that in the room people were paying attention, Alfred. I can tell you that. We don't have time for questions, unfortunately, but I would really take the time to thank you for being good sports and coming to this conference, this talk, which is for Linux kernel development, and you were very, very available, and it's been a pleasure to interact with you over the last few weeks. Thank you very much. Goodbye, Alfred, and goodbye, Masahito, and see you around on the internet. Happy hacking. Right. That's all. Yeah, we need to switch the...
Okay, cool. So, hi together. Today we are doing a talk about deploying and managing SCADX schedulers in CachyOS. Yeah, and this also applies to other distributions. So now we want to just introduce us, who we are. So I'm Peter Young. I'm doing mainly the package maintenance, testing, and infrastructure at CachyOS, and I'm test engineer. Vladislav is mainly doing the software development of CachyOS and like our Cachy builder and also the welcome screen and others. Piotr?
Hello, I'm Piotr. I'm kernel maintainer in CachyOS. I work as academic teacher in Poland.
So, what we do, we started in May 2021 with CashOS as a hobby project. We are an Archlinux-based distribution and focus on performance and user experience. Also, we have shipped about the last few years out of 3 schedulers, like Bore, Kakulib, BMQ, and TT. We have adopted SCADX in late 2023 and helped a lot with the integration of SCADX into distributions and also shipping this to users. And now we want to share the experience to here, and yeah. I'm gonna skip the next 2 slides, which mainly introduce the CashOS project because of the time. And Piotr will now talk about the integration with systemd.
Hello, everyone again. I will say a few words about our implementation method in CashOS. At beginning, we didn't have any method of auto start to schedulers, and there was only one way to run scheduler. Just type scheduler name in terminal. It wasn't a good solution because we cannot start scheduler at boot, and in this version we have also some problems with logs. So I decided to choose systemd service to allow users run scheduler on boot. And my first idea was to create a separate service for each scheduler. And that wasn't a really good idea because too many schedulers could be confusing for users. To enable scheduler on boot, we should start one service, and if we want switch to another, we should stop previous one and start next one. So as I said, there was not good for users, so I decided to make it a different way. So I decided to create one parametric schedulers, and how it works. A very important option for this solution is condition path exists. You can start your system with another kernel, for example, long time support, and service won't fail, just won't start because condition was not met. And very important thing about this implementation is config file. And service read config file from etc default xtxt config. You can set here scheduler and flags. And when you start with default settings, BPF land will be start. But now I would like to thank Pietro Righi, son of my teammate Andrea, because he introduced a very cool option. We can override our current settings, but set new variable, and if we set variable and restart service, new scheduler is running, and if we unset variable and restart settings again, default setting will be used. As I said, we have some problem with logs. In previous version of schedulers, schedulers displayed a bunch of log statistics, and if we want to use main journal the namespace, it will be a big mess. So I decided to create separate log namespace for schedex, and we could check logs in this way. But thanks to Tejun, we have now a very cool improvement for STX schedulers, STX stats. So now statistics are not displayed anymore by default. But if you want to check statistic, all you have to do is just add monitor and interval parameter. Interval just amount of seconds. For example, half seconds, 2 seconds, 5 seconds, and so on. And statistics will be displayed, and we can check what is going on. But I know that console management could be very hard for beginners, because it's very hard to use if we just begin our adventure with Linux. So in CatchOS we have prepared some graphical user interface for that. We have very cool soft called CatchOS Kernel Manager, and in this software you can build your own kernel in graphical user interface. You can add custom patch, custom fix, and so on. But the more important thing is that you can set scheduler in graphical user interface. You can also add flags, profiles, and now my teammate tells something more about benchmarks.
Hi together. So in the CashEOS community, BPFland and LAVD is the most used scheduler so far, and we have seen with BPFland improvements of interactivity, and especially under heavy load scenarios, the desktop stays responsive, which is good for workstations. It shows a better FPS stability too, so the difference between the high and low FPS. Also, it has hybrid support, which, like at newer CPUs, like the AMD ones, which has only one CCD with cache, and also ENP cores. Additionally, it provides predefined profiles, like for low latency scenarios, gaming, and power save, and there I choose different options for the scheduler. Shang-Wu already showed what LAVD is for. It's mainly focused for gaming. It shows improvements in 1% lows and average FPS compared to the EBDF scheduler. I have also a benchmark in the next slide. This has been used by the Steam Deck in the future and has been also rolled out by some handheld gaming distributions like the CashEOS Handheld Edition, Bearside, and others. Additionally, it provides the auto-preload feature, which changes between different loads the scheduler, how it acts. So here we can see a slide between EVDF and LVD. In the average FPS, it reached in Baldur's Gate 3 around 5% higher FPS. And this was equal to at the 1% lows and 99%. So STX Loader is a scheduler manager which basically provides a dbus interface to switch the schedulers with some tools like Power Profiles daemon. We have been in contact with the maintainer of Power Profiles daemon about the integration with different profiles, and they generally agreed, and in the future we will work on a configuration file for Power Profiles daemon to provide a seamless integration of SCADX into Power Profiles daemon. The problem is, in general, launching SCADX schedulers or managing a systemd file is problematic because it requires sudo permissions, and if I want to change, like for a game, want to change the scheduler from EVDF to LVD, the user need to start the scheduler with sudo permissions, and this is inconvenient. So this can provide a dynamic scheduler usage depending on the workload and profile, like CPU governor works. The dbus interface provides several features like start and stop the scheduler, get the current running scheduler, the current mode, and support the scheduler. It gets started via a systemd service and waiting for signals. It can be also used to switch between STX and EVD, like the default scheduler, and yeah. So now questions? Yes? Sorry.
So you mentioned the comparison between EVDF and LAVD, and I think you should probably also look into tuning EVDF. Like what we see is like the default EVDF, it has like a lot of context switches. I think it's 4 or 5 times. I forget the exact amount, but we're seeing like large number of context switches. So you have to increase the base slice, to reduce that amount. Otherwise, the overhead is quite high. And then the other problem with EVDF that we see is the eligibility feature in EVDF, for which there are some new fixes. So EVDF definitely has problems, but with tuning, it performs. It can perform well. So I think you should probably do those tunings, and then rerun comparison and see how LAVD is doing.
Yeah.
Hi, Joel. One remark: the base slice length, right? I remember Youssef Esmat talking about Chrome OS. This is something you can do from sysfs, right? Yes. It's not a patch. It's you set a different base length, so that it's something that the distro can do and ship like that, right? It's not a patch. Okay, no, I want to clarify that.
Yeah, also already doing this like at a customized kernel, which EVDF includes as scheduler. But in this test case, we just wanted to test also stock EVDF versus stock LVD to provide proper results, and not, hey, there's tuned, and then maybe there comes some confusion in the benchmarks.
Right, because in fact, they're not using EVDF at all. This is a comparison to make it resonate with the audience, but they use Bore from Masahito from the presentation prior. That's something that I forgot, but it's also worth mentioning that the CacheOS by default does not have an EVDF. They use.
Yeah, it's provided as a second kernel, but as default, it's the Bore kernel used because it's very good for desktop usage, and yeah.
It's pretty funky in the CacheOS land. Thank
you.
No, I will share the screen. No.
you share
They need to share the screen because, yeah, I need to share the screen. Let's see if it works. I am connected with the tablet. I'm not going to say it. May not run Linux, you know. Where's the screen sharing? Can you help me? Where's the screen sharing? Okay. All right, so no screen. Okay, fine, no problem. I don't know. Okay. So no screen sharing. All right. So we're gonna do without screen sharing. So you're gonna get a subpar experience. I had planned a more engaging. That's right. So let's get the take presenter. I'm presenter. Now the slides. Okay. All right, so welcome to this session. My name again is Giovanni Gerdovic. I work at SUSE, and this is a session that I intend to be as a roundtable, a forum where we can share experience or try to identify issues, not necessarily solve them, but try to identify issues regarding the possible shipment of SCADX to users, so into the distributions. And so that's what it is. I hope it's not going to be just me talking to myself, you know. I have sent a couple of emails to invite people from other distributions. I see some faces, so let's hope for the best. And I would like to try something a little fancy in this session, which is to do live polls. For that, I would need my mobile phone, which I've lost. The live polling that I have set up, and we're going to see if it works. Maybe it doesn't work. Maybe it's going to be very cringe. I don't know. So the way I have intended this is that more or less you all have a device. Could be a laptop, maybe a smartphone that's likely to be connected to the internet. So my plan was to ask you to go to this website, which is called Slido, like slide, but with an O. Slido.com. So if you really would, I would really appreciate if you can play along and indulge me into this. Because they can't log into the, it's inconvenient to log. The reason I'm doing this is because I thought that asking the audience to log into big blue button and enter the, all right. I mean, why didn't you do that? What kind of, seriously, why don't you just? What kind of, this is better. This is, seriously. So Slido.com, and then you have to enter a code for this poll, for this event. And the code is 1310125. So I am confident that all of you are there. And I will now start it. The first few polls are warm up, just to get familiar with this format. And I will now start the first one. So it should be up. So now if you have the website, I'm asking, and this is why I wanted to share the screen, the poll says, for the people at home, which Linux distribution do you use or develop? I wanted to know who's in the audience, right? So to know if there maybe some distribution is not represented in this audience, so that's something that I wanted to. So to give you time to vote, I'm going to read the options that I have enumerated: Ubuntu and derivatives, Arch Linux and derivatives, for example, CashOS, Debian, Gentoo, OpenSUSE or SLAS, Fedora or RHEL and derivatives, Android or Chrome OS, we got a few, other, and then I don't use nor develop Linux, which, why not? I mean, we're inclusive, and if you want to. So, unfortunately, I would have liked to share the, maybe I can, no, I cannot share the screen with this, I can share the screen. No, I can't share the screen with this. I can share the screen with this, right? This can. It should do. Anyway, it's cumbersome. All of you can see it, all right? So I'm not going to do that. So exactly, we have Ubuntu and derivatives 28%. Then second is Fedora or RHEL 26%. Arch Linux and derivative 15%. And then we got OpenSUSE, yay, 13%. And then we got some Debian, some Gentoo, Android, but those are less. All right, so I'm going to stop this. So we know that we have Ubuntu, RHEL, Arch, and OpenSUSE. So stop this. So you don't see anything else, anything. And now I'm going to start the second poll, which is still on the same page, which is very cool, I think. We got 55 votes, by the way, so this is statistically significant. So the second poll, which is now up, is which field of the IT industry do you operate in? And I'm asking this question because I find that the interest towards KDEX or the diffidence often relates to what's your job. Like if you have to support it, you say, wait a minute. But if you want to use it to make better services for your own platform, for your own service, for your own company, you say, yeah, sure, I want it because it's another tool, so I want to use it. So there is this is why I'm asking your job. But as you see, I didn't ask you a login or anything, like this is all anonymous. So I'm gonna, I enumerated all the different fields that I think are in IT. I will read only the major responders. So we have majority of distro vendors, 37%, thank you very much. So you're in the right room. And then we got social media, good guys, I know who you are. And then some semiconductors, that would be like, you know who you are. And academia, cloud computing, consumer electronics. Yeah. All right, so we know who we are, and we can get started. I'm going to stop this poll. How many people? 56 votes. So I think we're doing good. Thank you very much for indulging me. I was skeptical if this was going to work. OK, so now we can start. Next slide, please. And that would be this. Yes. This is supposed to be a forum, so the mics are available, I hope. So just, bring it on. OK, disclaimer. My employer, my organization, is undecided on whether or not to include this in our enterprise distribution, at least for the moment, and we're evaluating, right? So we don't know. Community distribution, different story. Like the only limit is the time you can put into it. But we have a couple of packages, and and this difference, I'm going to mention it later also in the talk, which is you are bound to provide commercial support or not, and that's all at least for the people that I've talked to, at least for our point of view. Oh, I have a raised hand. So please, go ahead.
Hi, can I be heard?
Neil Gompa, please.
There we go. There we go. Now I can be seen. Hi. Sorry, I'm not there in person. I would have loved
So
to,
there is a problem.
but,
We're not hearing you. We're hearing some of your voice, but it's very, very low in volume. So I'm not sure if it's on your end, on our end.
Let's try boosting it. How about now?
Yeah, I think. What do you think? What do you say? It's better. Like, can you guys hear that? Yeah. From back of the room, they say yes. So please go ahead.
Alrighty. Hi. Sorry I couldn't be there in person. But yeah. So I'm gonna say something that's probably a little bit weirdly controversial, but as a distro vendor, particularly one that does stuff in desktop Linux, because I work in Fedora and Fedora KDE in particular, SCEDEX is going to be a boon for me because the main scheduler that's part of the Linux kernel is pretty bad for desktop workloads, like almost across the board. And it's been that way for such a long time that most of us, as desktop developers and whatever, have kind of given up on ever getting anything improved for us. So for me, SCEDEX is very interesting because I see an opportunity for us to make the desktop experience actually match responsiveness of, say, Mac and Windows for a variety of desktop use cases, because no one else seems to care. And so we have an opportunity now to fix that. So I want to ship it sooner rather than later.
There is a mic here, please. Does it work?
Yeah, so earlier today I mentioned one thing is I don't really want SCEDEX to be the scheduler for anything else. If you are using SCEDEX for your production, or across the board for distribution, you're doing it wrong. Because SCEDEX is, to me, something that's great for evaluating new type of algorithms, for research, fast things. I love SCEDEX for that. But when it comes to actually, if you have something, we're going to be passing this, this third party, or everyone's going to be doing their own thing. And I mentioned earlier, what I would love personally would be have like a governor type of scheduler where you would say you would have, because right now I really believe, because you have Red Hat, SUSE, everyone is using, basically developing their schedulers for, what's the word I want to use? Yeah, we're looking for the mic. Yeah, where's the throw mic? Anyone have the throw mic?
Yeah, I do, sorry.
You're hiding it, because that way the camera doesn't see who I am, so that's why, yeah, see here. So So the idea for the desktop thing, what we really need is a desktop scheduler, because right now everyone's developing it for the back end. The money that's going into Linux for development is mostly from those that, where's the money? It's in the Googles, the Metas, the high frequency trading. They don't care about desktop. And what if we had a separate scheduler that was just for desktop, that you had just maybe a small group, but everyone had a single source to work on in the kernel, I think you would develop and improve the scheduler. And another thing what I love with SCEDEX is someone like, say, if you are with the Googles and everything else, you could say, hey, we're trying this new, we have this new algorithm. Hey, does this work for you? And then throw it to them. They just have to throw in the SCEDEX scheduler, test it. If it works, great. Then they can implement it back into the C code. That is what I'm actually pushing. So yes, I agree. I'm on the Chrome OS. So yes, we suffer the desktop issue as well. And we have a bunch of hacks to get around it other than SCEDEX. But this is what I think would be the goal.
So I think the difference between what you're saying and what I'm saying is that for most of us on the desktop side, over the years, we've given up because we've tried. I know that, for example, Kolivas tried for years to bring a desktop scheduler into the upstream Linux kernel, and frankly, no one cared then. And there have been subsequent attempts in the going forward, even to integrate some improvements into the main scheduler. And it doesn't actually matter. So like for the rest of us, what are we supposed to do? I think the real reason that SCEDEX happened, and I'm really, really, really stoked for it personally, is because it gets us out of this stuck loop that we've had for almost 15 years. So like, unless something is seriously changing in the scheduler community upstream in the Linux kernel, I just don't see that ever happening.
I'm actually one of the reviewers for the Linux upstream kernel scheduler. I was actually involved in some of the cons, the flame wars back then. So yes, I am very well. I'm friends with Peter Zylstra and everything. And Yuri Lely, who's another scheduler maintainer, is sitting right behind me. Things are changing, and actually, this is I was a proponent for SCEDX because I've always been a proponent for this separation. Yes, there's been this ideology. SCEDX, I even said earlier, SCEDX actually came about, as you said, because the desktop scheduler was kind of being ignored. I'm for that, but I still think, yes, that is basically, I think SCEDX is a stepping stone to the goal. Yes, for you, from your point of view, you just say, finally, we can do it ourselves. But SCEDX is causing the change to happen, and we might as well do it properly and not through a hack.
So the only thing I would add is that it's kind of difficult to predict how things are gonna go from here, right? So like predictions and reality don't always agree. So as we gain more experience, and I'm sure you will too, it will develop in certain form. So it may be that the eventual form it takes is that we're going to implement back the ideas back into the governors in the kernel, or maybe maybe something doesn't make that quite appealing, right? So we don't really know for sure how it's going to happen, but I think that is definitely one of the possible scenarios, and I think different people might reach different conclusions. So we're just going to have to see how it develops, right?
I guess my perplexity is who's going to do the work, because as far as I understand, I mean, in your case, you're essentially perfectly fine with using the BPF implementation, because I guess it works better for your use case, even in production. So I don't think you have a feeling of, okay, I need to spend more time in maybe going towards what Steven is proposing. I'm not sure if Chrome is maybe willing to do that. I'm not sure. From distributions, as you said, I guess my personal understanding is that it's maybe not our main focus, like more several type of workloads. And so who's actually doing? So we can probably agree, yes, maybe we want to go towards what Steven said, or maybe not. I mean, that's up for discussion. If we say yes, who's gonna do it? That's, I guess, the main question.
Yeah, I mean, it's a valid point. And there's also another thing, is like the fact that SCEDX is a fairly new project, because it's been developed for 3 years or more probably, but it's approaching to the upstream now. So trying to plan for the next step, that would be either a governor approach or extending SCEDX to have a pluggable scheduler. Who knows what's going to happen? But these are valid points that I'm glad that they're coming up at in this place. But yeah, we need to keep in mind that it's a new project.
So like I said, who will do the work is actually a very good question. And I'm hoping that we could get funding on my end to help we do it. It's still questionable because we're going through it ourselves, the whole reorg right now. So we're trying to figure that out. But that's one of the reasons why I was a proponent for SCEDX, because usually I'm not a BPF person. I've still yet to write a BPF program. So no, I haven't needed it. No, I actually I just modify things, but that's another story. But no, I'm saying when I saw this, I've always struggled with how. Actually, I was talking with Linus Torvalds at the ARM Summit, and I brought up SCEDX and stuff like that. And this is when he was still saying no, and. I said to him, we have like this environment, like we don't care about, all CPUs. We have a few CPUs. We have one user, and that we want to really tune our scheduler for this one user. And every time we can't make a modification upstream, and Linus goes to me, he goes, well, yeah, if you modify the scheduler, he goes, yeah, about this pluggable schedule, but everyone wants to do their own thing, and if you modify it, you break someone else's workload. And I said, yes, Linus, that's the rationale for having pluggable schedulers, so you don't have to worry about breaking someone else's workload, because everyone has the same workload here. And he just got quiet and walked away from me. So, anyway, well, actually, someone raised their hand, but I just realized it's lunchtime. There's food. So one last question, and we should be having food.
Neil, I think. Please, Neil, we close with your intervention, and then we head off to lunch because we are out of time. The lunch break was exactly now, so we close with you, Neil, please.
Sure, and then I can go have breakfast. Yeah. So like I think all the comments here are good. Like I just want to kind of close with saying like the underlying reason why, like from me as a desktop user and developer, that I'm excited about SCEDX is because the way that prioritization tends to work with having just the one scheduler is, things like user interaction, micro stutters, and stuff like that. Those are scheduling problems that we just don't have a way to get anyone to care about in the upstream Linux kernel. And so if that changes, that's fantastic. And that'd be great. But right now I have to work with what we have and what people are willing to deal with. So from me, like I want SCEDX to be everywhere, and I want it to be a tool that desktops can rely on directly to be able to do the right things for their user experiences.
Yeah, I share that sentiment personally. This is not the opinion. I thank you very much for being good sports and participating to the polls. It's lunchtime. Thank you to the remote attendees, and let's go have lunch.
Thank you, man.
I hear his voice. He was like, he and I don't agree. But so I'm not speaking for him. On the email that you sent out. So probably yes. Didn't have anything to add, but yes, yeah. What you guys were saying there. I was considering jumping in, but we just hang on time. I'm much different from what I was saying. Maybe a stepping stone to getting more development on the schedule. I don't know whether anything's been decided yet. It's given to 612, it looks like.
That is exactly, yeah. Yeah, but I couldn't get to it. Yeah, yeah, exactly. Those are, yeah. It's a discussion that we need to have, because now we are at the I don't like it, at that level. But we need to move forward and say, let's get it, but there are some items that needs to be, we need to decide how to solve the provenance, supports, like do I support the rest of the kernel, not your scheduler, or do I support anything and you're on your own? Those are things that need to be clarified, and I don't know, some working group, something like that, because...
And also the fact, like, people may want to use, like, a local system, so what happens if you load a scheduler that is not signed, because we don't have signed BPF programs.
Yeah, the secure boot situation.
How do you support, because right now you can just load the BPF program with a locked signed kernel, but that goes a little bit against the fact that you can't modify code. Even if, it doesn't have some big security implications, maybe. It's something that from a distro perspective should be considered.
Yeah.
And for Ubuntu in particular, there's also the fact that we need to find a way to have the user space stuff in Debian. That's why I got
First it goes in Debian, and then it trickles down to Ubuntu, right?
Yeah, if it's in Debian, it goes automatically.
Yeah.
And for the all user space stuff, especially the Rust part space, I look at the link that you sent me. There's that's good. We just need to add the few crates that we need and package those. So that part is, I think it's easy at this point, because the crates that we need are very well defined, and we just need to.
And in this way, like if you start getting the packages, in this way we start talking about some actual experience, like you start getting the bugs, and you start looking what they look like, because now, if we attack those 4 items that I listed, which were like quality, support, provenance, and tool chain, we're talking about hypothetical, because people are not using it, so you don't really know. Maybe it happens like this, what if it happens something in a different way? But if you start getting the packages in the community distro, then you start getting an opinion on your own, Because it is, I see a lot of diffidence, I don't see progress, and so someone needs to break this stall.
And maybe for initially, like if people start to use their own schedulers and they're complaining about performance regressions, it might be reasonable to like taint the kernel. If like, for example, in our case, have a source patch, have a source patch that taints the kernel if you load your own schedule. So once it's tainted, it's tainted. And you can see like,
this is something I wanted to bring up because I studied, I thought it tainted, okay, goodbye. But in the SUSE wording of what happens when it's tainted, it is, we say the support is limited. And so our engineer has this as a tool to say, look, you're tainted, so be glad that I am even looking at it, and then you have to establish if the tainting, the module that is tainting is related to the bug. You see what I mean? Because it doesn't say go away, because it's business, you know. So if you taint because of a networking driver, but you have a file corruption issue for the file system, you say, okay, it's tainted, but it's clearly unrelated.
But we have another problem, which is we support NVIDIA drivers, which taints our kernel. So
it's already tainted.
It's already tainted. My desktop is tainted because of NVIDIA drivers.
But you can add a new flag. You can write a new flag. It's called scheduler. You know. You see what I mean? Because now you tainted because you're lighting another 3 module, or there are several flags, right?
Okay.
One of them is the one for the module, but you can have a SCADX thing.
So
new one. You know?
It's true that we have the CSFS interface to show if you're running a SCADX scheduler or not. But what if I load my own scheduler, then I do crappy things, and then I unload the scheduler?
No, taint is like forensic evidence. That's
exactly.
That's the point.
We need a persistent state that says at some point you loaded your custom schedule. Because distro people, that you may get a bug report saying
like when they open it, not legal reasons,
not legal.
Have
support, because you may say. Yeah, but how do you check? Like people are just throw you the D message. How do you figure out like if at the time of the performance regression?
Kind of because the world is messy, you know, because those cases.
So this is not upstream Linux. Upstream Linux it's more of a distro, I think.
Yes, I'm talking about our.
And maybe that can be, but first of all, it needs to be tested on the distro. I think it's just going backward in this case. I think.
And in our case, we have.
And if it solves problems, then we may consider.
If I add like under there's a sys kernel SCADX, right? I can add like a older sequence or something. You can just read it.
Maybe that's.
So you know what happened in the past. I see.
Why not?
So this is not a taint flag. It's a new.
Just a sequence number. Just a file you read.
It's a file in ProcFS.
I can just add it.
But yeah. So the thing is like, for example, in Ubuntu they need to modify their Ubuntu bug report script to grab this file.
Yeah. To read first for
Yeah. So it's doable. It's just a silly script, but it's work to do.
Flag is just
tainted is no, it's not. I mean, you can't do this and send upstream and say, oh, I'm going to taint the kernel. No.
Okay. I think that part I missed.
Yeah,
it's a bit of taboo to add the new taint flag or what?
taboo, but I don't know. It's just kind of.
It's more difficult to convince.
Okay.
Yeah, and if we don't do a taint, then I feel like if we have like you mentioned like a file, it would be easier to add support for like supported.
Or like another thing is that
schedulers, because distros are probably going to want to have supported ones.
Yes. And one of the items I wanted to attack is how do you know if the scheduler that the user is coming with is one of the list? I don't know.
Like, so you probably have to have some sort of signing.
Signing, but people in the company have said signing, say, whoa, that's complex, and then you have a certificate authority and stuff like that. Let's have like a metadata, like a stupid.
This is just checksum.
Yeah, it's a checksum.
Not cryptographically sound, but it's a simple checksum. Exactly. The metadata that I was trying to, so you can compare them. Yeah.
Also, like when you load and unload the scheduler, there's a P message, like a print case.
Yeah.
So in this you can tell from when to when.
And to start, that's probably the best.
Yeah.
To start, just print K.
Yeah. I mean, it already does that, so you already see the column.
But now I understand when you say I don't want SCADX to taint the kernel, because then you have people using SCADX
It's just
this
used
is the
for
reason.
different things, right? So paint is mostly used when action in the past, right, can be contributing to the bug now. So that's what it is mostly for.
Yeah.
But it's not for keeping history, right? It's just that like the kernel is in a state where the past action may have corrupted the current operation. That's what it primarily means. So it's just a little bit different here, right? Because here, like when you unload it, it shouldn't have any side.
It's for something different. I see what you mean. It is not the right tool.
Right. So it's not like it's for persistent things, right?
Yeah, this is not. Okay.
No, but having the checksum is interesting.
No, it's necessary. It's not it's necessary.
Something like that. Like you say, you specify like requirement. If you load this scheduler, you must match this checksum, and that could be helpful for the distro guys.
What would be checked? So I can see it being generated and like printing that out somewhere. But what do we use to check that checksum? Like where is the master list of approved checksums?
Okay. This is later. First, let's lay the foundation, saying okay, there exists a checksum of the scheduler, and then we will build a list of those that you trust. And
like we need an interface that says.
But first, you need the.
This is the white list of schedulers that you can load with the name and checks or just checksum. I don't know if the stat check doesn't need the name.
Now, the establishing if a schedule is accredited, different story. Like you need to study, you need to understand. But first, I think that this is will happen. It's necessary. Several Oracle as well said something like this.
Oracle was more brutal.
No, yes, and they say we only want to allow our schedulers and not those of other people. And I asked, so how do you tell them apart? Oh, yeah, I don't know. So this is mechanism is necessary, and then built in the list, it's a separate, I think, task.
But there's also the thing like, can all BPF program be checksum?
Yeah, no.
Actually, BPF has like a support for like generic checksumming. I don't know.
But this is exactly why signing BPF program is difficult, because it's not an ELF file that you say, okay, this is but there is a loader that sections this program and put it elsewhere in the language. Probably is not treated. Probably is not treated. Let's go to lunch. I'll join you and collect my stuff, okay? Yes, absolutely. Yes, let's go. Yeah, let's do it. I think there is a social event for the plumbers today, but it's okay. I mean, let's absolutely, yes.
Thanks for organizing.
Yeah. No worries. No worries. I like the adrenaline, the adrenaline of.
The live poll was a lot of fun. You should do that more.
We should do that more. 100%. Yeah.
All right. See you around.
See you. Bye.
Yes.
Cool. You don't really need me much, do you? I said I'd shepherd this session, but...
Okay. You are welcome.
If you're okay, I may pop next door because I really wanted to see what's happening.
For sure.
So yeah, I'll go around and make sure everything gets started. Okay.
Yeah, just checking if everyone has the PDF.
Ja. Aber sonst geht's gut. Ich habe auch schon keine Dinge machen. Das passt schon. Den habe ich nicht, da steht nur Catchbox-Akkus, habe ich getauscht, aber. Ach so, ja, ja, das habe ich schon. Habe ich ja schon. Bis später.
Hey, can you open the mic here? Hello. Hi, everyone. My name is André Almeida, and this is Daniel Stone, and we are the organizers of the Graphics and DRM microconference. So welcome, everyone. First of all, we need to thank our sponsors, because without them, it couldn't be possible to have this event. And also, it's good to remind that we have a code of conduct. So please be polite with your colleagues here. And if you need help, you can contact anyone from Linux Foundation or the conference runners to have assistance. And yeah, that's it. And our first speakers are Ellen and Sebastian.
So hello everyone, my name is Sebastian Fricke.
My name is Ellen Koike.
And we would like to present to you our approach of unifying different GitLab CI approaches for the Linux kernel, so for different subsystems to use CI systems.
So let's start reviewing about what is DRM CI in case you are not familiar with that. So what is DRM CI? So DRM CI is a GitLab CI definition. It's a pipeline to test the DRM CI subsystem. It is an in-tree solution. It also uses the free desktop infrastructure, mostly because of the connection with labs to access the devices. It also has annotated expectation files, so all the tests that are supposed that we know that are failing and that are flaky is documented inside the kernel code. How you can use it? You can just add a repository inside the gitlab.freedesktop.org, and you need to request access to DRM OK group to have the permissions, and you can trigger your pipelines from it. This is how the current pipeline looks like. So first we have a stage that we build like containers with everything that's required to run the rest. Then we have a stage that we build the kernel and the test suites. Then we execute the test suites on top of several devices. So each of those columns is a different driver. And the last column there is where we run tests on top of virtual machines. So we execute, for instance, on top of a VKMS driver.
Okay, so now that we know how DRM is doing CI, let's have a look at how other subsystems doing CI. So here we have a look at basically the Media CI, which has recently done a new spin-off of their CI, which was previously done on Garrett and is now done on a free desktop GitLab instance. What you can basically see is that we have some overlapping parts. So obviously we also do that whole thing in containers, and also we compile the kernel. So, but with a few differences. For example, we not only compile with GCC, but we also compile with CLang, and we compile with different versions of GCC. But we also do, for example, cross compilation on multiple architectures. Another thing that we do a little bit different on the Media CI is that we have some static checks like smatch and sparse, and we do some linting. Like, for example, we do check patch, and we do some checks about like trusted users for for getting patches merged. You have to have trusted users from a group of people, which are basically committers, and so on. And one other special thing is that we do bisecting tests. And what you can see there, which is missing, is that we don't do tests on real hardware so far in the Media CI.
So we have those two different solutions, but we also have another one called KCI GitLab. Well, we were discussing the name during lunch today, but and this proposed solution is supposed to be like a common base for all those CI. So let's understand a bit about it. So there is a patch that was submitted on the end of February this year, and it's, as I mentioned, it's meant to be a common base. It has this feature called test scenario, where you can override the jobs that's already defined there, and is also easy to test, to share your test scenario. So it's a bit like a device tree where you have, you can include the configuration file and then override the properties, and you can share that specific device tree, right? So in this case, would be a variable. This is how the pipeline currently looks like. So we also have the containers, we have some static checks, and we have build. So we build documentation, we build the kernel with different configs, and for different architectures as well. We have also another stage there just for optimization. But then the idea is this to be a base so we can put the others on top.
All right. So now we had a look at how DRM is doing CI, we had a look how the media subsystem is doing CI, and we have looked at basically what we see as the common ancestor for both. And so to see that in more detail, we now have a look at the differences and the similarities between all of these different approaches. In this graph, you can see basically on the very left side, the things which the media CI is doing, which are neither found in the KCI GitLab so far or in the DRM CI. The same thing on the very right side for the DRM CI. And in the middle, you can see what the KCI GitLab is currently providing, which is used by basically both of them, or which should be used by both of them. So let's start with the middle one. So basically in KCI GitLab, we already have all of the compilation things, all of the container preparation things that you need. We have like the basic CI preparation that you need for doing your CI system on your subsystem. We have the static checks, we have like the linters, like checkpatch, for example, and we have the whole free desktop CI templates, which are currently used by both of these systems. And we do basically testing of documentation as well. So when we look at the differences, we can see that Media CI is currently doing a bit more extensive compilation, which can easily be added to KCI GitLab, but that's just something which is currently a little bit different. Bisectability tests are currently also not available in KCI GitLab, and also this trusted user check, which I talked about earlier, is currently not found in KCI GitLab. And on the DRM CI side, we can see basically the one big problem that we currently have, which is that currently the DRM CI is doing tests on real hardware via Lava. This is currently not implemented in KCI GitLab, but we basically envision that this could be done by the kernel CI tools to basically do those tests in the future more easily, and that could be then implemented in KCI GitLab for both of those cases. And also the DRM CI has a concept of having lists of flaky tests or tests which have accepted warnings or accepted errors. And with that concept, they can achieve that only patches with the 0 warnings and 0 errors are accepted for merging. And that's a pretty good concept, which could also be merged into KCI GitLab. And a thing which is currently found in both of them, but not in KCI GitLab, like the orange part, is that both of these CI systems, like the DRM and Media, have special test suites. And these special test suites, they run on virtual machines in order to test for specific behavior, basically. And those things would have to be merged into KCI GitLab as well.
So how DRM, right, and DRM CI could profit from migrating to KCI GitLab. So we are not doing any static checks at the moment, so we could get this from KCI GitLab. It's also easier to specify test scenarios like per driver and per container. Right now, when you trigger a pipeline, it executes tests on top of different drivers, or you need to use a specific tool to only test what you need. With the concept there, it's easier. Also, the idea there is to be independent of platform. So right now we depend on free desktop. So ideally later we would be independent of that. And it can be also a base for other tests, since executing like K-self-test and K-unit, it's pretty standard the way you execute it. So we could have a base for all the subsystems.
Okay, so now that we looked at the different aspects like of that, we would like to show you in detail a bit which problem we actually see to be solved. And the problem that we see is that with the efforts that we currently see on the media subsystem and on the DRM subsystem is that a large group of people is basically building the same basis for two subsystems. And this looks pretty inefficient and duplicated for us. So we would like to have a common ancestor for both so that any work on that, like any update on the latest best practices, for example, benefits for both subsystems. And not just for both subsystems, but also what we currently see is that for another subsystem which hasn't put any effort so far into a CI system, the entrance barrier is quite high. Like you can't just set up a CI out of nothing. And we basically envisioned that with a better common ancestor for both of these systems, another CI system, like another subsystem can easily take that approach and build upon that. And which also then has the issue that currently each of the subsystems has to use their own infrastructure. And they don't benefit from any infrastructure from someone else or from the work from someone else. And so that's currently the problem that we see.
So why should you care? The idea here is we could reduce the maintenance cost. We could get more reviewers to the RMCI. We could also have other kind of tests and infrastructures included with reduced cost. And we as a community would also be contributing to other subsystems as well. So we would be contributing to the Linux testing ecosystem as a whole.
And which downsides did we identify so far? So one thing that you've probably noticed while upstreaming to the Linux kernel is that whenever you have a big community of people, reviewing changes and getting them accepted is sometimes a bit harder. So that is definitely something where changes cannot be made as flexible and as quickly maybe, but which also has the upside of you can't do failures that quickly. So that it's definitely a bit harder. And also when you want to design a new change, you have to have a bigger scope in mind for that design. And another downside is that currently the whole KCI GitLab thing, as the name says, is pretty much specified on GitLab. And so it is not impossible to have a new spin-off in the future, for example, to make a GitHub base. That's not impossible. But for now, this approach is pretty much specified to GitLab.
So here are the steps that we'll need to take to migrate to KCI GitLab. So first we need to finish upstreaming KCI GitLab, which means that we need to move it to tools/CI folder. It was one feedback from Linus, to be more like a generic thing, like a library-like. And the point for DRM would be that we need to utilize these scripts from tools/CI in the RMCI. So we need to submit the version 2, and the work is estimation there. It's 2 weeks of FTE, but only 2 days just for the point 2 there for DRM. And the second part would be to move completely the DRMCI to use the test scenarios from KCI GitLab. So one of the paths that we see is instead of being dependent of Mesa CI to do to dispatch all the tests to devices, we could use the work being done inside the kernel CI initiative with the kernel CI labs. So using them as a hub of devices, for instance. Once they have that structure, we can just migrate and re-implement the dependencies instead of depending on Mesa CI, which would depend on that specific software, which would simplify a few things. And then we can write the test scenarios inside for DRM. So work estimation for that, assuming that the kernel CI project is ready, it would be like 2 weeks as well.
All right, and so with that said, we would basically like to know your opinion about this. Like, is it something you would like to approach, to have the DRM CI on a new ancestor, or not? So any questions are open yet? Otherwise, we have some questions prepared.
a small question. So currently, it is not that we are just using Mesa CI. It is that for DRM CI, we are sharing devices with Mesa, and actually we are more of a user on top of Mesa rather than a main user. So how do you plan to share it or to share the existing devices, existing setup with Mesa? Yeah. Just because they are doing more tests than we do in DRM.
Right. So the question is regarding how we plan to share the devices with Mesa since they are doing more tests. And just one point that you mentioned, we are using Mesa CI in some point because we kind of include their YAML files directly from a specific version. So all the scripts and definitions about how we dispatch the tests to the devices is inside Mesa. It's not in the kernel part. So we are using Mesa as a library for CI. So regarding the sharing the devices, right now what we are doing is we execute the DRM CI tests on lower priority because for Mesa is more time critical. There it blocks patches from being merged. So this is how we are now currently handling the resources.
How would you handle that with KCI?
So So the question is, how would we handle with KCI GitLab? The idea here is if we manage to use kernel CI as a hub for labs, the kernel CI API would provide all those options. We could do something similar regarding priorities as well.
I'm probably taking too much time on that. But how would you share the existing devices with Mesa? So that's how I...
Right. The question is how to share the existing devices. They can be shared across several projects, actually, that they are not dedicated to a specific project. Yes, it's still using Lava. So we would have like a layer and using Lava behind it or any other kind of lab.
So very quickly, I don't want to eject the discussion towards media, but you introduced the media CI, which is great. But as you said, we don't do device testing right now. Is there anything that could be reused for the DRM CI to introduce device testing in media as well? Is that in the plan, or is this something that you...
Like the idea is that...
No, not the idea, the exact... partially the answer has been done when you mentioned Lava and kernel CI. Is there any plan to introduce testing for media as well in the kernel CI infrastructure so that it can be integrated in the media CI as well?
Yes. So basically the idea is by moving the DRM CI over to basically run on top of KCI GitLab and then implement real hardware tests on basically via kernel CI. We basically have built that in then as a feature for KCI GitLab. And when we then put media CI on top of KCI GitLab, you just have the real hardware tests basically on the go.
And just tiny details. It will be not necessary, but testing camera capture, it might be very different than testing display rendering. So it might be an effort that it might be actually instrumented from scratch.
Yeah, I think it's layers. Like the thing that you pretty much get directly as soon as you have the real hardware available is, for example, doing fluster tests with codecs. I think that is a thing that could be really easily done then. Doing more complicated tests with cameras then is I think is step four. Not sure if I'm wrong there, but I think this is something which kernel CI currently can't do, right? Camera tests. And so
we don't have that yet. But we can do. The nice thing is that we have Fluster, a lot of scenarios for Fluster, Chrome OS Tast, and a few other things that you gain as an extra on top of what Media CI already supports. So you don't need to go and implement the test in Media CI. You already have that in kernel CI.
Okay.
Yeah. The basically idea is we already have a lot of work done. We don't want to redo it on media part, and we don't want other subsystems to be redoing it every time from scratch.
So thanks a lot for the presentation. I'm all for having kernel CI on GitLab for desktop. Please remember to ask any other vendors to bring us runners, because otherwise it's going to be a nightmare for everybody on free desktop. So that's something that should be handled from day one, like you need to have some kind of tags or something like that, because otherwise that's going to be terrible for everybody.
Okay. Yeah, I think this is something where we would have to discuss how we handle that. Currently for the media CI, we have sponsored runners. And so I'm not sure how this whole thing would relate to when we have multiple different subsystems using the same infrastructure. So yeah, that's something to be seen.
Just, I'm not really sure I got how kernel CI and GitLab are used there. Will it be like kernel CI is just replacing like the Lava type lab management stuff, and GitLab, we'd still be using GitLab as sort of like the runner and the architecture for this stuff? Or is, as far as I know, kernel CI is not using GitLab.
So one thing that I would like to clarify first is that kernel CI is the initiative. We renamed it, there's a software that was recently renamed to Maestro to avoid confusion. Do you want to add something?
Yeah. So kernel CI is there is a core system called Maestro, and that has an API where anyone could throw test requests into it. So what we want to do is that the GitLab CI infrastructure would just throw test requests into it. Oh, I have this kernel build, this kernel config, whatever. And kernel CI is good at tests. And then you can benefit from whatever we have already. Like, oh, can you also, by the way, also test the Fluster stuff that you have in kernel CI? And you can do that from patchwork. We have a halfway implementation for that, for example.
Yeah, there are two levels of integration, actually, with Maestro that we can think of. One is, as Gustavo mentioned, regarding, OK, just test this for me, bring the results. And the other one would be to just make available the devices, and so users can have a bigger control of what's being tested. This is another path that we could go.
Out of curiosity, which kind of latency are we talking about? Like when you say submit a PR to DRM, once that's all integrated, how much time would it take to get the results of the CI run?
At this point, DRM CI doesn't have any hard time-bound thing, because it's just use it as a tool, so maintainers just execute the test and check the results later to check if everything is fine. In Mesa CI, we have a time-bound of 1 hour, and but we actually need to remove a few tests from it, so we don't test everything, so it to not be a blocker for merge requests. What we do is we do post-merge tests with more like, that takes more time. And if something goes wrong, we notify back people.
Thank you. Just a related question or comment. So if we start adding, for example, yeah, I'm thinking from the MSM side, if we start adding media tests for the MSM hardware, and if we start then adding same tests for the other hardware, would that start delaying the Mesa CI? Would that start? So how should we scale, or how much of the hardware do we need for the, or do you estimate that we need for the existing CI setup? So not from the runner side, but from the hardware side.
Yeah, at this moment we are using. Yeah, Daniel can reply better.
Way more than you think, probably. You know, I guess there's a couple of issues. One is that IGT tends to run long, and media tests tend to run long. Like, you know, they've been made to be really comprehensive, which they are, but you know, a lot of them don't parallelize in particular, which really hurts us, unlike the GPU workloads where we can get in and out way more quickly. Our baseline is 10 devices for any type, because a couple will randomly die on a weekend. A couple of them are going to burn out, and you know, you'll need to just decimate your testing workload over the course of about 5 years because you can't buy any more of them. So I'd say somewhere between 10 to 15 is probably sensible. And yeah, it actually tends to coexist pretty well unless you have, hypothetically, a test suite which runs for 3.5 hours. And at that point, it doesn't matter what the priority is, because half of your devices are buried for 3.5 hours, and then everyone's really angry at the CI team, hypothetically.
Having worked on GitLab pipeline refactoring and stuff in the last year, I've found it to be awkward to be able to run things locally, not setting up a runner and doing the full circle. You really don't want to have a pattern where people have to push to get results, right? If you have a fast machine on your own, you should be able to run things. Is that something you've thought about tooling-wise on this project and help educate people?
Yeah, so we have the same problem in Mesa CI, who is very well established. We have a few scripts that help us to execute locally. It reads, parse the YAML file, understand all the pipelines. You can even put a job ID there and say, hey, produce it. And it will download the Docker file in your machine and execute the test on top exactly how it is executed on the cloud.
Okay, perfect.
One thing as well I haven't really considered with this is how are we going to like workflow this into like the current DRM workflow? How do we? Yeah, I think that's something we need to probably talk about a bit more at some point. Like we've talked about it in the past, but I think I've fallen off that topic a bit. But you know, like how we go? Do we want to aim for pre-merge? But where would we want pre-merge? Or do we want to do it like kind of for me? The ideal thing that would save me time. Speaking purely for myself here, is that instead of people submitting merge requests to like in email, something happens in GitLab or it's pulled into GitLab, and then the tests are run, and then I only really look at merge requests maybe once, twice a week, and if I can just go and go, okay, this is green, I can pull it without having to sit down and then build it locally, because I generally end up doing like 2 or 3 hours of builds locally on every pull. So if that latency wasn't there anymore and I could just go, oh, it's all green, I can trust that this is built and I don't have to care about that. That might, make things easier. Then, but also then something I could push up to then tell me the merged builds still work as well, because there's always conflicts you don't see and things like that. But yeah, that's what I'm trying to work out, ideally how to integrate this into the workflow of what we do. But I think we probably need to discuss that sort of offline and think about it a bit more.
Definitely, yes.
Rob's doing that for DRM MSM, basically. He's guinea pigging it, so good job he's not here.
All right, and I think our time is up with that. I would say you probably know how to contact Helen or Daniel. So if you have any drive to get that forward, I'd say contact them, and then we can see what we can get going.
And also tomorrow we'll have the Kernel CI happy hour. So if you want to join us, we'll also have a booth, which is what time that you mentioned?
Yeah, somewhere in the hallway.
From 3 p.m. Yeah, in the hallway. If you want to come by and talk, and yeah, we'll be there. Yeah. Okay, thank you.
Oh, this is the clicker. Yeah.
You want to start?
Okay, yeah, are you ready?
Yeah. Okay. So yeah, thanks Sebastian and Helen. The next one is going to be Dmitry Barashov talking about MIPI DSI power states and how they work or don't work with DRM. Thanks.
Yeah, more of the don't work. So this is this has been in some discussion and in some troubles for the last, I would say, couple of years. I would like to try to summarize what was on my to-do list, and maybe you will help me to select, or maybe we'll come with another approach, because currently I'm proposing two not so good solutions. So yeah, unless you, well, probably most of you do know that, but MIPI DSI is one of the display buses. It uses packets. It has several lanes, differential signals or three-wire signals, whatever. What is important for us is that it's a bus. You can have multiple peripherals connected to it. Usually it is just one, but there can be virtual channels, and there is a thing called sublinks, where you split the bus for several displays. And it, unlike what we are used to in the DRM, it has 3 bus states, completely off, clock on, and the low power mode, where the slow messages go over the bus, and full video on, where it is in high-speed mode, where all of the lanes are on, and when the video stream is actually going. How does that map to DRM and to the bridge and panel API? So I'm using bridge names, but the same maps one-to-one to the panel, DRM panel. So I hope you don't mind that. So the obvious thing was, okay, first we enable the video stream, we power on the bus, and we then, after that, send the commands. That didn't fully work, and that didn't work for Sun4E, if I remember correctly, because on that platform we cannot send any of the DSI commands after starting the video stream. And of course, it does not show how to shut down the panel, because yeah, we should do that in other way around, and we still are sending the stream, so still no commands. And so this was the try-to, which some of the platforms, including MSM, approached or used. Power on the bus and run the MIPI clock on the from the mode set of the DSI host bridge. Then send the commands from the peripheral, from the panel. Then go back to the encoder to enable video stream. And during the shutdown, try shutting down the panel at some point, but then it almost worked. It was not fully symmetrical, it was not clean, but then there are some special panels, so for example the parade one, which caused a lot of troubles, I think, for one of the persons in the auditory. A DSI to EDP bridge, because it required to be programmed before turning the DSI clock on, and there is no place to do that in this with this approach. So after some back and forth, we landed yet another approach, the ugly, I call it ugly, sorry for the author, pre-enable pref first flag with unpronounceable name, which basically told that if you compare two things, we were going first peripheral, or then the host, then turn on the encoder, and then call enables other way around. So what this flag told, we should first turn on the lower layer and then pre-enable the upper layer. So this allowed us to power on the DSI bus first if the panel or if the bridge required that. Then turn on video stream, then do some final programming, and undo the same thing in the on the shutdown path, on the disabled path. Troubles? Yeah, troubles, of course. There is no way for the host, for the DSI controller to understand if the bridge sets this flag or not, or if it didn't it set it on purpose, like parade, or didn't set it because it was not yet told to set this flag. So we had a lot of issues with some of the panel drivers which were supposed to set this flag but did not, and there is no way to negotiate that properly. And the second point is that it does not cover the case of the multiple devices on a bus, because, okay, the first panel, the first bridge comes up, turns on the bus, and what happens if the bridge on another sublink wants to do something before switching on the clocks or before enabling the video stream? There is no way to synchronize that. So this is the approach that I have been toying with for some time. This is to move the control over DSI bus states from the DRM call chains to actually host driver, and let DSI host call into the panels or into the bridges and tell, yeah, we are going to power on, do your stuff. And we can do this for all devices on the bus. So if this makes it symmetric for several panels or for several bridges on the sublinks, there we do not have a necessity to synchronize them. It's already done. On the DRM thing, it is not so easily mappable, well, not so naturally mappable, because DRM no longer controls the panels. They're enabled by the host, or no longer controls the bridges. They get enabled by the host, or they get programmed by the host calling into that driver. But still, I think that that's a good thing. Problems. So it does not, well, so first, good things. It doesn't require any kind of feature negotiation. You just call into the panels. You can enable that on first on the host, then on the panels. It provides state separation. It can handle multiple panels or multiple bridges. But it still requires rewriting all the hosts and all the clients, all the drivers. And it also, well, I said it enables all the panels simultaneously. But what if we do not want to do that? So the question is, if we actually want to enable just one of the panels on the link. And the last question, which I was not able to solve, is how this maps to ultra low power state. Well, in fact, I should admit I could not fully understand how the ULPS at all should be handled, or if we should care about it at all. So that's a question to you, because maybe you know more than me, or hopefully you know more than me. And another approach that also has been in my head for some time. Okay, this really looks like the runtime power management. Because, yeah, if we have the panel that is going up, it can do whatever stuff it needs. Then it can tell to the host, yeah, dear host, please come up, resume, and then we can start sending the DSI commands. And the same goes in the disable direction. In the disable case, yeah, we first send our disable commands. We put down the host. And then after that, we can disable our clocks, we can disable regulators, we can do something else to shut down the bridge. But again, it still requires to rewriting everything. And it does not solve the case of sublinks. It does not solve the ULPS. On the other hand, and last but not least, it also puts some special note or special meaning to the DSI host being on and off. So currently, the DSI host can do whatever it wants with the runtime power state. It can enable itself or it can disable itself when it wants to. With this approach, now the panel, the bridge controls, and it means that, yeah, if the host is on, then we are ready to send the commands. If you want to point to that out, yeah, I remember that in the documentation for the DSI, we have special comments that telling that, yeah, the MIPI DSI transfer should work at all the time. That's not true. That's probably not true. I think we now have a special comment for that, but still, that's probably not true. So I would really like. Yeah, I would really like to hear your comments. I would really like to see arguments or any comments regarding these two approaches, because otherwise I'm just going to send this approach in a few weeks, hopefully, and look how it maps to everybody else. Yeah, Doug?
I would at least wonder, you have DSI bus callbacks. I'm curious, would it be better to not make this DSI specific and just say, hey, for all bridge devices, you add an extra mode that's, power on that's different than pre-enabled or some essentially add something new to all bridges so that you don't have a weird specific DSI thing. Maybe that would cause more people to shout and yell and flame, but, having DSI specific code is also not ideal.
Yeah, I think that was discussed at the same time as we were discussing the pre-enable first got landed. I don't think, if I remember correctly, that approach was not appreciated by the DRM community and by the maintainers, because it does not really map to anybody else, and there is literally no significant point in doing that. So if you see, this is not the DRM calls. This is really a calls to MIPI DSI device. So the problem and the approach with this, we do no longer call DRM panel functions. Well, we call them through the usual DRM bridge chain calls, but this is no longer required, or this is no longer a required part of the chain. So most of the drivers will not or can skip sending of the comments from the panel enable or panel pre-enable.
Yeah, I think part of the issue has been that so far we've tried to, like from a device model perspective, we've tried to model power state and handle them both at the bus level, like device model bus, and through the framework itself. And so we've been trying to shoehorn a lot of the power state management into KMS, but it's never actually been in place in Linux. All the bus power management for any other bus in Linux is done at the bus level. And so it's difficult to get it to work because we're basically doing what nobody else is doing. So I guess from what you were saying, I don't have any question. Please send that one.
Okay. Which one do you prefer, this one or the RPM one? Because they are both moving decisions to the...
So I haven't really thought about the runtime PM one, but I'm kind of concerned about, so what does that mean for a DSI host or DSI device to be powered on? How does that translate? To which power state does that translate? And so I'm kind of concerned that we will have something inconsistent, and some device will need something and some other will need something else. Probably some DSI device will need to be in high-speed state. Some other will map that to just having the clock lane turned on. And so, how can we maintain a consistency at the framework level, basically? And I think with that one, the one you have currently on display, it's easier to maintain that consistency than it is for runtime PM. And then all your concerns about changing the API, rewriting the clients, even enabling multiple panels, I'm pretty sure we can do something about all of them, writing compatibility layers, adding some kind of mux driver to handle multiple drivers, maybe, I don't know. But it looks to me like those cons are actually much more manageable than they are for, both the other solutions you presented, I guess.
Okay, my only point for the multiple panels, if there are several panels of the same DSI link, I was really hoping that if the hardware engineer is saying that they are related, so we would bring them up anyway. The problem with the sublinks is that I don't really have a use case. So most of our use cases just use a Well, in the best case, it is just a single DSI to DSI connection. In the worst case, it is a bonded DSI with 2 hosts and two bridges or 2 panels or 2 parts of the panel. But I have not seen a use case for sublinks actually.
Well, or it could be like, if we want to go insane, I guess the sanest way to go about it would be to have multiple devices on separate virtual channels. But I don't really see a use case for that, and we would still have different virtual channels to differentiate, and we wouldn't be able to send, well, depending on the bus capacity, but we might not be able to send to both at the same time, so we would have to choose, but we still would be able to choose because, yeah, we have something to differentiate which panel we want to send to.
Yeah, the problem is that with this approach, after the pre-enable finishes, all the panels on the sublink are on and running. Even if we don't, even if we don't intend to send the stream to them.
Okay.
So that's my major concern with this. Yeah.
Just even ignoring the implementation from a conceptual standpoint, if you don't enable all the panels at once, and one panel wants to be in high-speed mode and one panel needs to be in low-power mode because now you're bringing the second panel up later, what state should the bus be in? Like, do we request it to go back to low-power mode, but then, you know, like, is there some sort of, you know, reference counting, or like, how do we manage the state of the bus at that point?
Yes. So we do not support sublinks from the DRM point of view yet. So there will be, most likely there will be a ref count if we get to that point. For just going back and forth to LPM mode, that's what we currently do when we have to send the low power commands like set brightness, which is usually sent in the LPM mode. Yes, it is just set the flag manually on the device, call the transfer, switch it off again. So yeah, this is a little bit ugly, but this is what we currently have, and I don't think we should change that part. Yeah, a question to more hardware people or to actual users of strange hardware, any kind of comments regarding the ultra low power states and if we should care about them at all, or please forget. Okay, silence probably means please forget. Okay, then I think that's it, unless Steven has anything to say about runtime RPM. No, okay, then thank you. Thank you. Okay, then I'll just do it.
Isn't it tomorrow?
Why not? No. I don't have USB-A. Okay. No problem.
Oh, you want to share the screen?
Yes. It's somewhere.
Oh, yeah, yeah.
This one. Yeah. You chose Michael.
Here, okay.
Oh, yeah. All right. Cool. Yeah. That works.
Yeah.
So, I'm looking at, yeah, we still have 9 minutes. Okay. So I'm starting right on time? I can enlarge the screen if needed. Saying this should be Okay.
Hello, everyone. Now we're going to have this session with Luca talking about how to plug DRM pipeline.
Thank you. Hi, everybody. I'm Luca Ceresoli, and this is a start of a discussion, hopefully, about components of a DRM pipeline that can be hot plugged. So I work at Boolean as a Linux kernel device driver developer mostly. I'm working on a project for a product. It's a healthcare product which is going to be launched next year. So it's in an advanced stage of hardware design. It's basically a classic ARM64 product. It's using device 3. It works normally with a specified set of features, but the peculiarity is it has this connector in red in the picture where you can attach an add-on at runtime. At any moment, you can attach and detach these add-on, which that's a proprietary connector. It can add components on some buses that are non-natively hot plugged, not discoverable, including MIPI DSI. So that's the complexity of the project. And on the MIPI DSI, there is, on the add-on side, at least on some of the add-on models, there is a DSI to LVDS bridge connected to an LVDS panel. So this is an overview of the product. The overall solution for the whole thing, the whole product, is to use device tree overlays. There is a discussion about this on Friday in the embedded micro conference. So specifically, this is specifically for DRM right now. There is the latest patches around are the V4 series, which I've sent yesterday just to have the state-of-the-art public before this discussion. If you've seen V3, it's very similar, so not big changes between V3 and V4. The series is about the whole work, and one of the patches is specific for DRM. So this is the goal of the product and of the project, and the approach we propose in the series is the hot plug bridge. So the main issue with DRM is that the whole pipeline is assumed to be immutable except for the panel or display, so what is after the connector. But it's not the case for this use case because there is a bridge, and a bridge is not supposed to be ever removed from a DRM pipeline unless you remove the entire card. But here we want the card to be always present. We have user space, Weston, or can be whatever, which is using possibly multiple displays. It has to be notified when there is a panel attached, adapt the graphics to the geometry, and so on. So the idea was to implement a bridge, a DRM bridge, which is decoupling the two sides of the pipeline, the fixed and the removable one. So this is how it looks when there is no add-on connected. So again, the red block is the connector, and we added this bridge in the middle, which is basically representing the connector. So imagine a bridge, which unlike other bridges, it doesn't have any register, it doesn't manipulate the video, it only has DSI input and DSI output, but DSI output could be present or not. So that's somewhat a bridge in some sense. So the pipeline, when there is no add-on connected, looks like this. There is, in this case, there is a bridge before the connector, which is inside the system on chip. And so when it is running, you can see in the text below, there is one connector. It's a DSI connector. The status is always disconnected because there is never a panel attached directly to this connector. And when there is an add-on present, there will be so the other part of the hardware, and a new connector will be added, will be populated at runtime. That's an LVDS connector in this case. And then there is a panel and whatever, so you can see the connector added using mode test, for example. So there is one connector in one case and two connectors in the other case, and the LVDS connector is always connected when it's present because the panel is always connected to the previous bridge. So that's what works right now in the latest version of the patches. The So the hot black bridge is not, as I said, a classic bridge in the sense that it's a chip with input pins and output pins and registers and so on. So representing that as a DRM bridge is maybe a sort of not necessarily the obvious abstraction. However, it has a lot of advantages we found. So it fully decouples the two sides of the pipeline. So there is the fixed side and the removable side, and none of the other two bridges, the one before and the one after, knows anything about hot plug. They needed 0 changes to those drivers to work with hot plug, which we believe is a great advantage because that would allow any other bridge to be used in that place without any modification. So the Samsung bridge will always see the following bridge, which is the hot plug bridge, that would look normal. And the TI bridge will always see the hot plug bridge before. And when the add-on is removed, the TI bridge is just removed, just like any normal device. So those drivers are not even aware about hot plug. Also, the implementation is self-contained. Almost all the implementation is in the hot plug driver itself. We have a couple pretty small modifications to the DRM core. There may be more needed, maybe for some additional aspects I'm still working on, but it's still pretty self-contained and clean, so not touching too much of the core. That was one of the design goals. It's not necessarily the best one, but that was our idea. And the DRM card is always present, so the user space can rely on that. Current status, so I just sent patch series v4 yesterday, and so the patch number 4 in the series is adding this driver, which is basically the core of the work. It's a pretty small driver, a few hundred lines. There was a little feedback from Maxime Ripard on V1, and then most of the discussion now is in an email thread with Sima after she reviewed my V2 patches with a lot of change requests. Is Sima in the room, maybe? No? Okay, that's said. So work that I've been doing after that is in V3, I changed how the connector works. So I added this LVDS connector, which I described. It is added and removed dynamically based on connection and disconnection. It is inspired to DisplayPort multi-stream transport, the PMST, as suggested by Sima, and I think it was a very good improvement in how the thing is exposed to user space. It's more realistically matching user space. I've also made a small step in V4 to remove the bridge notifiers. So now there's a new operation in the DRM bridge function, so it's not terribly different in the practice, but it's a small step forward. I'm working on other aspects, especially the format change on DSI to notify to the DSI host about format change. But mostly I have some very big open issues still open. So I'm still needing a lot of clarification on the input I got from Sima, because it's, well, some of it is not clearly understandable to me. So I would benefit some additional information on that. And so up to now, Advanced has been very difficult to try to understand all the aspects. So one very fundamental question is what should be moved from the hot plug bridge driver to the DRM core or the DRM bridge core? Definitely something should probably be moved. So the core should be more aware of what's going on instead of pretending it's just normal stuff. But it's not exactly clear. And especially, there is one even more fundamental question, and that's whether a hot plug bridge should really exist or not, in the sense of a struct DRM bridge object. So definitely a connector must be created, but a bridge is not totally obvious that it's a good idea to have it, even though if we don't have it, it's not clear to me how we can keep the card existing when one bridge, so the last fixed bridge, will not see anymore the following bridge. So currently the code is not, no bridge is expects to see the following bridge disappear at any moment. So that would break a lot of things, and I think it would need to rework a lot of things in the core and in existing drivers. So it looks like having the DRM, the hot plug bridge in the middle is still a good implementation technique to have it more transparently into the pipeline. The other aspect is lifetime ref counting. DRM bridges have no lifetime management because they are not supposed to disappear ever, unless the card disappears. And so one proposal by SEMA was to make the connector we are adding already, which has already ref counting lifetime management, to have the connector own the removable bridges. So when a removable bridge appears, get it parented to the connector so that it will benefit from the lifetime management ref counting of the connector itself. That's possible. It has implications, complex implication in the implementation, but I think it's possible. However, there is a suspect that we would need ref counting for the bridges anyway. So that's the other question. And one other aspect, just to mention the big ones, is atomic updates. So what happens if we remove during an atomic update? That's a topic I still haven't opened, so I don't have much material on my side. But so that's the issues I have, the topics, and that's the design. So I'm open to comments, suggestions, whatever. Questions?
I didn't hear the right hand.
Oh, sorry.
Yeah, okay, so, okay. The connectors going being registered and unregistered, that was my comment during the talk, and that's good that they are now appearing. The connectors being removed or unregistered. So that's good that is now a thing. I'm not sure that there should be a hot plug bridge because we have detached operation. Yeah, most of the bridges do not care, and that's a bug. I mean, we have a lot of bugs and we have a lot of issues, I would say, with ref counting with the bridges. So we had those with the deregistration of the bridges, and when the bridge disappears, when the previous bridge already has a link to it. Because usually bridges just take a link to the next bridge and then they store it like forever. So this looks like a thing that needs to be fixed. We need an event, or we need maybe a callback telling that, yeah, the next bridge has disappeared. Or maybe that should be solved using a dev link or in some other way. So that's the thing to do. For the hot plug bridge, I said I think there is no need for a special bridge, but if you have if you think that it's that something needs to track the powering on and off, for example, some electronics in your add-on, then it might be a thing. So don't create it just for the sake of it. If you should need it, if you need to do some things with that, or if you need to link to parts of the bridge chain.
Okay.
That's I think most of my comments.
So the aspect of bridges disappearing. So as you said, there are many bridges take a pointer to the following one and keep it forever, and so that's, I'd say, the number one reason we have the hot plug bridge in the middle, because the previous bridge will get a pointer to the following one, which is the hot plug bridge, and that is not going to disappear. And then the following bridge is, I mean, the hotplug bridge has a pointer to the following one, the TI bridge in this example, but it knows it may disappear, so it treats that carefully. So the idea was, let's put all of these disappearing pointers management inside one small driver, which does that. So that's one main thing it does. And that's, I'm not sure it answers your...
I would say, well, my humble opinion is that I would prefer maybe for the next bridge pointer to go away at all. So make start from the bridges that you own, that you have in your chain, and make them stop using the next bridge pointer by having an easy-to-use API to get the next pointer at the attach and at the detach time, and then all other bridges can follow. I think that is an easier, well, in a longer term, that's a better solution than having a separate hot plug bridge that just fits a place in just for the sake of having a pointer. I mean, yes. Let me explain. So we had similar situation on our platform where we added the aux bridges for the intermediate devices like DisplayPort PHY or the DisplayPort retimer, up to the point where we get to the actual USB-C connector. But they are actual devices on the actual bus, so they exist in the probe, in the device tree. So I would say make that, you can make that a discriminator. If you have a special device in your device tree, then it might have a bridge.
So, yeah.
Won't you need something in the device tree anyway, though? Because most of the bridges, like the DSI M bridge there, would probably try to like look for its next device and not find it, right? And so it's got to point to something that says, I'm expecting to get something later, so it doesn't just fail to probe and say, hey, there's no next device, right? Normally, when they're probing, they look for either the next bridge or the panel, and if they don't find that, I would consider most bridges would just say an error, not I'm a hot plug thing. They would say defer, which would be bad, because you don't want it to sit in a defer loop, right, until someone adds a thing. I don't know, maybe not, but like to me it feels like there's got to be something in the device tree saying, you know, my next device isn't going to exist until someone adds a device tree overlay, and we don't know what that's going to be. And so either you need a separate node that's going to get populated, or you need a property that's added or something. But so maybe there will be a device tree node.
Yeah. And if there will be, I think there will be a bridge for it anyway, because you need to link, if there will be a device node for this hot plug part in the device tree, you will have to have some kind of bridge anyway to link those two parts. That's what we did with aux bridges.
Yeah, so that my understanding is so we could remove the hot plug bridge, but that would mean the previous bridge would need modifications first to know that the following one could disappear and appear at any moment. So that's something like information in device tree. And then it needs to be modified to not hard fail or hard defer when there is no following bridge. And then it needs to be modified to know it could disappear, so remove the pointer, whatever. So this is, of course, doable. However, it looks like at the next design, you change the hardware. You don't use the Samsung DSI M, you use blah blah device, and so you have to modify also that driver again with all of those changes and so on. So that was exactly the idea of let's put one thing in the middle which is valid for every bridge and does all the thing, and to the previous bridge everything looks like it's always present, no problem. That was the idea. So I understand it might be to some extent cleaner to remove that, but it would make a lot of changes needed to the kernel. So I'm not sure. Do you think this is really the way to go? I don't know. I'm okay if the answer is yes. I'm just trying to understand the advantages that might come from modifying potentially up to every bridge driver.
From my point of view, the advantage is to have the Yeah, from my point of view, the advantage is to have a consistent API and consistent use cases for all the bridges, so that there is no, so that there are no two kinds of bridges, which know that the next thing can appear, disappear, appear, disappear, and other bridges that are settled on having.
Okay, so that it would become, let's say, the default that every bridge must expect that the following one will disappear.
Yeah, pretty much like we are slowly progressing towards DRAM bridge connector or any other, any kind of connector being created not by the bridge itself, but by the root driver.
Yeah, I see. So in the case of, like you mentioned, the API looks like, looks like somewhat similar to like the v4l2 macros to send a call to the following or previews, you don't know. Yeah, anyway, an API to tell the DRM core, please tell this thing to the following or previous bridge, whatever it is, which could fail. No? Would that would?
Okay,
let's go for Maxim.
Yeah, no, I think it's quite important that we don't special case it. If we expect bridge to be hot pluggable, then all of them should be, and because like otherwise, basically every driver will eventually have to check whether the next bridge is a hot plug bridge that is, well, each bridge up front will never move. Possibly every bridge after will move, but depending on the hardware configuration, you will not have the same combinations. So some of the bridges will be before on some boards, some of the other bridges will be after the hot plug connector, so it's going to become a mess. And so I think, yeah, the way to handle it properly in the core would be to just declare all bridges hot pluggable, and so at any point in time, you can expect it to go away and deal with that. And so I think in your questions slide, yeah, that one, you shouldn't really tackle all these issues in this particular order. I would first go for the lifetime of counting ownership issues, because there's a lot of bridges that take pointer to the next bridge. It's like fairly common in drivers. So we need to address that first if we want to be able to remove them. And then, yeah, probably dealing with the bridge removal during atomic updates then, and how do we deal with that? And here I think it would be quite nice. So we kind of have a mechanism to deal with the whole DRM display, DRM device going away because it's been hot plugged. And so the way it works is that it sets a flag in the DRM device, and then every time you're supposed to access the device, you actually check if that flag is set, and only if it's not set, you actually do the device access, which is so DRM dev enter exit for reference. And so having a similar mechanism for bridges would be nice, consistent at least. And then I think the two questions remaining, the first one would probably be like, do we need to have a hot plug bridge, which will kind of depend also on whatever the device tree maintainers say. But I'm fine with it either way, I guess. It's not a big deal to me. Either way is fine. We have some drivers that have device tree nodes that are not actual drivers. We have the other way around. We have, it's not a big deal anyway. And what should be moved to DRM core? I mean, yeah, it will depend on whatever we have done before, so it's hard to tell right now. Whatever can be shared, I guess. But yeah.
Yeah, so basically the idea is to have, add a native support for hot plugging to bridges, and then one by one implement it into every driver that needs that. But we'll still keep the old thing around until they are all.
I mean, ideally, I think we can do something that doesn't need to modify each and every bridge driver.
At the same time.
Yeah, we have some functions, for example, that are used quite commonly to get the pointer to the next bridge. Maybe we can just make that function take a reference, for example, and then all the drivers are doing the ref counting properly, or somewhat properly. But so I don't think we need to, like, it's probably a bad idea, actually, to try to make it opt-in. It would be much better to do it in some, possibly with the help of Coccinelle, I don't know, but rolling it out all at once. It should be fairly easy.
I think one issue with getting this done with device tree is that, as far as I understand, the DRM core has no idea about which bridge is connected to which other bridge before the DRM bridge attach call. And to get, but in this case, we, I think we need some to find the previous and next bridge even before the attach function. So the core doesn't know about the connection between bridges natively. I mean, it doesn't know anything about device tree.
Yeah.
So
But I was, sorry if I didn't understand what you were trying to say, but we have some, the core itself doesn't know about basically how the bridges are described. That's true. But we do provide some helpers that are opt-in to drivers to use the device tree to know which bridge is next. So I don't know, it's something like DRM OF get next bridge or whatever, which takes the device node, returns to your pointer. If we can make that return a reference counted pointer, then it should be fairly easy to roll out to pretty much every driver, I guess.
Yeah, but still the single bridge driver, currently the single bridge driver know which is the next or the previous because they know how their device tree is represented. Like they know port 1 is the following or the previous, whatever. The core doesn't. So if like a bridge appears, the core doesn't know to which other bridge it is connected, so it cannot inform the correct bridge. It has to like inform all the bridges, which is what we do now. Inform all the bridges, and then each bridge will go and see, is it my follower or not? And they all will fail except maybe one. So that is...
So you mean when you apply a new overlay?
Yes, yes.
But my understanding of overlays was, so if you want to add a new overlay, you would add that OF graph port node, and so you would get notified, right? Because you added some new node to the device. So
the new node, you probe a device, you probe the bridge driver.
But you have an event mechanism for overlays being applied to device in the kernel.
Yeah.
Then maybe we can just leverage that, right? The last bridge that has been probed will need to have a new port node to get that new bridge. And so we'll get an event from the kernel, so then we can notify the DRM core that there's a new bridge. No?
Yeah, the notification to the DRM core that there is a new bridge is already there. I mean, on DRM bridge add, the core knows, so that's fine. It still doesn't tell anything about the topology, but it tells the core there is a new bridge somewhere. But then the core is unable to find to which other bridge this one is connected. It could parse device tree, but it doesn't know whether, for example, port 1 is the second sync port or the first source port or whatever, so it cannot find the previous bridge reliably.
Yeah, but
it will be the driver itself which will parse its own device tree. It knows that like port 1 is the second sync port, and so it will use that to find its own previous and its own following bridge and then attach to that, so which happens very late. So the core doesn't know up to that point. So there is no way the core can inform a bridge, hey, your follower is arrived. It can inform all bridges, which is what we do now, in v4. It can tell all bridges. There is a new bridge. Please check. Maybe it's your follower. It doesn't seem very great, but it's what we have.
So first of all, as I said, when you're attaching the next bridge, it can look the previous bridge, and then it can actually say, yeah, there is something going with you. So with the
didn't get you.
Well, if you can go back to the yes. So when probing the SN65, you can find the previous bridge and tell it to the SIEM that something has happened.
Yes, that's basically what happens now.
That's one possible thing, and that might also simplify some other use cases in the USB-C stack. And the other pointer or the other idea, maybe I will be frowned upon, is that currently as you said, we build a chain of the bridges during the attach time. That's when we create the chain. But you might very well think about building the chain to the probe time, because that also solves another issue. What we had is that we create the bridge, it gets registered in the core. The previous bridge gets a notification. It gets probed. It finds that next bridge pointer. It stores it, but then for a reason that next bridge goes away. It gets just removed from the system. So there were resource leaks in our case. There were accesses to the unregistered memory, etc., etc., etc. So we solved that by making sure that the bridge is registered last, when nothing can remove that device anymore. But maybe that's also a pointer that, or maybe it points that we should change the bridge chain creation. I mean.
Okay, so thank you. Time's out. Thank you for the discussion.
Thank you, everyone. We have the final slot of today is free, so we can have ad hoc discussions. So if you want, we can continue this discussion there. Okay. So now it's time for the break, and we have half an hour. So we are back here at 5 o'clock. Okay. Thank you.
Laut, oder?
Ja, ja.
Sorry.
Das
das ist
wenn du
Geräusch.
es rausholst, dann auch.
Okay.
Deswegen klingt es dann so.
Gut.
Yeah. Thank you.
And yours is called S for some reason.
Oh, really? Yeah. Serious. Please.
Right, let's get back going again. Now we've all had coffee and healthy snacks. So Tony, Andre is here to prove the widely held theory that the best way to get a talk accepted is to run a microconference and talk about GPU resets.
Thank you very much. Welcome, everyone. So yeah, I'm here to talk about GPU resets again, and hopefully we can get some ideas together on how we can improve on that. So GPU resets can happen after an invalid GPU command when your shader goes on an infinite loop, or when you have some power management issues with the firmware. So there are a lot of things that can cause GPU resets, and The approach that happens in Mesa is that user space drivers ask the kernel if everything is okay, and the Mesa can do something about it. So, but we don't have a consensus here on what should be done, and some implementations believe that they need to queue the Qt app, and also the kernel can detect an infinite loop and issue a reset by itself. So yeah, the question on how should GPU resets be implemented, it's open. Every driver has its own way of doing that, but at least we have a documentation now to try to get everyone on the same page. So this is like the guidelines that we hope that we can get to a common implementation. So every DRM driver has an API for that. So we have one for Intel, one for AMD, one for MSM. So the first question of my presentation is how can we get a DRM API for that? Because one thing that gets on the way here is that GPU resets are linked to contexts, and every DRM driver has its own context implementation. So my first question is, it makes sense to have something like a structured DRM context to help with that? Dave?
There you talk, yeah. I'd have to be sold a lot better. We did have a DRM concept many years ago, and we didn't carry forward with it very much. I think the question you need to answer here is, what do we get from this, from the ecosystem or from the user space point of view? Like, it's like, yeah, we have a commonality here, and it is kind of messy that every driver does this, but every driver has its own command submission API, so you already have to deal with submitting the commands, so getting the reset information by the same API is not hugely, like, what's the win in terms of the bigger picture, for like user point or for the drivers in the user space, what commonality do we get out of this? Because yeah, like there might be some use in having a context in the kernel, but I'm not seeing how much code I'm going to get pulled out of this into a common thing, or how where the big win is, I suppose. Yeah, it's like.
Okay, yeah. My hope would be to get, because nowadays if something happens. That's wrong. Nowadays, if a reset happens, every driver will do something different, and I was hoping that with a common API, everyone would be obliged to go on the same direction. I don't know. Yeah, that was my hope.
I guess the main, or the other motivating thing I can see for it is it sort of depends on what happens with the scheduler, which is pretty unknowable. But, you know, the priority for scheduler stuff is derived from context. So maybe there's an opportunity to like clean something up there if we had a common notion of a context, but. Priority? Is context a meaningful UAPI object? Asked Dave. I mean, it is to all the drivers, but you know, I don't immediately know what we'd gain from having a DRM common context thing as like first class and maybe surface to UAPI.
With that idea that you had of like we could, we could make a sort of everyone operate the same way across the drivers easier, maybe like having like IGTs that sort of define what we want to see, like a conformance thing in the IGT level might be helpful to drive something like that, because then you go, well, at least we've got one test, and if you build your driver towards that, making sure that test works, then you should operate like all the other drivers. Or, yeah, that might be a win I could see making this more useful. That, you know, you could drive this sort of. It's very hard to drive, saying we want you all to operate the same way, but it's very easy to say just pass this test and people may think about it more. So, you know, but I'm not sure again if there's enough right now to just start with that, or whether you want to start with trying to do the test and then trying to work out how it will work.
Okay. So, yes, we need a test for that. And how is the proper way to get this test written? Because I couldn't figure out a way to, from user land, to know that this driver is okay after the reset. Because what we see a lot on AMD GPU is that you just get a blank dark screen after a bad reset. So we need to, I don't know, how can userland check for that, you know?
If AMD GPU, it's a bad reset. No, that's like another, like, there's no way for you to write a test that will make AMD fix reset, unfortunately. You know, it's like, they try and they get a bit further and the next chip might work better, but the 2 chips ago breaks, and it's a constant keeping up to date with. Like, I think Intel and NVIDIA have a lot more robustness around resetting than AMD have, and I don't know how you know it. Like, usually you know because the machine's still running, because otherwise your machine either dies or everything gets stuck in a kernel wait loop somewhere. It's like, yeah. But I don't know how you would definitely say things are good, the GPU reset it, because, yeah, you would have to monitor for about 10, 20 seconds more to make sure you didn't have some thread stuck in a CPU loop forever. And yeah, it's messy. I think one thing that might kind of be useful, and some of them do have this, I think, is a way to trigger a reset through like debugfs or something like that.
Yeah, there's a way to do that.
And maybe, again, that's another thing, if we expose this sort of context thing in debugfs objects, you could then have that API be a standard trigger to trigger resets and make the testing a bit easier. You know, that might be another way of thinking about it.
Okay, so do you think the way to check if the driver is good is like to track for the threads, if they survive, if they are stuck in the I/O control, something like that?
Yeah, I like the way it dies is so bad that it's generally like, yeah, and I've been hitting them all week with AMD GPU again, and it's like it generally just sitting there, and other random CPU threads get stuck waiting for something. It's never, it locks up the K workers, or it does really hard to detect stuff from sitting at your machine, like you've no screen, but you can LS and it might work, or you could LS and it might hang, or you could maybe LS and then you try to sudo and you can't do that because
okay.
Yeah, it's just unstable machine, and there's no way. The only way I could, again, I'm not sure I do it programmatically, but like demessage is usually got the information that either the reset happened or it didn't. So it must be in there somewhere. Like, usually it's like, there may be some way you can hook into the driver and say, did that reset actually succeed at the driver level, and pipe that out. And so I just don't think we report that properly at the moment. Generally, though, if it didn't work, your test is probably going to die before it gets logged to disk. So, it's like... I see.
Yeah, I'm afraid that the driver will lie to me and say that survived, but the screen is just a black screen. So there's no way to, I don't know, poke the HDMI buffer and to check if things are getting there.
Blue? Cool. Yeah. I mean, there sort of is. Like, there's some, you've got Chameleon from Google and other HDMI capture, but that's usually the best way. Like, some of them do have CRC, and I think that's there on some AMD devices, but there's no good standard way that everyone supports.
Okay.
And also, generally, again, if it's dead and you try to do any of those things, it's just going to hang in the kernel. You're not going to be able to make forward progress. The machine will lock up and you'll have to reboot it. So it's like, yeah, it's one of those like, yeah, do I need to reboot the machine? If not, it succeeded. Otherwise, yeah, I need to reboot the machine.
Okay, so in summary, do you believe that things are so fragile right now that I can just check if the system is responsive? That means that reset succeed. Something like that? Okay.
That's probably as close as you'll get. I think there might be worth looking into the drivers and seeing what information that they print and demessage, because like the AMD GPU one generally says the reset succeeded, and when it doesn't usually lie about that.
It does.
Yeah. Or it resets one piece and then the next piece falls over.
Yeah, maybe surfacing up a reset counter into debugfs per device might be a shout, and then just try to run a really basic job, like run a compute shader that pokes a value in memory. And
okay.
That actually occurs after a reset.
Yeah, I think on AMD as well, they do ring tests and stuff after a reset to try and recheck that the ring is at least submittable, but again, sometimes that succeeds and the next thing you do blows up.
We have sort of turned a bit left though from what should the generic DRM semantics of GPU resets be to why is AMD GPU really buggy? One drives the other, unfortunately. I think one thing that is are we trying to aim for 3D driver submitted bad things? That's a different problem than the power management one. Power management going bad usually means that there's something else unstable in your system, and then the reset might happen, and you will probably reset again 2 seconds later. Whereas when you've got an app missubmitting stuff, or you've got a malicious app trying to just trigger resets, there are different things to solve for, and just detecting those and making the semantics around, should I just kill the app, or should I just hang and leave the app stuck in D state, or what should you do in those situations? And I think there's already been a number of contentious discussion, is probably the nice way of saying it, about what AMD should, the user space drivers should do, whether the X server should die. We've had that with Intel, it just exits, and you're like, okay, where did my server go? And it's there's a lot of debate around even how they should operate from the high-level OpenGL Vulkan user space APIs, and they're even specified, and there's still a lot of debate about how we should do it. So,
yeah, I have a slide for that as well. For the OpenGL robustness, there's no consensus on what should we do if app isn't using the robust API. But I don't know if anyone would like to argue for some policy, if we should definitely kill those apps because they will probably just hang forever anyway, or if the user should have the chance to do this by themselves.
Yeah, my feeling on the robustness thing is every compositor should be robustness. Every system app that's generally installed should be robustness. And if it's just a game that's not using it, then killing it's fine. But GTK should all be robustness. All of the things that are drawing your desktop and do things like that should have robustness handling. And this should not be an optional thing for those sort of things. Because, again, killing a game, no one's going to care. But when it's Firefox or stuff, that has an actual user impact, and we should make sure they have robustness used and talk to the compositor writers and say, look, robustness is important. We should be enabling it, and that removes the problem that AMD has created there, because Marek is blowing away apps people care about, and it's well, if those apps had robustness, this wouldn't happen. So why don't we just get the bloody apps?
See, so it's a way to force everyone to be robust, otherwise they will be killed.
The problem with undefined behavior, it's defining it's really hard after the fact. So but there is defined behavior for robustness, so we should just make people use the defined path.
I see. Another problem with GPU resets is that we would like to know what caused the GPU reset in the first place. But this is also very challenging to know. Because a lot of things can be locked inside the firmware side. So my question is, what's available for us in the open source on what should we collect from the GPU resets to get to the bug reports later? What would be useful for us?
So yeah, it's not something you're trying to like analyze programmatically, but just trying to get a bunch of logs to look at by eye later, right?
To look by what, sorry?
By eye.
Ah, okay, by eye, okay.
Is that what you're saying?
Yeah. What I mean, I would like to know what can you get from the driver right now. If you can have like a standard DRM, output.
Yeah, I mean on the ARM side, like speaking both for Mali as well as like for Drino, there is dev core dump, which is really device specific, but that's a pretty good way to, in a nicely standardized way with UAPI, which isn't terrible to dump out a load of relatively free form, here was the state of the device when it went under, and like some things which may have led to it, even like Mali's got firmware scheduling as well, and we can scrape logs out of it, but most of the time it's not the issue there because the firmware's sort of too small to be too incorrect.
Yeah, like an i9-15 has its complete, I don't know if it has dev core dump, but it has the equivalent. It has like its error code thing in debugfs or somewhere that you can, again, it's a lot of information that I generally had never managed to use to fix anything, but I'm sure people have, because it's useful information. But yeah, I don't know if there's a good, I don't know, is FD info sort of useful in this area, or is dev core dump probably more useful?
We tend to use it for the like, something goes wrong every 3 weeks kind of thing. So it's not active polling. It's just have this thing run this test until it eventually dies, and ping us a big old file.
Yeah, like that sort of lot, especially when there's firmware involved, sounds like you would want to dump as much information out, especially if you're looking for power management style bugs where it's like, yeah, that state's just not information the driver probably has. Or, that's the problem, is like how do you distinguish between something that's misformed user space by, that accidentally happens once every 3 weeks. Like generally my assumption is if it only happens once every 3 weeks, it's a power management bug, but that's not always true, but it's usually a good basis for figuring it out. It's like, yeah, that rate of failure is generally a hardware or firmware level problem. Whereas, like every time I run this app and it crashes right here, it's pretty much a memory corruption in the app or a stupidity in the driver. But occasionally you do find, but it's how much information. I don't know if there's any way to standardize it. It might be the mechanism for dumping it. Dev core dump is probably suitable, and we should just push that into more people. But
yeah, I'll just second the state dump. It's really important to get as much information, like whether it's into dmessage or into a dump, as possible about what might have happened. I mean, in a lot of cases, like in our case in Chrome OS, we've got a fleet of devices that we can't hope to reproduce every issue. So what we get from the dump is like all we have to go on. And if it's not enough for us to debug it, or if it's not enough for a SoC vendor to debug it, then the bug just goes unfixed. So it would be nice if you were talking about tests earlier, like in IGT. So if we had some different tests that weren't just hitting a debugfs interface to check the software handling for resets, but we're also doing things like, hey, run an infinite shader and see if it gets killed, or reproduce, have a actual small GPU program that reproduces some hang that we've had in the past, right, with the hardware, some out of bound calculation or whatever it is. If we have things like that, and we can make sure that the drivers are, one, correctly resetting, and two, like dumping information like this is what happened, that would be really helpful for higher level application developers. That, for example, this is something we run into with Chrome all the time. Graphics driver stays the same, Chrome gets updated, Skia changes, it's submitting different GPU commands, suddenly we get a bunch of GPU hangs. Like, what's going on? Well, we don't have enough information, so the more we get, the better.
Okay, yeah, that was okay. right ways.
I mean, having a standardized core dump interface like you were describing earlier would be ideal. The problem is that a lot of times the firmware is out to lunch and not able to populate any data into that.
Yeah.
What do you do then?
Yeah, I feel that. That's why I written in that way, because I feel that most of the useful information is locked inside the firmware, and it's hard for the open source driver to do something anyway, right? Yeah. Do you have more questions, more feelings about GPU resets?
One question is sort of like, do we care about reporting that sort of stuff like to the app? Like, is there a space for like two interfaces here? One for like dev core dump, the whole thing went down, or is there one for like reporting more like this specific app crashed to backtrace in the app, like the same as like you would with a CPU crash by an app, so one is like a catastrophic system crash, and one is like this context with this one app in it has broken, and we just want to report that information in the app standard out before the app dies. It's like, is there two different things, and we should probably try and separate that out a bit to think of what should be in one or the other?
Yeah, I know that Radvi has something for that, because on Mesa you know that you can poke if the context was guilty or not, and I think on Mesa you have an MVVAR that you get there, and every time it detects that it was guilty, it will try to dump everything. But yeah, it's very ad hoc as well.
Do you can sort of dump out all of the BOs and all your state structures, and what's still in the ring buffer, like what you last emitted when it was guilty, but you're not going to get a usable backtrace, right? Because it's turned up sometime later and you're not in that execution flow anymore. So I'm not sure how much useful you can get to apps that isn't what dev core dump can already do, which is, here's basically everything that was mapped into VA at the time. And, here's the ring buffer, and go stare at that for a week. Good luck.
Yeah, it's very hard to link. You have the kernel information, have the user space information, and somewhere that is the problem, but it's very hard to link both things. Yeah. More comments? Okay, I think we're good. Okay. Thank you. Andre.
Okay. This talk summary is we are fucked. On AMD.
Hello. How you doing?
Nice to meet you. Nice, everything was You're a gardener or something.
No, you ever try and do that? That hurts.
On here you've just got the change between the slides. The arrows there.
Ain't no one paying you to go to miles.
Wants to go with the beard.
Daniel.
Daniel who?
Daniel.
Okay.
Daniel Stone. Him and me.
Is Christian König here?
He's my business guy. He funds all my work. He doesn't work for Red Hat. Last year, when was Dublin? No, Dublin was Dublin last year? 2 years ago. At least a year ago. Yeah, it was 2 years. Yeah, it was 2 years. It was 2. No, it was 2 years ago. We were at Dublin. Yeah, at the Dublin.
Oh yeah, it was right after.
At Dublin Plumbers. Myself and Daniel sat down in a pub for about 5 hours and just drank Guinness and figured out the future of the graphics stack. And we're like, that's the only two people we need. It's like,
Well, it sounds promising to me.
it worked out.
UTF-8 encoding was also this guy developed while drinking beer. On a napkin, apparently.
It's like, come on, tell me ideas. And he goes, I'll get someone to do it. And it's like, cool. That one was rather cool. Yeah, it was a good one. But yeah, we also share a birthday 10 years apart. And I've known him since he was about 16. Planning the future of Linux graphics since 2004.
Everything's corrupt at us.
20
behind
years.
closed doors.
Oh, Jesus, all the good stuff
Forcing
happens.
the nasty plans.
All the good stuff happens behind closed doors. You don't fucking actually develop stuff in public. Are you crazy? Do you believe the hype? Drink the Kool-Aid.
I fell for it. Yeah.
Yeah. They talk about it. I'm on a hot mic. I'm going to get recorded saying that. Burned.
Shall we get started? So, hello everyone. My name is Prakash Gupta. I work at Qualcomm as part of Linux kernel team with primary interest in memory, subsystem, SMMU and MMU. Today I will be talking about the need and proposal for supporting a generic restricted DMA buff heap. Let's get started. Yeah, this is the agenda. So while I understand audience may already have some brief understanding of DMA buff and DMA buff heaps, this is just a refresher. So DMA buff heaps were introduced for sharing buffers between multiple devices, primarily avoiding copies for pipelines. And DMA buff heaps provides user-land interfaces for allocating particular type of memory. Currently, upstream supports CMA, DMA buff heaps, and system heap, which allocates from buddy. To support secure use cases, now we can come to the point what should be the terminology of these use cases, whether these should be called secure, restricted, or protected. But in the context of this presentation, we'll be referring them both as protected and restricted. In Qualcomm context, some of these use cases we refer them as secure. So there is a need to support secure DMA buff heaps. And what is the property of these heaps? The specific type of memory these heaps are referring to, they are restricted from HLOS access. The restriction can be partial, say read-only, or altogether there is no access from HLOS. And not only HLOS, different VMs can have different access control for these heaps. And that is the primary need for secure DMA buff heaps. Now, what are the methods to restrict the buffer access? There are XPUs in some vendors and in Qualcomm solutions to protect this memory region. The other method is through type 1 hypervisor stage 2 based restriction. Through stage 2 page table, the buffer access can be restricted to certain VMs. I've given some references if you want to understand more about these in the footnotes. So the question arises why we need protected DMA buff heaps. So the use case requiring protected DMA buff heap, protected buffers. So we understand some use cases should be protected from HLOS access. Now they require protected buffers or restricted buffers. They can take benefit of DMA buff in the mechanism it provides for a pipeline and user space interfacing. Now, below are the few examples in Qualcomm case where these heaps can help. There are secure video playback and fast RPC, CPZ use cases which are needed for video post-processing. I suppose for other vendors, they may have their own use cases which can take advantage of protected or restricted DMA buff heaps. Now, these use cases can also be achieved using custom userland and kernel driver interactions, but there are few challenges what I want to talk about. Now, if I take example of fast RPC, fast RPC use case at present in upstream is able to achieve the functionality of restricted buffers without actually using restricted DMA buff heap. And the way it is done is the buffers are allocated by unrestricted DMA buff heap, which are supported in upstream. And through fast RPC kernel interface, the kernel driver, fast RPC kernel driver protects these buffer using Qualcomm SCM interface. Now, this can be achieved by, now as you see, this is achieved by a kernel interface, but the kernel driver is aware about the specific type of the memory the use case has to use, which is not giving this decision to user land alone. Kernel driver is involved in this case, which can be avoided if we substitute this functionality with a restricted DMA buff heap, where user land alone will have the decision or knowledge about the type of memory this pipeline or this use case need to use. So these are example of some of the downstream Qualcomm secure DMA buff heaps we are using. There are secure system heap, which all of these cases, the buffer protection is through Qualcomm SCM interface. The allocation methods differ. In secure system heap, we have system heap, buffer allocation. In secure custom CMA heap, we have custom CMA heap, which patches are posted in upstream. Secure carve-out heap, there are carve-out bitmap maintained. The buffer protection method in all the cases are through Qualcomm SCM interface. Now, as we see example in Qualcomm case, there are 3 type of secure DMA buff heap required. I suppose in case of other SOC vendors, they may have their own use cases. Now, the common part is any non-secure, any restricted DMA buff heap would have 2 interfaces. One is the buffer allocation, and other is to protect the buffer, their own buffer protection methods. 2 examples I have listed here is Qualcomm SCM assign, and second is OPTI or vendor-specific buffer protection, which may or may not use XPU underlying. Now, each vendor would need a separate heap-based memory protection method. Now, if we implement vendor-specific heaps, this is how it will look like. In Qualcomm case, if we say secure video playback, may use Qualcomm secure pixel heap, whereas in vendors, there can be vendor OPTI-specific and further heaps. So I suppose this is going to fragment the system, and we can have, if we are supporting vendor-specific DMA buff heaps, we are going to have further more heaps. So there was attempt in upstream some time back to support vendor heaps, and based on community feedback and our feedback, the discussion, there was a suggestion to provide restricted heap ops as internal ops on the DMA buff, try to reduce some of the fragmentation arising out of various allocation methods and buffer protection methods. So at present, there on top of these restricted heap ops, few vendors have posted their patches utilizing these heap ops, including Lenaro, OptiIC, those patches are posted. One of the suggestions on top of reducing code duplication by using restricted heap ops is if we can have named heaps based on use case rather than vendor. Now, secure video playback is a common use case. There can be vendor-specific differences in the way they secure the buffers. But from user land, it is one and the same. Do we really need abstraction? Do we really need user land to be aware what kind of buffer protection method the SOC is applying? Yes.
Okay, so user space needs to be aware, for instance, if you actually have intention to only share it between, say, 2 devices, but not the third device. So you actually need to separate allocation to binding to device A and B, but not C. Because I've seen a use case where all memory was, say, assigned into a protected domain. And that included both graphics, but also crypto buffers. And you could dump the crypto buffers using the GPU. So that's why you need to actually bind memory to a device based on the use case.
I understand, but if the difference is only between, say, Qualcomm and other SOC vendor, where the buffer protection method may be different in QCOM SCM and Opti, if based on that difference alone, and the use case is the same from user land, they will expose different named heaps.
Yeah, but my point, say if you have a device with 10 devices, how many heaps would you need, right? So instead, you should allocate the memory and then bind to these and these and these devices. Because then, say, a stage 2-based setup can then just map it into those IOMMUs.
So in downstream, we do have this mechanism, which is a dynamic protection through user space. Now, it is again use case dependent. Some use cases require buffer protection during allocation, where they don't want to pollute the user land, that after allocation, you are protecting the buffer in a second stage, in a next step.
Yeah, my point is that you have multiple stage 2 or second stage page tables that you partially update like one of the devices, but not the other one. So you can't just say you abstract away whether there's a stage 2, because like only the app might know, or something in the kernel might know actually which devices need access to something.
Okay. Yeah. Okay. Point taken. So this is my last slide.
May I add something to that? Sorry, I don't have full experience in the field, but is there no other mechanism for user space to know what device this need to be mapped to? Because this is a problem we are also looking at. Apart from the protection mechanism, the user space also need to describe, okay, map this to decoders or map this to display. So is that something also that has been looked at?
So when you say map it to display, it is from, if I say ARM terminology, these are particular vMITs, or we are saying from attachment perspective in the pipeline. Because if it is attachment, even if we take out a restricted heap requirement, the attachment are still done in the pipeline, where you export the buffer and various devices can attach to it in a non-protected use case currently.
Yeah, but to user space, generally, it's just like clubbed up as one name of a heap.
Yes.
Can we not like do more granular level? Okay, this particular trust zone protection and these VMIDs.
Okay. So in downstream, we do. In the reference I was giving for secure system heap, they are named heaps where every vMID, a separate heap is exported to user space, and so they can directly allocate from the named heaps. there is no metadata, side metadata provided from user land that though we are using restricted heap, but this is the type of restricted heap I need to allocate. So it is explicit in our case. But it does increase the number of heaps multifold. And as we mix up number of SOC vendors, then it is going to explode.
Yeah, excuse me if you already said that. I missed the beginning of your talk. But why do you need the separate DMA heaps at all? Why can't you just export the buffer from the one device and then import it to another device? Because both secure playback and what you said about the video processing from, I think, Iris through the fast RPC or from a camera covered by allocating a buffer by one device and then import it to another device.
So that is the case where it is not restricted buffer. So where we need to apply certain restriction on the buffer where HLOS or particular VM cannot access, that cannot be achieved with the existing heaps. Unless there is a, like the example I gave of fast RPC, unless from user land to kernel, the example fast RPC, they intimate fast RPC driver to apply that restriction after allocating the buffer.
Specify the restriction when allocating the buffer to the device that allocates it.
So the allocation is happening with the DMA current case. If you see during DMA buff heap IOCTL call, where from user land you are indicating to the DMA buff heap to allocate a buffer whether as scatter gather buddy or from CMA. So that's where it is the allocation is happening currently. You can have other methods, like you can do directly from the kernel driver, you can allocate, okay? Yes. And you can have your own custom interfaces, but that does not fit into the DMA buff. The core idea here is we are not keeping the logic, what is the use case and association to protection method in kernel. That control we want to keep with the user land, because it is more aware about the pipeline elements. Okay, and whether it is a secure use case and it wants to apply that, the protection.
The user space can easily fail to do that if it's not done properly. And also, I'm just slightly resistant to the idea of generic allocators.
Mm-hmm. Okay.
Dave? Yeah, I guess I think it's really, really hard to abstract away the semantics, like, just having a heap called SVP, which is, enough for a certain level of widevine, like that is really appealing in a lot of ways, but it means completely different things on different platforms. So you can have codec and display only. That can be enforced by you take page faults if you try to map it to the GPU, or you read nonsense if you try to sample it from the GPU because the encryption key hasn't been applied if it's actually encrypted. Or some of them are the APU takes a hard reset that's out of your control. So I think at some level, user space already has to be pretty well aware what level of protection it's going to apply, because it has to tell downstream elements. Like if you're trying to do SVP on a platform where you know that the display controller will get your video on a plane no matter what, then that's the way you can configure that for that platform. But you also need to tell the display path, you cannot import this into the GPU. If you need to fall back to the GPU for any reason, then just don't even try, like show this as black. Whereas on other platforms, that you're not going to hit direct display paths, and whatever the platform owner is has sort of made that decision that accessing via the GPU is okay. Or another example is, you know, if you don't have HDCP, then you have to downgrade content over an external link, but what's an external link varies a lot depending on the use case. Like, you can have an extremely non-secure external display link, but if it's in the back of an airplane seat, the odds of someone disassembling it and, you know, actually intercepting that are low enough that it's still considered secure. So I just think there's so many platform and product specific things that you can't just say this is SVP and still have it actually be useful to user space as much as it would be good.
Okay, but that would require user land having awareness about various vendor heaps, and based on the platform, they would need to you know, tie the use case. There may be different steps, but in case there are no differences, just the buffer protection method is different, and that's why now the vendor has a different named heap. So that abstraction now has to be within user space somehow.
Yeah, I think so. I mean, there's already so many hoops you have to jump through to get the content providers to trust you that, you know, that boat's already kind of sailed, I guess.
So this is my last slide. To utilize these heaps, as I said, downstream we have these heaps. On upstream, we are trying to make support for secure video playback and other use cases which require protected or restricted DMA buff heaps. So we have posted secure system heap examples. Secure context bank support we have posted. Now, other vendors, so far what posting is done, the buffer protection on the SMMU side is done by Opti or through SCM, the Trusted Execution Environment. In our case, it is through HLOS. So ARM SMMU driver having support of securing the page tables. So that support we have posted. And that is, so far currently it is Qualcomm ARM SMMU driver specific, but it can be extended to any other vendor who want to utilize HLOS based page table protection. Iris VITC a non-secure support that is posted, and Iris VITC secure support will follow. So once all these building blocks are in place, we should be able to support secure video playback and other secure use cases on Qualcomm platform. Yeah. Any questions?
Okay, so just to explain to everybody else, Iris VITC is the video mem-to-mem decoder. Maybe that makes your life slightly more obvious to other people in the room. And that's actually my question. So if you say that the DMA buff is allocated from the external heap, and then it is either allocated as protected or it is later said to be protected, how can you make sure that rogue user space does not give unprotected buffer to the VITC driver and tell that, yeah, it is purely secure, please decode high quality video context to it?
So it is enforced through access control. So various vendors can have their own different ways to enforce access control. But in type 1 hypervisor cases, the way it is implemented is, as I said in my talk, SMMU has also support for secure page tables. The end-to-end, yeah, I'm coming to the answer. So if let's say the user does not allocate from the protected buffer, okay, and it allocates an unprotected buffer and try to configure rest of the pipeline for a secure use cases. Now the hardware would utilize that. In ARM we have configuration like SIDs for accessing, tagging every access along with the SID. So for use cases which are tagged differently for secure and non-secure use cases, so you can assume in this case non-secure buffer will be tagged with secure SID configuration, and that access will not go through.
So what does that mean? It will crash the machine?
It will crash the machine.
Oh, so thank you. You just crashed my phone or my laptop. Can we not do that, please?
So I'm not entirely sure whether this part where user can completely start, but I'm saying if it is able to do that, then access control will catch it.
Yeah, so this should be handled by the driver, not by the user space. Because otherwise, you have just crashed my laptop. So, yeah.
Yeah. So my understanding is, I have limited understanding on the video driver side, but there will be usually checks on the driver side about pipeline establishment, okay? Not, so I may be contradicting myself on the driver awareness part, but if somehow those checks are not there and we are able to provide a buffer which is not secure, a system would not allow it from access control perspective. But yeah, you may be right. In case if driver is user is able to allocate, then there can be issues. Yeah. Okay.
Who is the consumer of these buffers? Is that secure world, or are they also mapped to like non-secure VMs?
So these are protected use cases, as I earlier mentioned. So protected not necessarily means secure. So secure traditionally people refer with trusted execution environment which can access. Protected is what non-HLOS, HLOS has certain restrictions on that buffer. By consumer, we are talking about DMA use cases. So DMA engines are consumer of these buffers.
But they must be like CPU accessible by some entities. Are these trusted apps? Are these
not necessary? CPU can still have just a control path where it may or may not necessarily have data access to these buffers. So it is just setting up the pipeline.
So who writes to these buffers then? Directly hardware?
DMA, yeah. Hardware.
Which hardware?
So like in secure video playback, you can have video IP will be accessing these buffers.
That must be software.
No, the hardware components. So these are, so DMA primarily we are using, DMA buff we are using for the DMA pipeline, and these are DMA engines who are consuming and generating these buffers. So not necessarily, there can be cases by restriction, the restriction can be that it's accessible by both HLOS and non-HLOS, but it is again use case dependent.
At least the beginning of the pipeline to be CPU accessible, like if it is decoder, the input to the decoder will be decrypted content, and that will be...
The control can be...
Okay, so that is for hardware decryption and hardware crypto engines. So, thank you.
Okay. Any questions? Thank you.
Okay, thank you everyone for attending the DRM and graphics micro conference. See you next year.
looked the thing up. There's a bunch of problems. Haven't really looked into the reset problems yet. I'm currently trying to solve the memory leaks that it has. Even documenting it can help a bit. Trying to use it in a dummy driver and it just starts exploding like 500 times. Basically, don't follow that rule, don't follow that rule.
Are you also
Where's the Rust driver? Co-developing, I had co-developed PCI abstractions. Now I'm a bit out of the loop, but I'm trying to basically half the way on the C side. So one of the reasons we've been looking at the scheduler, because put Rust on top of it obviously has to be safe. When the C part is leaking memory, obviously kind of surplus. So your job is more, why have you been looking to offer? I need something useful.
When you can tell it fast.
One of the issues we can tell you is it's very bad for user experience to have to use the games. So yeah.
So Steam Deck hardware is obviously
yes, Steam Deck hardware is only one hardware is in GPU and
Like compared to doing GPUs.
I would not bet. I would not like on the GPU we write.
what were the issues you're running into? It sounded as if user space is doing something fishy, then it should happen, and you don't know if it happened or not, and sometimes the screenshot goes blank and you don't know why. Is that the situation? Yeah, that sounds shit. That's really a mess.
I take care of the... I just take care of the kernel side, and then there's a bunch of people trying to take care of the HDD side. And one thing that they need from the kernel is information about
It seems to be a bunch of pipeline steps.
we talk about most is
more general purpose code.
I was trying to...
Even if a GPU, like, just to get anything, you still need to find about
Definitely be doable that we'd have a way now or later to detect if the reset command actually has been submitted to the chip. Right? You don't really know if the firmware
which you do not know, which you do not understand.
when it is complete. Would you say that's correct?
You don't have to actually problem is
just like hope some stuff randomly and see what
yeah,
happens.
you change the hue and color. Can get information from registers, etc. But in difficult mean that after a reset you can't just any register.
Oh man, we've got this guy who's working on HDR
According to
stuff.
them, I can even.
It's amazing when you
I shouldn't rely on information after the reset.
It's got like the sun right behind it.
So yeah.
So he joins the call and
In practice, on the Steam Deck, what is the typical
so you can see
problem?
this really nice artful window and the rest is all dead.
Yeah.
And then AGC kicks in and suddenly it's like you can see his face. Sun's all reflecting off. It's like
Protect the hands.
the HDR experience like my retinas have failed.
Typically, the user space applications of a video game, for example.
So we're at the point.
Invalid command buffer, or what's, have you analyzed it? Do you know? The user space typically does for that.
It's getting there like maybe on the translation layer. It's all pretty well fleshed out in possibilities and stuff. It's just pushing down to cadence.
So we have a lot of things on this deck.
Currently, Mesa communicates with the kernel driver, right?
And everyone else has like
By you means the guy who tries to figure out what's going wrong, also talking to the driver through Mesa exclusively? Or the other means you're using?
For the just use Mesa to figure out because Mesa will have proper objects, so to require the kernel because if you need when you want to ask for GPU information, the driver needs to know them, and yeah, it's probably the same as
No one knows that yet.
after resets. Your problem seems to be actually just a lack of information, right? Yeah. But even if you had the information, you would still be spiritual, wouldn't you? I don't know. I really don't know. I don't know what
How much of this shit do we have to disclose?
In the case, the reset works, right? When things start rolling again sooner or later. Yes. In the bad case, it doesn't work, and you don't know why. And you would like to know why, and then down the road, you would could discuss strategies how to solve it. But so far, we don't even know what the problem is. Oh, that sucks.
Yeah.
Look, but
so, what's the name again?
Yeah.
Yeah.
I'm definitely interested in
the memory stuff doesn't seem to
you forwarding information. You see my email address on the list?
Yes, I am. You are as well?
I am, yes. I won't be able to remember your name most likely. I should write it to my notes. Or take a picture even better. And Google also knows that we talked. It's certainly handy. We can Andre or all the, like, sheer coincidence, all the Red Hat office managers in Munich are Portuguese.
What? Oh.
I suspect that they have a cartel when hiring people.
Oh, that's okay.
It's illegal officially, right?
Yeah.
I know we can. I saw you posting. You probably saw me posting too.
I don't remember the name.
I just a few days ago asked for the maintainership of the
That's going to take that.
That's not my part. If you're excited about showing your it's working with me, right? So.
Oh, no. I feel sorry for Dimitrios Sapenko, who did the generic shrink stuff, which I think got to like V30.
I made it to time. What was this?
Generic DRM shrink to evict.
Oh, I think that was for Rob Company. Yeah, because he cares about GPU, I care about that's kind of a deal. So I've been up at the beach and care about the display. Rob and Connor and all the other people. Smart people who care about GPU.
Yeah.
How far is it?
No.
Hey, how are you?
So they both.
The buff is this, yes.
Yeah,
The buff.
this is the buff. Okay, it's good. 4 people.